ICVGIP 2020. We have a packed schedule and we are starting our day with a very interesting tutorial from Shubham Tulsiani. I'll just hand over to Siddhartha to introduce Shubham. It's all yours. Go ahead.
Actually, sorry, I might again need to change system permissions for me to share screen, so I'll quit and join in a minute.
Sounds good. Yeah, I'll introduce you after you join back in.
Okay, sorry about this. Yeah, thanks. Sorry about that. I think it should work now.
Awesome. Actually, Shubham, could you just open the opening screen of your slide just so that we are sure that it works? Perfect. Okay. Sounds good. Yes. Great. All right. Let's start. Welcome to this first talk of the day, which is a tutorial by Shubham Tulsiani. I am delighted to introduce Shubham, who is currently a research scientist at Facebook AI Research in Pittsburgh. He got his undergraduate degree from IIT Kanpur and his PhD from UC Berkeley, working with Jitendra Malik and Alyosha Efros. And he will shortly, in 2021, be joining Carnegie Mellon as an assistant professor, and we wish him all the best in the new job. And Shubham is an expert in computer vision. And while some of his recent work has focused on robotics and robot learning, he is also an expert in the specific topic of this tutorial, which is computer vision at the interface of the 2D and 3D modalities. And he's published a number of wonderful papers on this topic, which I've been following for a while. And I am very much looking forward to this tutorial, and I'm sure all of you are too. So Shubham, over to you, and take it from here.
Yeah, thanks a lot for the wonderful introduction. I'm actually originally from Jodhpur, so I kind of saw that the conference was supposed to happen in Jodhpur initially, and then given the times it's not, so I'm slightly sad that this is not in person, but again, thanks for joining very early in the morning for you. And I think maybe before I start, a couple of things about maybe the organization of the tutorial. So I think I'll try to leave ample time for questions, and I've kind of structured it so that it's roughly 90 minutes of me speaking and hopefully about half an hour of people being able to ask questions. And I'll try to have sort of breaks at 30-minute intervals if people have any questions then. So I think there might be a Q&A, so please feel free to keep typing in questions, and hopefully I'll get to address them in between the talk, or if there are many more questions, then maybe later in the talk as well.
Let me just jump in here to interrupt for a moment. Audience, there is a Q&A link in the WebEx panel that you should see on the right. Please do type in your questions. I will be following them and relaying them to Shubham as you type them in. Okay, sorry, go ahead.
Yeah, okay, thanks for that. Yeah, so with that, today I want to talk a bit about learning single view 3D prediction. And again, as you'll maybe see through the tutorial, it's sort of a very, very broad area, and unfortunately, we'll not be able to go into all of the details. But I really hope that all of you take away at least the high-level ideas of this research area from this talk. And in particular, if some of the initial concepts or some of the key ideas are not clear, please feel free to ask questions specifically on those as well. And I hope that by the end, you at least have a very good sense of the lay of the land in this research area. So yeah, with that, I'll get started. And sort of just as an initial motivating example, let's consider this particular image that you're all hopefully seeing it. And over the last decade or so, the computer vision community has made a remarkable amount of progress, right? That uh, the state-of-the-art systems can analyze this image and tell you a lot about it. And just as an illustration of this, if I take this image and feed it into Google Cloud's computer vision API, which is maybe a representative state-of-the-art system, it very, very quickly and very, very accurately tells me that, this is an image of a living room. There are some furniture items in it, that, in general, this is some sort of a room. And it can even name some of the objects that are present in this image. For example, it understands that there's a coffee table somewhere, there's a couch somewhere, and so on. And in fact, we can actually do better than this. The state-of-the-art systems can do much better than this. They can analyze more or less the pixels of this image and demarcate the pixels into different objects. For example, we can, let's say, this particular annotation was obtained by a system called mask-RCNN, which can very easily tell me that on the left, there's this couch. It can pretty accurately identify all the pixels that belong to it. And similarly, for all the other objects, it can identify the pixels that belong to the chair and so on. But both of these examples that I showed to you, one where we were naming the different objects that are present, or in this case, naming and demarcating the specific pixels, are really just trying to understand this 2D representation, this 2D image grid of pixels. It's just trying to give names to the entire image or to pixels in this 2D representation. And what this pursuit of classification or detection really misses is that this original image that I was showing to you is really kind of a window to the 3D world behind it. That, this image is something that someone just captured from a specific perspective, but really it's a 2D representation of an underlying 3D reality that lies sort of behind this image. So, just as a conceptual thing, you can think of this image as just a painting that an artist made to depict the real underlying 3D world. And sort of, again, from a perspective of a robot or any intelligent agent that wants to act in the world, you don't really care about this image. You care about the underlying 3D world. For example, if this robot needs to go and clean the chair behind, it needs to understand that there's some free space between the couch and the table that it can walk through, that the chair is actually far behind in the scene and the couch is closer on the left. It needs to understand maybe the shape of the couch if it wants to adjust it in certain ways and so on. So really, an image is just an agent's window to the underlying 3D world. And the goal of this talk is to figure out how is it that we can, given this sort of an image, get some understanding of this underlying 3D physical world. So sort of to be more concrete, the task that I want to talk about today is that of being able to predict the underlying 3D representation given a single 2D image. So given an image such as the one on the left, we want to be able to predict a 3D representation of the underlying world that lies behind this image. And sort of, when I say this, being able to infer 3D representations or being able to infer 3D reconstructions, some of you who have been following the successes of computer vision over the decades might wonder why is this hard, given that you've seen many successes. For example, some of you may have seen systems that can reconstruct entire cities or entire sort of tourist hotspots, such as the Roman Colosseum. So this image here is from a very famous 2005 paper by Noah Snavely and colleagues. I think it was called Building Rome in a Day, or maybe that was a follow-up one. But essentially, given many images just taken from the internet of tourists who are going around the Colosseum and clicking pictures, they can reconstruct this very, very detailed model of the Colosseum. And if I upload a new image of the Colosseum, they can precisely identify where that new image is taken from and what's being depicted in that new image as well. And it doesn't really work for just this particular example, but for many other cases as well. For example, sort of in the middle, you can see the Statue of Liberty, again, reconstructed given many images, or also some pyramid in Egypt, which again, we can get pretty accurate 3D models from given just raw images. And if someone else is taking a new image, you can again identify where that new image is being taken from and identify what is being seen in that image. And this particular success of being able to reconstruct very precise models from images is not just limited to sort of monuments and statues, but can also be applied for specific things like some of the sculptures in museums. So this is maybe one of the initial examples where 3D reconstruction or 3D scanning was really shown to work, where there was a massive funding on being able to obtain very detailed models of some archaeological artifacts, such as this particular statue. And this is just an illustration of the 3D model that they could recover given many scans. And this technique has sort of since matured, and we are able to also use this technique to reconstruct not just statues, but more complex things like sitting presidents. For example, this is President Obama being put in front of a camera rig that is really trying to capture the 3D structure of him. And just sort of a fun fact, on the person standing, the person standing to the rightmost is actually Paul Debevec, who is in some sense my academic brother. He's my advisor's he's my advisor's student and has had a wonderful career in Hollywood and academia, and of course got to meet President Obama and scan him and get results really like this, where given Obama sitting in front of a camera rig, you can obtain extremely precise, detailed, and textured models of the sitting president. So what I've been showing you so far were these amazing successes, right? Where we can obtain very precise, detailed 3D models of all kinds of things, from cities to particular statues to actually sort of even indoor rooms, which are not shown, to presidents, and get this rich and amazing detail. So the question that one may have is, why is this task that I'm talking about different? That we can get 3D reconstructions in detail of a lot of these things. So what's so different about this particular task that we want to talk about today? And so the real difference, the key difference, is that what I want to talk about is trying to infer 3D structure given just a single image. So all of these successes that we have seen across decades have really shown remarkable results of being able to infer 3D structure given many images. So there was this entire camera rig in front of President Obama, or there were these thousands of tourist photos of the Colosseum. And by integrating information across these many images, we could obtain very precise reconstructions. But our goal in this talk is to understand how, given just a single image of a new scene, such as one that you may randomly encounter on the internet or a robot that's new to your house experiences, given just the single image, how can we infer some 3D representation of what we see in there? And this sort of difference that we have access to just the single viewpoint of the underlying world is what makes this sort of problem very challenging, as we'll also see a bit later. So sort of to reiterate the task again, given just one image of some new scene that we are encountering, whether taken from the web or a robot in your new home, we want to be able to understand some 3D representation of what we are seeing. And so far I've been talking about this in a bit abstract, but to maybe really concretize the task, there are actually two questions that we must think in terms of. The first is, when I say that we want to infer some 3D representation, we must understand what representation is being talked about concretely. What do I mean by some 3D representation precisely? And sort of the second thing is, of course, a bit tied to this, which is, how is it precisely that we are going to infer this, whatever target representation that we have in mind? Operationally, how is it that we'll be able to infer this representation given a single 2D image? And in most of the time in the tutorial, I'll actually focus on the question of how. But before we can do that, I want to give you a brief overview of what are the different possible representations that have been pursued, just so we have a basic understanding of what are the different possibilities there are to choose from when we are talking about 3D representations of objects or scenes. So one of the more popular ones and the commonly used ones is in the form of a depth image or a surface normal image. So on the left, we are seeing an image of some scene, and in the middle, you see a depth representation of it. So in the colors that are shown here, blue indicates something that's closer to you, red indicates something that's further from you. And similarly, surface normals, so depth indicates how far a particular pixel is, and surface normals are supposed to indicate what the orientation of the local surface at that region is. So again, in terms of the colors shown here, A purplish color indicates that the surface locally at that pixel points up. A greenish color indicates that the surface points left, and so on. So both these representations, depth and surface normals, are essentially pixel-aligned representations. For each pixel, depth tells you how far that pixel is. Surface normal tells you the local orientation at that particular pixel. And because these are pixel-aligned representations, they're actually very easy to use and predict in learning-based systems because, for example, you may be all familiar with something like semantic segmentation systems, which again predict per pixel semantic outputs. So essentially, any convolutional network can very easily predict these pixel-aligned or per pixel representations, such as a depth or a surface normal. And they, in fact, tell you a lot because you understand that given this image, all the pixels on the bed have a surface normal that's pointing up, or that the wall is further from you than the bed is, and the depth image can tell you these kind of things about the 3D structure of the scene. And while they tell you a lot, there is some fundamental limitation to these representations. Because these are pixel aligned, they cannot really easily tell you about the hidden stuff. So given the image on the left, you all understand that the floor continues below the bed, or that there is a wall that continues behind the bed. But a depth or a surface normal representation just cannot tell you this because it only models information about the visible aspects of the scene. For all pixels on the bed, you have some information, but for the pixels that are not visible, for the part of the wall that is not visible, a depth or a surface normal representation doesn't tell you anything because it is pixel aligned. So while it can give you a great amount of detail about the visible aspects of the scene, a depth or a surface normal representation just fundamentally does not tell you about anything invisible in the scene. It doesn't tell you about the underneath of the bed, doesn't tell you about the floor below the bed, and so on. And so David Marr, I think, coined this term that these representations, these pixel-aligned representations, are in some sense 2.5D representations and not really 3D representations because they don't tell you about the full scene. They only tell you something about the visible aspects of the scene. And so one other representation that is sort of more 3D is that for volumetric representation. So here I'm just illustrating it in context of this particular object, where you can essentially imagine a grid and dividing that grid into many, many tiny cells. And for each cell, you can store something that this particular cell belongs to the object, this particular cell belongs to empty space. We can even remember the color of each cell. And so you can think of it as essentially a 3D grid-like representation wherein each cell we are storing something that, for example, occupancy and color. And this representation, again, is very general. It can very easily let you represent different kinds of shapes like tables, chairs, bottles, entire scenes. But it's very memory intensive because it's representing the 3D space. And so the complexity of this representation goes cubically with the amount of detail you want. If you really want to model the shape of the legs of this particular chair very accurately, you'll need an extremely high resolution representation. And because the complexity is cubic, this becomes extremely memory inefficient if you want to model very high level of detail. And so as an alternate 3D representation, another popular one is that of using point clouds, where you don't represent the empty space, you only represent samples from the surface. So for example, if we see the car in the middle, there are just 1,000 points, let's say, that are representing different random samples from the surface of the car. And you should note that the order doesn't matter. If I just give you 1,000 points and shuffle a couple of them, they're still representing the same sort of set of samples. And again, they're very memory efficient compared to volumetric representations because we are only representing samples around the surface. Empty space is not really contributing to any samples. But unfortunately, they don't explicitly represent geometry. These are just point samples from the surface. But if you, for example, look at the table that's shown in the middle, to understand that there's a flat region at the top, it's extremely difficult to get that intuition by just looking at random samples from points. There's no information being encoded in this representation that there's a local surface that is flat there. And sort of while you can add bells and whistles to this representation to encode some local information like that, overall, it's extremely difficult to get them to represent very coherent geometry. And so one other extremely popular representation for 3D structure is that of a polygonal mesh, where we now have vertices as well as their connectivity. So for example, if we look at the pyramidal structure on the left, we are storing not just the vertices of the triangle, but also that they are connected to each other and form the triangle. Or there's a rectangle at the top right of the pyramid. We are again storing not just the location of those vertices, but also that they connect to each other in this sort of rectangular way, and all those four vertices form a face together. And again, just like point cloud representations, this is pretty memory efficient because you're only representing the surface and not really caring about the empty space. And I'll not go into too much details of why this is the case, but you can think of each face as being sort of a planar region that you can texture by drawing an image or painting an image on that planar region. And so this mesh representation is extremely easy to texture and render. But from the point of view of learning-based methods, it becomes pretty difficult to handle varying topologies. So if you look at the donut or the toroidal shape and look at, let's say again, the pyramidal shape on the left, they have very, very different vertex connectivity. The face matrix F or the adjacency matrix F across those meshes is extremely different. And being able to design neural networks, for example, that can predict such diverse topology is extremely challenging. And so maybe one last representation I want to mention, which is actually a special case of mesh-based representations that is very popularly used in 3D prediction, is called a morphable 3D model. So in this, we start with a fixed base mesh, such as a sphere, and we say that this representation can describe shapes by deforming this base mesh. So for each vertex, we can specify a new location or a new position, such as I'm showing sort of a new position for the red vertex. And if you specify maybe new positions for all the vertices in a sphere, you can maybe construct a bear out of it. But you have a fixed connectivity. So the connectivity is assumed to be the same and fixed as that of the base mesh or the sphere. And you're only allowed to change the vertices, the position of the vertices. And again, same as meshes, it's extremely memory efficient, easy to texture and render. But as I mentioned earlier, we are assuming a fixed topology. So this can only describe very limited variation. For example, you can never deform a sphere to describe a shape of a donut or a torus because you can't really construct that hole in the middle by just simple deformations. So in some sense, it's only a special class of the mesh representation where you're fixing the connectivity. But I'm just mentioning it especially because this is one of the more popular representations used when people learn 3D in 3D inference. And I've gone into detail of some particular representations, but there are actually many, many more possible. For example, CAD designers use something like CSD trees to construct complex shapes out of subtraction, addition operations on simple primitives. Or there are extensions of depth images that can let you handle the invisible surfaces in some way. And maybe similarly flavored extension of depth images called multiplane imaging, where again, maybe I'll skip some of the details. And there are just many, many more representations of 3D structure that are possible. And what I really want you to take away from this is that there is no best 3D representation. It really depends on the task. Different representations have different trade-offs. And for example, if you were to come to me tomorrow and ask me, which is the one 3D representation that you'd recommend to me, I really won't have an answer for you. I'll have to ask you about more details about what you're doing and then think about it in terms of the trade-offs. For example, volumetric representations are pretty general, but memory, expensive in terms of memory. Depth representations are very easy to predict, but cannot capture invisible surfaces, and so on, as we sort of discussed earlier. But really the main takeaway for you should be that there are many different kinds of representations, volumetric, point cloud, etc., that each have their own sort of benefits, while also having some particular limitations. And as long as you have them in mind, you'll hopefully be able to realize which of them is more suitable for your particular application. But there are these many possible ways to represent what you're seeing in a particular 3D scene. So yeah, we talked a bit about what kind of a representation we can use. And for most of the tutorial, we really want to focus on how is it that we can predict some of these representations given just a single 2D image. And before even going into discussing any specific approaches, one thing we really need to internalize is that the task of inferring 3D from a single image is an ill-posed one. So, maybe some of you are familiar with this particular illusion called the Ames room. And given this image, I assume all of you are seeing that the person on the left is much shorter than the person on the right, and the person in the middle is of some sort of an average height between the two. But the reality in this case is that all three people are of the same exact height, and it's the room that's shaped a bit weirdly. For example, the room is trapezoidal, and the left wall is actually much taller than the right wall. And it's been constructed in a specific way to give you an illusion because you expect some sort of regularity in the world that the person on the left is much shorter, but that's not really the truth. So this sort of an illusion just illustrates that while the actual 3D structure is something different, you can imagine some other thing that consistently explains what you see. And given just this one single image, both of them are kind of equally plausible. It's just if I tell you that the structure of the room is as shown on the right, that maybe you understand why this is happening. And maybe just another example of a similar optical illusion is that as you move the camera around this particular animal, you imagine that its head is moving around, but of course it's not really moving. Also, you presumably think that the head is kind of not carved in, but carved outside. It's sort of not, it's more concavish as opposed to convex, but that's not really the case. And it's just kind of something that your mind is making up to explain what it's seeing in this image. And more than these optical illusions, here is maybe a slightly more concrete example where if I show you the image on the left, one plausible explanation of the underlying structure is that there's some sort of a folded paper with different, slightly different shading across different horizontal lines kept on some sort of a floor, for example. But there are actually infinite plausible solutions. For example, it may just be a painting of a paper. It may be some sort of metal sheets that are cut out and being illuminated in a particular way, or it may be some lighting artist who has focused his lights in a specific way on a plane that is creating this illusion of the structure. And what I really want to drive home is given a single image, there are infinite possible explanations of what 3D structure could have caused that image. And so in that sense, it's really an ill-posed task. When I say that here is this one 2D image and infer the underlying 3D structure, there are infinite possible solutions when we speak from a mathematical perspective. So that's the bad news. But the good news is that our world is not random. We sort of live in a structured world. So, given an image on the right, because we are familiar with the structure of our world, we have very strong reasons to believe that there is a flat road. There's a building on the left, which is mostly flat with some windows. There is a car, and we roughly know the shapes of the car and so on. And so given our knowledge about the structure of the world, while it is true that mathematically there are infinite possible explanations, what we must understand is that our knowledge about the structure of the world makes some of these explanations more likely in context of our world than others. And so the task of being able to infer 3D from a single image, in some sense, is trying to seek the more likely solutions given our knowledge about the world. So whenever we talk about this question of how we can infer the 3D structure, what we really are asking is how can we build an approach that leverages the world's regularities to infer the 3D structure given a single image? And so very broadly speaking, I'd categorize these approaches that try to leverage the world's regularities in two buckets. One, where we try to leverage them explicitly, which I'm calling single view modeling, where the key overall approach is that we assume some sort of a world model or a prior, and then we try to fit that model to a given image. And I'll briefly show what this is. And the other one, which we'll actually focus on a bit more, is where we try to implicitly learn about the world's regularities using some sort of training data, where by seeing a lot of training data, we hope that our prediction model implicitly can learn about these regularities, and then given a new image, can use these sort of regularities to predict likely solutions. And here I'm really drawing this maybe sharp line between approaches, but the reality is much more fuzzy. But just for the purpose of understanding, let's just draw this distinction. And maybe just to illustrate the first way of doing this, which I'd actually argue goes back many decades. So this is the very first PhD thesis written in computer vision by Larry Roberts called Machine Perception of 3D Solids, where he was also trying to study the exact problem that we are talking about right now, which is given an image such as the one on the left, we want to infer the 3D structure of the underlying world. We want to infer the 3D scene that generated this particular image. So really, we are talking about a problem that's maybe around 6 decades old at this point. And so given this particular image, what Roberts' approach did was first compute an edge image in some form, because in those days, it was extremely costly to store raw images because you only had limited representation power, and it really helped you to draw all these edges, and that was a much more memory efficient representation that a computer could fit. And given this kind of an edge representation, or a differentiated picture, it was called then, the approach was to assume some sort of a model of the world. So the model of the world was that there are these limited shapes that exist, such as some sort of a cuboid, some sort of a prism, and maybe another kind of a cylindrical prism on the right. And any image is generated by some transformation of these models. And so the goal is to identify a transformation of these models that gives you back the image that you're seeing, or the edges that you're seeing in this picture. And I'll spare you a lot of the details in terms of how the search worked for the transformation, but essentially following this ideology, Roberts could compute a 3D representation of the scene, understanding that there's this pyramid and this cuboid in this particular configuration that is generating this particular image that you see on the left. And so the model of the world was that there are these limited shapes that generate the edges in the image that you're seeing, and we really want to fit transformations that best explain the evidence that we are seeing here. And over the decades that followed, we actually did generalize this approach a lot. So instead of assuming fixed models, we started assuming deformable 3D models. Instead of assuming edge features, we started assuming slightly more complex hog-like features. But the key idea remained the same, that we have some sort of an image, and we assume that that image, or some representation of that image, is generated by a transformation of a known model. And then we try to find the best transformation that explains the image evidence. And there have been many different approaches with variants on this essential central idea. And here's maybe just a few representative examples where you can identify the 3D structure of the various beds that are shown, or some of the couches, or the tables, the chairs, etc., by identifying the different planes, or identifying a transformation of some base model which has all these planes, to figure out what the structure of the objects in this image is. And unfortunately, this model-based detection does have some limitations. So on the left, you're seeing this typical bed, which this approach can detect fairly well. But this particular object shown in the middle is also a bed. And so is this more messier bunk bed. And so it's extremely difficult to come up with models that explain all these different shapes under one single model called bed, or transformations of a single model bed that explain all these. And similarly for chairs. All these chairs are very different, and it's very difficult to construct a single chair model that can slightly transform and explain all of these different images that you're seeing here. And maybe sparing you some more detail here, but a similar issue can be seen when we try to do model-based scene layout estimation. So again, we can assume that scenes are generated by imaging something like a box-like room where there's a wall in the front, a couple of walls on the left, a ceiling at the top, and a floor at the bottom. And then we can really try to fit this model to image evidence, such as lines and vanishing points, and again, sort of sparing you a lot of the details. But this box-like room model can be fitted to new images such as this, and we can recover pretty precise estimates of the layout of the scenes shown here. But again, the limitation is that this particular model, this particular box-like model for rooms, doesn't really work across all rooms. So for example, on the right, we are seeing an image of a rather circular room, and on the left, we are seeing an image of a room which sort of has a hole because it continues into another room. And so this box-like model will not really fit well to either of these two things. And yeah, so that was a very brief overview of how we can leverage the world's regularities explicitly where the overall approach is that we as the user design a fixed world model, that there are these particular objects, or that the rooms are generated in this particular way. And given a new image, we try to fit parameters of that model to best explain what we're seeing in that image. And I think maybe this is a good time to take a slight break and see if there are any questions from the audience. I unfortunately can't really see questions directly, but yeah.
That's okay. Thank you so much, Shubhan, for the wonderful tutorial so far. I see one question on YouTube, which I will relay to you. This is from Aditya, and he asks, so I'm paraphrasing this slightly. When you are looking at an image of, say, a chair, and there are issues such as occlusion, can a fixed volume be assumed? And when certain features like chair legs are seen, a certain volume is delegated. In other words, if you see and detect something you know to be a chair leg, can you assume it has a certain volume and perhaps other layout constraints like symmetry? Aditya says, in this way, occlusion can be taken care of along with impending symmetry. So he would like to know your thoughts on imposing this sort of model prior.
Yeah, no, that's, I think, a great point, and actually goes to point out some of even the unsolved problems so far, that we don't have very principled ways of modeling occlusion yet. And so I think the techniques that Aditya mentions, that if we can identify something as a chair leg and we have knowledge of symmetry, we can assume that something symmetric might exist in other parts of the chair, is certainly a plausible one. And, I can maybe also point out some methods which are operationalize this. Some of the challenges that come out, though, is if you're just seeing the top of the chair, you're still aware that there are legs because you are aware of the structure of chairs in general. And even though you have not seen direct evidence of one of the legs, even one of the legs, you still know that there are going to be some form of legs. And maybe depending on how the chair looks from the top, you can even guess whether they'll be, legs with wheels or straight legs and so on. So while using things like symmetries can allow you to maximize how much you get out from the visible aspects, that doesn't always tell you everything. And I'm not sure, maybe there was some other part of the question as well, which I didn't address well.
No, I think that was the question, and thanks for addressing it. If Aditya has any follow-ups to that, Aditya, please do type that on YouTube or on WebEx, whichever you are online on. I don't see any other questions from the attendees yet, but please do keep your questions coming, basic or advanced. That was a great question. Keep asking, and Shubham, maybe you can continue, and if there are more, we'll take them at the next break.
Okay, sure, yeah. Thanks for helping with the questions. And yeah, again, if you are in the audience and have questions, please do feel free to type them or send them. I think we'll maybe get back to questions again in a bit, maybe in 30 minutes or so. So please do let me know if you have any questions by then, and hopefully we'll also get to more questions at the end of the talk. So yeah, going back to where we were, we briefly looked at what I'm calling here single view modeling approaches, where we as a user design some sort of a prior about the world, or assume some sort of a fixed model about the world, and given an image could just fit that model. But the issue really was that whatever model we hand design is often very limited and cannot really capture a lot of the variation that exists in the world. For example, diverse shapes of chairs, diverse shapes of beds, or diverse layouts of rooms. And so there's been a lot more work, especially recently, in this other way of leveraging the world's regularities, which I'm calling sort of implicit leveraging of world's regularities, where the overall approach is that we use some form of training data to learn a predictor. And we hope that this predictor has abstracted out the knowledge about the world using such training data and then can work on a new image. And this particular idea of implicitly learning about the structure of the world is not specific to single view 3D prediction. In fact, we have all seen the success of deep learning over the last few decades, which really is an homage to this particular idea that models that are learned with lots of training data can really learn about the structure of the world and can infer it on new images. For example, we may all be familiar with this particular success of deep learning in image classification. This is probably an image from AlexNet, where given a new image such as a mite or a container ship, a train model can very accurately identify it. And for example, we can also apply similar ideas for other problems like object detection, where given an image on the left, we can again easily identify all of the objects that are present here. And the success is not limited to just applications in computer vision, but also has the same ideas have been applied to other use cases such as machine translation. So for example, if you go to Google Translate and ask it to translate anything, it's probably using a deep learning model to convert, let's say, English to French. And all of these successes have really um, led to significant improvements in state of the art, but have relied on large scale annotated data. So across all these examples, we've seen millions of annotated images in ImageNet or many annotated examples in MS COCO. And that is why we've been able to sort of perform so well. And what I'm calling this approach is that of learning from direct supervision. So just as sort of a caricature of the approach, what we have is an input image, and we learn some prediction model. And when we are dealing with images, it's typically some sort of a convolution neural network that predicts the label that we desire. For example, in the classification case, this label would have been that here's an image of a ship, and the label is a container ship. And the way we learn this prediction system or this prediction CNN is by supervising it directly with the true label. So corresponding to the predicted label, we also know the true label, and we use some sort of a loss function. And we say that, let's say, the likelihood of the true label should be pretty high. And this allows us to backpropagate and train our convolutional neural network to predict the desired label. And as I was saying earlier, in case of classification or detection, this has really been enabled by using large-scale datasets such as ImageNet or MS COCO, where we have about 1 million labeled examples or million isolated objects, which allow us to learn from direct supervision. That is, given an image, we can predict segmentation masks or labels of images and can supervise them using annotations in these datasets. And so one popular approach in 3D is to directly apply similar ideas to the task of 3D prediction, where now instead of requiring prediction of some labels, we learn convolutional neural networks that can predict some form of 3D representation and can then supervise this 3D representation against some known ground truth. So just again, a very caricature recipe for learning under this paradigm of learning from direct supervision is as follows, right? That one, we decide on what it is that we are trying to learn, what's the objective that we'll use for learning, and then go and collect lots and lots of training data for this task. So for example, in ImageNet, we require 1 million examples. We can similarly collect maybe several thousand image and underlying 3D representation pairs. And then we can just learn a predictor using of this representation, where we just say that given this particular image, you should predict this particular 3D representation. And that's it. Well, actually, these days we need to wait for a few days, tune our hyperparameters, watch training curves, and so on. And at the end of all this, you'll have a predictor or this convolutional neural network, which you can then use to predict 3D structure of a new image. And this exact recipe for learning has been used for learning 3D prediction in many different cases. And just as the initial illustrations of this, there was this NYU dataset collected by Silverman et al., where there are these very popular Kinect sensors, which can give you RGBD images of scenes very easily. And so you can go, in this particular case, go into many houses of grad students living in NYU and scan their particular rooms or their workstations and collect pairs of RGB images corresponding with, with their corresponding depth. Again, in the images here, blue represents something closer to the camera, red represents something further from the camera. So using things like Kinect, we can collect this sort of a data set where we have pairs of RGB images along with a per pixel depth representation. And then here's just one particular model from Eigen and Fergus, which was using this particular data set to predict depth images, where I think maybe the final depth prediction is somehow cut out. But given an input image, we can train a system to predict a depth representation and then just simply say that a predicted depth should match the ground truth depth. And in their particular case, they were using some scale invariant objective because it's slightly easier to tell that something is twice as far as something else, but maybe telling precisely how far something is a bit difficult, and that's maybe just some detail that the loss function was taking care of. But sort of at the end of the day, given an input image, they were able to train a prediction function that could predict depth using these pairs of images and depth images as supervisory signal. And at the end of the day, their predictor could yield predictions like this, where on the left, we are seeing the original input images. In the middle, we see some of the predictions, and on the right are the ground truth. And the predictions are actually quite reasonable at a coarse level. They can very easily identify what is closer, what is further. But there are some details missing. For example, if you look at the boundaries of the chairs, they're not very precise. And actually, this to some extent has been addressed by subsequent work. For example, this is one of the more recent works from 2020, where you see that the predictions are actually much more accurate and much more crisp. And it's been achieved through a combination of using more data in terms of training, slightly better models, and better objectives that are more tuned to the boundaries in the image. But given sort of an image such as the one at the top, we do have systems that can pretty accurately predict depth of each of the visible pixels. And we can do this using essentially this approach that I described earlier, where we collect lots of depth data by using some sort of RGPD sensors, and then train some prediction models that can infer these 3D representations given a single image. And this exact approach has also been used to predict other representations beyond depth representation, because as we said earlier, while depth representations are easy to predict, there are some fundamental limitations that they don't model the hidden aspects of the scene. And sorry, just to show that this particular pipeline was instantiated for depth representation, where we decided that we'll train a multi-scale convolution model and collect data set in the specific manner to be able to learn depth prediction. But really, the exact same overall idea can be used for learning a different representation. For example, in this case, a volumetric 3D representation, where now we use a different source of 3D data, which in this particular case is the ShapeNet dataset by Chang et al., which is a really large-scale 3D object repository with textured 3D meshes. So here I'm just visualizing several of the shapes that are present in this data set, but really for each of these mesh, there's also some texture that gets overlaid on each of the chair or the planes or the cars, for example. And so what this can allow you to do is render each of these objects from arbitrary viewpoints, such as with the corresponding texture. And so we have these images, and because this is a synthetic data set where we know the true 3D models, we also have the paired 3D model. And so we can just create a data set from the synthetic data ShapeNet by rendering objects from many different poses, obtaining images. And because we know the true 3D model, we also have the paired 3D supervision. And given that, we can essentially learn to predict 3D structures. So here is just an illustrative approach by Girdhar et al. From ICVGIP 2016, where given an image on the left, which is actually a rendering of a synthetic model that is pasted on some random background, they train a convolutional neural network that predicts some 3D volumetric representation. In this case, for each cell, they predict whether that cell is occupied or not. So it's sort of a probability for binary occupancy. And given this predicted representation, they just say that this predicted 3D structure should match the ground truth 3D as accurately as possible, where we know the ground truth 3D because this is a synthetic data set, and the image on the left was actually obtained by a rendering of the true 3D model that is shown on the right. And in this particular case, the training objective is something like maximizing the 3D intersection over union, where a 2D illustration of intersection over union is shown here, where given two shapes, such as the circles here, or maybe the chairs at the top, we just see what regions they have in common, and again, how much region they occupy in total. And if we try to maximize this, we'll just ensure that both of them are essentially the same. And so by maximizing this, something like the 3D intersection over union, we just encourage our predicted 3D shapes to be as close as possible to the true 3D shape. Just doing this using lots of synthetic data from ShapeNet, as we saw earlier, can allow us to learn prediction system that works reasonably well even on some real images. So on the left in each pair, we are seeing some new image that the model has never seen before. And on the right, we see the corresponding 3D prediction where the dark red voxels are predicted to be occupied with high likelihood, and the slightly greenish ones are predicted to be occupied, but with a slightly low likelihood. And you can see that the core structures are actually reasonably well preserved, but the details are missing. For example, across all the chairs, you don't really see very precise thin legs, or if the seat of the chair has some of these strips, we don't really see that structure here. And that is to some extent because volumetric representations have some difficulty in representing the very fine details. And so some follow-up works have similarly looked at predicting different representations using a very similar approach. So given an input image, we again predict some representation, in this case a point cloud, and supervise it against the ground truth, in this case using a different objective, which is called the chamfer distance. So again, just maybe give a high-level idea. If we have two sets of point clouds, say S1 and S2, maybe the blue one and the red one, all we say is that for each point in, let's say, the red point cloud, the closest point in the blue point cloud should be close by. So you can think of having two different point clouds and trying to match them as well as possible to each other at a very high level. And so again, given an input image, we can predict a point cloud and then just say that the predicted point cloud should be as close as possible to a sampled ground truth point cloud. And this can let us learn predictions such as the ones shown at the top, where we are seeing the input image on the left and two views of the predicted 3D shape on the right. And sort of a very similar idea also applies to not just point clouds, but also meshes, where, I'm again, not going to go into a lot of detail here, but at the end of the day, we can obtain systems that, given an image, can predict some sort of a mesh-like representation of the corresponding object that was shown here, where in this case, also the training objective was similar to the chamfer distance that I talked of earlier, but with just an additional term that the mesh that we predict should not change too rapidly, or local regions in the mesh should be sort of smooth. And just a combination of these two could let us learn mesh prediction. And again, I'm sort of skipping over a lot of the details here. And while earlier we were looking at the case of predicting 3D structure for a single object at a time, we can apply similar ideas of learning the supervised 3D prediction to that of predicting scenes, where this particular work actually models the scene as sort of a hybrid representation. So as a depth image for the background and a volumetric representation for the foreground, and with corresponding losses for each of those aspects. So for the background depth, we have a loss similar to the depth loss that we saw earlier. And for the volumetric representations, we have an IOU loss similar to the loss that we saw earlier. And this can allow us to predict 3D structure of scenes, again, assuming we have supervision, where given the scene that we saw earlier, we can obtain this kind of a representation where there are different objects, and we can even manipulate the scene and so on. But I mean, just sort of looking back at this high-level picture again, what we saw was, given an input image, we can learn a convolutional neural network that can predict some form of 3D representation, as long as we have the corresponding ground truth 3D supervision, and we are able to define some sort of objective. And we saw this exact same idea being applied to different representations, such as point clouds, meshes, voxels, or sort of hybrid ones, such as in scenes. And I'd like to emphasize that this is, while the overall approach that I'm showing here is kind of pretty simple, that we predict some sort of 3D representation and supervise it against the ground truth 3D, there are actually many, many interesting research questions in this particular area. For example, what is the precise representation? What is the model architecture that can accurately predict such representations? What exact objectives should we use so that some of the details are preserved, for example, and so on. And while I didn't have time to cover some of these interesting directions, I'd just like to briefly mention that, in terms of representations, there are other aspects that one can tackle. For example, instead of explicit volumetric representations, some recent approaches pursue implicit volumetric representations, or instead of predicting the whole object together, we can try to predict a more compositional structure, that there are legs of the chair, or there are different handles that there are some sort of symmetries across these base structures. Or when we are talking about scenes, we can generalize depth representations to more layered representations that can capture not just the visible aspects, but also the invisible aspects. And so while across all these approaches that we saw earlier, or the ones whose teasers I'm showing here, the essential idea is the same, that given an input image, we have a convolutional network that can predict this representation by supervising against the ground truth 3D. There's still sort of a very rich research area with many questions that are yet to be tackled. But what I would really like to highlight in the talk is not going to detail in any of these particular questions, but just mention the fact that the ground truth 3D supervision is extremely hard to acquire. So across all these approaches that we saw earlier, we were assuming that as supervisory signal to learn a convolutional neural network, we can access some ground truth 3D supervision. But we could only do this in some synthetic settings. So a lot of the approaches that I showed earlier were using the synthetic ShapeNet dataset for training, because that is a setting where we can generate this ground truth 3D supervision. Or in some limited settings, we can scan some indoor scenes or objects and acquire ground truth 3D supervision in those settings. But speaking more generally, ground truth 3D is much harder to acquire. For example, here are just random images of wildlife or animals. And I really can't imagine someone creating large-scale scans of animals like tigers or parrots or eagles or peacocks, because these are extremely uncooperative entities that just won't stand around for you to be able to scan them. And so what we'll maybe focus on a bit later in for the rest of the talk is whether we can learn 3D prediction without using 3D supervision, or in some sense, whether we can learn 3D prediction using some form of indirect supervision. And while we have had a great amount of success in being able to learn from direct supervision, as I saw earlier, there are fundamental limitations in what settings you can obtain ground truth 3D in. So maybe this is, again, a slightly good time for me to pause and see if there is one question or two, and then maybe we'll move into the last part of the talk.
Awesome. So, Shubham, it turns out there are 5 questions. So, sure. People are clearly very engaged with your talk. Would you, by the way, your video is cutting in and out. Can you still hear us clearly?
I can hear you, though, yeah, it does give me some low bandwidth warnings.
Okay, I can see you again and hear you. I could hear you even when your video was off. So, if your sound really cuts out for a while, I will let you know. Okay, so let's start with the questions, and I will bump the balance of the questions to after the talk, whenever you think that you don't have enough time. Okay, so the first question is from Anantraj, and he asked for a clarification. In 3D from direct supervision, is the input image at training time a 2D or a 3D image? That's more or less the question as asked verbatim.
Yeah, so in all of these works that I was talking about, it is always an RGB image that, so you just have for each pixel, just the color values and no information about depth. But for all of these training images as well, the true 3D, the model itself never sees that information. So across maybe all of the papers that I'll talk about today, the input image is always an RGB image, but what varies is how much you know about that image at training time. In some cases, you know the true 3D model that you can use as supervision, and in what we'll see now, you don't really know that.
Maybe you can clarify the sort of extent of the 3D knowledge here. So is the ground truth 3D model, how often is it a full 3D model, such as a mesh or a point cloud or a volumetric representation? And how often is it an RGBD image? In other words, the ground truth just adds the D channel.
Yeah, so I think that's a great point. So I think in all of these cases, we were assuming that we know the true 3D representation that we are pursuing. So for instance, whenever I talked about RGBD, like depth prediction, there we assume that for this RGB image, we know the true depth. When we talked of mesh prediction or volumetric prediction, there we assume that for this particular RGB image, we know the true volumetric model or the true mesh. And so it's whatever output representation we are pursuing, whatever output our model is predicting, we were just assuming we directly know that as the training signal.
Thank you. Let's move on to the next question. There are some questions from people who've already had their questions answered by Shubham. So I will, bump your subsequent questions to later in the queue and ask a question to somebody new first. So this is from Prateek. He asks, given that the point clouds in your examples are not very detailed, where are point cloud-based methods used practically?
Yeah, so I think that's, again, a great point. So one maybe caveat or clarification there is the results that I showed for the point cloud was really maybe from the first point cloud prediction paper that I was aware of, and subsequent methods have added much more detail to it. That said, point clouds are very natural in some outdoor driving scenarios, for example, where let's say you do have some sort of depth sensors, where depth sensors automatically give you a partial point cloud, and then being able to complete that partial point cloud to a full point cloud is something that very naturally occurs. And more than that, I think point clouds are just, if we're talking of something that we want to infer from RGB images, are something that are more easily predictable than mesh-based representation and less memory efficient, more memory efficient volumetric ones. So it's sometimes you want to handle arbitrary structures, so you can't really predict meshes, but you have memory limits, so you can't really predict volumetric 3D.
Awesome. Thanks, Shubham. Okay, the next question is from Srikanth, and he asks, scale invariant loss function will probably recover relative depth. Any thoughts on recovering the scale?
Yeah, so I think that's a great point, and you're absolutely right that the scale invariant loss function, so it only predicts depth up to a scale. So you may be predicting the scene that's twice as big for every point, or everything is twice as far away, and the loss would be perfectly happy. There is kind of a trade-off. So some of the later works that predict depth don't use scale invariant losses. They do, or maybe they use a combination of sort of absolute terms and scale invariant terms. The reason that the initial paper that I talked about used a scale invariant term was that, the same image where the person in front of you is twice as high or the scene is twice as big will also generate the same RGB pixels. So those authors thought that being able to asking a model to predict precise scale is going to be tricky, and therefore they used a scale invariant loss. Subsequent models do use sort of losses that vary with scale, with the idea that you know how big chairs are. So if you see a chair, seeing how big it is will roughly tell you sort of how far it is. So you can use losses that are tuned to the scale, and people have used a combination of those. And if you do want precise scale, you should use those losses as well.
Okay. Thanks, Shubham. Let's go on to the next question, or would you prefer me to stop the queue here and let you go on and queue them for the end? Up to you.
Maybe let's take one more and then we'll move on.
Okay, great. So let's ask the last question I have here from a new commenter. So it's a good place to draw a line after this, I think. And everyone else who've asked other questions, I will make sure Shubham sees your questions, assuming there is time, but we'll bump that to later in the talk, if that's okay. Please do keep sending in your questions. All the questions I've read so far are great questions. So this is a question from Anuja, and she asks, will camera position be a problem here, as perception will change and 3D representations will change with the camera position? Or will a generalized model cater for camera position as well? So yeah, I read out the question as asked.
Thanks. Yeah, so that's a great question and will actually be even more relevant in sort of the following part of the talk. But just a high-level answer is, whenever we are learning these prediction systems, we are assuming some sort of a training distribution, right? That the depth images the images for which we are predicting depth are typically taken from how high a person is, looking maybe slightly down at 5 degrees, because that's how people typically take pictures. And if your data set had this sort of a view distribution, and you trained a learning-based model to predict 3D under this view distribution, most often you won't really generalize to varying distribution. So if I take a model that was trained for indoor depth prediction, and now I really made my camera just look down instead of kind of forward, we will not get very reasonable depth prediction, because statistically it's not the kind of thing that the model has seen earlier. And I'll actually maybe touch a bit more on cameras in the following part of the talk as well, and maybe we can pick this up again later.
Yeah. Yeah, thanks. I mean, do you want to say a little bit? So, because Anuja specifically says 3D representation will change with camera position. I mean, except in cases like depth images, my understanding is that the 3D representation itself rarely changes with the camera position. The camera position is just how you do the projection to 2D. So, Shubham, would you just like to add some thoughts on that?
Oh, yeah. So I think, thanks for catching on that. Yeah. So the 3D representation that we're trying to infer is more or less invariant to the camera position. So if we are seeing the chair from the front or the chair from the side, we're still trying to infer the full 3D of the same chair. So the 3D representation that we'll predict doesn't really change. And in some sense, we're trying to infer the structure that's invariant to the camera. And I'm again seeing low bandwidth, so I hope I didn't get cut off. But
no, your audio has been coming in uninterrupted throughout. It's just a video that keeps coming and going, but your slides are on there and your audio is fine. All right, thank you everyone for your questions. All the questions outstanding are noted, and assuming we have time, we'll get to them later in the talk. But for now, let's let Shubham continue.
Okay, thanks. Yeah, I think I'll try to leave at least 15 minutes again by the end of the talk for more questions. But yeah, sort of maybe coming back to the talk, what we saw so far was that if we have supervision for the true 3D structure, we can use a lot of supervised learning approaches to learn 3D prediction. But really, one of the big challenges that I want to talk of now is that it's extremely difficult to get such 3D supervision. And so we want to see if there are models or approaches that can allow us to learn 3D prediction without really using ground truth 3D supervision. And one possible solution to that is by what I'm calling using novel view images as supervision. And maybe just to illustrate this in action, we should consider this particular example where, let's say there's this 3D rabbit in the middle or there's this rabbit that you're walking around and seeing. So, and let's also stretch our imagination and think this is sort of the first rabbit that you ever saw in your lifetime. So you're seeing this rabbit from the front and you're imagining some sort of mental 3D model of it. And maybe you're not seeing the tail of this rabbit. And so the mental 3D model that you imagine thinks that there is no tail, that rabbits don't have a tail, for example. But then you move around and you see the same object from different perspectives. And in particular, you see this object from the side and you see that this rabbit does indeed have a tail, and that the initial mental model that you had formed when you saw this rabbit from the front was kind of wrong in certain ways. So as you walk around, you see the same object from different perspectives, and the perspectives that you see later provide some error correction signal to the mental models that you had imagined when you had seen this particular object from limited perspectives. And so just by walking around and experiencing the world or this particular rabbit from different perspectives, you can get some sort of 3D information about the structure of what you're seeing. And this is one thing we can operationalize to learn without requiring 3D supervision. And just sort of an example of this, in a maybe toy setting, given this an input image, such as the one on the left of this chair, again, we want to be able to learn some prediction system, some CNN that predicts a 3D representation of what we are seeing. Here, I'm maybe illustrating a volumetric 3D representation of the underlying chair. And as supervision, we don't want to use the true 3D of this structure, true 3D model of this chair. Instead, what we can use is the fact that this chair looks like this from the front. So we are saying that we have this observation of the same chair, this observation, oh, that this chair looks like this from a known camera C that, in context of the first image, I moved a bit. So the first image is from the side, the second image is from this relative viewpoint, and the view of the new view of the chair is like this. And then all we can say is that the predicted 3D that I had from the first image should just be consistent with this other observation of the same instance that I get by moving around or from this novel viewpoint. So again, just to highlight what's happening in this picture, given one image, we are able to infer some sort of 3D representation at the top. And to supervise this 3D representation, we don't use the ground truth 3D. All we say is that this 3D representation should be consistent with some other viewpoint of the same object. And that can allow us to learn 3D prediction without requiring 3D supervision. And here in this particular picture, this observation O was in the form of a color image, but actually we can use other kinds of images as well, such as a foreground mask image, which we can obtain by, let's say, segmenting out objects, or maybe a depth image. So in this case, we're assuming slightly more information from other viewpoint, like a depth sensor. But even this can allow us to recover the full 3D structure, including the invisible aspects, by being used as some sort of supervisory signal. And all we need to do is to define this sort of a geometric consistency loss that measures whether a 3D representation that we predicted is consistent with some 2D observation that we have from some specific viewpoint. And actually, I think I might want to skip a lot of the details on how we define this particular loss. Maybe I'll just give a couple of high-level points. And one being that when we are trying to figure out how consistent this 3D representation is with some 2D image, such as this depth image or an RGB image shown, we can decompose this into per ray terms. So instead of asking how consistent this image is with the 3D shape, we can ask for each pixel how consistent is what we know for that pixel with respect to this 3D shape. So, each pixel essentially corresponds to a ray that is emanating from the camera and then passing through this 3D shape. And we can try to ask how consistent is the 3D shape with respect to what we know for this particular pixel or this particular ray. And so all we need to really define is a per ray consistency term. And sort of as an additional aside, it needs to be differentiable so that we can plug this in some sort of a learning framework. And so to be more concrete, we need to define this consistency loss between a 3D shape representation that I'm calling X and this particular ray that is passing through this volumetric grid, for which we know something, such as maybe we know that this ray hit a blue, sort of a brown pixel, so we know the color of this ray. Or in this particular case, maybe we know the depth of this ray, that this ray terminates at this specific depth. Or if we have a foreground background image, then we know that this ray hit the object versus it didn't hit the object, and so on. And we just need to be able to define a particular ray consistency loss. And I'd like to say that this is a problem that has been studied in a lot of multi-view reconstruction works as well, where they use very similar techniques that, for instance, including the statue reconstruction work that I talked about earlier, where you have these many observations of a particular scene, and using similar ray consistency terms, you're trying to figure out what is this one 3D structure that can explain all these views. This question of ray consistency between a volumetric representation and a per pixel sort of an array has been looked at in these works. And I'll again actually maybe skip all of the details and just note that there are ways to make this differentiable so that you can plug these losses in a learning framework. And sorry, I'm skipping all of the details here, but I'll be happy to explain some of these later if you have any questions. But at a very high level, all I just want to say is, given an input image, we can predict some 3D representation. And if we have a differentiable way of defining the consistency of this 3D representation with some image, we can use this novel viewpoint of the same object as a supervisory signal to learn some sort of 3D prediction. And we sort of did this in a synthetic setting to begin with, just to ablate how well we do compared to ground truth 3D supervision. So again, using the ShapeNet dataset that we saw earlier, this is the input image. This is the ground truth 3D shape, which we again have access to because this is a synthetic setting where we know that this is the precise chair being rendered. But again, we won't really have access to ground truth 3D in realistic settings. But for these input images, using only foreground mask supervision from a couple of novel views for each object, we can infer reasonable 3D, except maybe the concavities at the chairs are missing, which is sort of a fundamental limitation of using mask supervision. But if we do use depth supervision, then the prediction improves a lot. And in particular, the concavities in the chair also emerge. And actually, the prediction using depth from a couple of views is very close to using ground truth 3D as supervisory signal. And this just tells us that if we have multiple views of an object from even a small number of views, such as 2 or 3 views, as in this case, that provides enough learning signal to be able to learn accurate 3D prediction. And one sort of limitation of what I talked about so far was that it was assuming that we know this particular camera. And while this is okay for an agent that is moving around and it knows how much it moved, it's not very easily accessible if you want to use data from the web. And again, maybe I'll skip a lot of the details here, but you can also learn to predict not just the shape, but also the camera prediction by just saying that the shape that I predict from the first image should be consistent with the second image when viewed from the camera that is predicted from the second image. So being able to have this differentiable consistency between the 3D shape and the 2D image can not just allow us to learn shape prediction, it can also allow us to learn camera prediction. And really what this enables us to do is go on web and scrape data such as from eBay, where people who are willing to sell their chairs typically naturally upload multiple images of the chair that they want to sell. And that gives us very natural multi-view supervision. And we can use some off-the-shelf systems to obtain some sort of coarse 2D segmentation and just use this for learning and get reasonably accurate, at least at a course level, 3D reconstructions without using any ground truth 3D supervision. So the only training data is of the form shown above, where we have many images of sort of about a few hundred objects, and for each we have 3 to 4 viewpoints. And just using that allows us to learn 3D prediction, where the images shown below are sort of novel images of new objects that our model had not seen during training. And sort of the key idea here was that given one input image, we can predict a 3D representation, and then we can essentially check this representation using a new viewpoint of the same instance, and just say that whatever 3D we predicted, let's say we saw an image of a chair from front from which we predicted 3D, should agree with a side view of the same chair. And this allows us to learn 3D, where so the key technique that enabled us to do this was some notion of differentiable rendering that allowed us to check the consistency between this predicted 3D representation and the other viewpoint of the same object that we had. And while I went into maybe slight detail of a particular work that used this approach for predicting a volumetric representation, the exact same idea can be used to predict other representations. For example, this particular ECCV 2018 paper used this approach to predict a point cloud-based representation where it gets slightly more details compared to a volumetric one, but essentially it's the exact same objective, exact same learning approach with the differentiable consistency now adapted to use point cloud representation instead of a volumetric one. And we actually get much more detailed reconstruction. So at the top is the input image, and then we see the ground truth. And the MVC approach is the volumetric approach that I described earlier, where I showed the results from eBay. And the last row describes the results of this particular paper, where point clouds let you get slightly more detailed reconstructions, but essentially using the same approach, where given two views, given two images, we predict 3D from one and verify it against the other. And of course, it's not just limited to point cloud-based representations. Using some form of differentiable rendering, we can also adapt it to meshes, where a differentiable render essentially looks at the standard rendering process. So when we are rendering a particular mesh, what we do is for each pixel, figure out what triangle is being visible at that particular pixel, and then essentially paste the color of that triangle onto that pixel. And there are some techniques that this great paper in CVPR 2019 had to make it differentiable, where essentially for each particular pixel, instead of using just one triangle, we use a combination of many triangles. And I'll sort of spare you a lot of the details, but it's possible to have a soft version of this mesh rendering and essentially have a differentiable mesh renderer, which we can again plug in to learn a mesh prediction now instead of a point cloud or a volumetric representation prediction, using exactly the same approach, where given one input image, we predict a mesh representation and say that this mesh, when rendered from novel viewpoints, should match the supervision that we have from those viewpoints. And as meshes are pretty amenable to being textured, this particular paper also showed results where it could predict textured meshes as opposed to just the shape. And those are the things that you see on the right. But sort of, again, maybe going back to the bigger picture, what we saw was given one image, having other viewpoints of the same object can allow us to learn 3D prediction. And I'd actually argue that this is pretty close or similar to how natural agents such as humans or robotic agents that we'll eventually hope to build can learn about the world. They'll learn about the world by moving around, interacting with it, moving around the object, seeing things around them from different perspectives, and being able to infer 3D structure by getting these images of the same object or scene from multiple viewpoints. But while I think it's a great way of learning from an ecological perspective, from the perspective of building agents that can learn about 3D, there are still limitations of this approach when we try to apply it to using internet scale data. And maybe just as an illustration of this, the approach that I talked about requiring multi-view supervision requires this form of data, where for this particular car, we require multiple viewpoints. For example, 4 viewpoints, where we'll predict 3D structure using one of them and verify against the other viewpoints. But if I go to Google and search for cars, the results that I get are of the following form, where I don't really have many viewpoints per instance. We only have a single viewpoint per instance, but thousands or hundreds of thousands of images of the category car can be easily collected, but we won't really get paired images that these 2 images belong to the same instance. And so from the point of view of being able to scale these approaches to work with internet data, what we'd ideally like to be able to work with are these single view image collections. So even at training, we don't want to assume multiple views, but just that we have many different objects, but only a single viewpoint per object. And in addition, we maybe want to assume, to make sort of this learning feasible, we can also assume certain limited amount of 2D supervision. So for example, in particular in the works that I'll briefly talk about, we assume that for each of these input images in the training set, we also have some annotated 2D key points that maybe tell us that here is the tail of the bird, here's the eye of the bird, and so on. And also the 2D sort of a coarse 2D foreground mask of the object that's shown here. But again, we don't have multiple viewpoints. We don't have that this particular bird looks like this from the front or this from the top. We only have this particular one image for this particular bird. And using these kind of image collections, we want to be able to learn 3D prediction. And so one of the first approaches we might think of is try to adapt the idea about learning. Instead of using consistency with a novel viewpoint, we can just try to enforce consistency with the same viewpoint. That is, given an input image, we'll predict some 3D structure and just enforce that this 3D structure that we predict should be consistent with the input image itself, as opposed to a novel viewpoint. And while this is a good start, this is not sufficient on its own. And just to illustrate this, here's maybe an example from Sinha and Adelson, which again, maybe just gives us an example of the infinite possible solutions to a particular 3D structure. So on the XY plane, we are seeing, let's say, the projection of some particular 3D structure. And one possible explanation is that this 3D structure is something like a cuboid, but there are many more possible solutions that will give us the same projection. And in particular, if all we are enforcing is the self-consistency, then all of these many infinite possible solutions are equally reasonable. And therefore, while this idea of using self-consistency or making the predicted 3D consistent with the input image is sort of a good starting point, it's not sufficient on its own. And there are different ways of dealing with the insufficiency of this, or different ways of preventing degenerate solutions. And one of the popular ways is to enforce a category level parsimony. And just an illustration of this in maybe the setting of cars is, if we consider the category of cars and consider many different images that we are seeing from many different viewpoints, because we know that all of them belong to the category of cars, the shapes across them don't vary arbitrarily. The 3D shape across all of these different images is sort of consistent with each other and does not vary significantly across them. And so what we can enforce is that across all these images, roughly the same model with limited deformation should be able to explain these many different images. So you can think of this as treating other images of different objects as essentially novel viewpoints of the same object with only slight deformation allowed between them. And again, I'll maybe skip some of the details, but just this idea where we try to look at the entire collection of images and learn a common 3D model that with small deformations can explain them, can allow us to infer reasonable 3D across many different categories, such as airplanes, bikes, etc. And in sort of a follow-up work to this, we also showed that we can not only sort of fit this model, we can also predict this using a convolutional neural network, which is maybe a bit more along the lines of what we've been seeing in the talk so far, where again, the overall approach is essentially the same, that given an input image, such as the one on the left, we have a convolutional neural network that predicts a 3D mesh, or to be more concrete, a morphable 3D representation, which is defined as this mean shape of a bird plus some limited shape deformation, where we constrain this shape deformation to prevent degenerate solutions with the exact objectives that we saw earlier, that this particular 3D mesh, when reprojected to the original image, agrees with the foreground mask that we have annotated. So this is sort of self-consistency with the input image. And we can enforce this consistency not just with the foreground mask, but also we can predict the texture that gets overlaid on the mesh, and also enforce consistency with the RGB values that we're observing in this particular image. But sort of just the combination of these two terms, where we're enforcing reprojection consistency with the input image and limiting the amount of deformation that's allowed across different instances, can allow us to learn 3D prediction. And then at test time, given new images of a new bird that we haven't seen in the training images, we can predict this 3D representation and also some sort of texture that gets overlaid on this particular mesh, and kind of render it from novel viewpoints just to convince ourselves that the 3D that we predict is quite reasonable. And it also works across other birds and can even capture some variations, such as the wings of the birds are stretched when it's flying, or the tail of this particular bird is much longer than the tail of the bird at the top. And we are able to capture such variations within the category, despite limiting the amount of deformation. And here are maybe just some more results showing 360-degree visualizations of our predictions on images from test set, where again, we are seeing these images, and just given this one image on the left, our model is able to predict the shape as well as the texture that gets overlaid on this particular shape. Sorry. And okay, maybe we'll just see one more bird rotate and then maybe move on. Okay, so the overall approach here was, as I said, a combination of two terms. One, that the predicted 3D representation should be consistent with the input image that we have, and that across the category of birds or across the category of cars, we limit the amount of variation or the amount of deformation that is allowed between the predicted 3D shapes. And while that's sort of a great idea for certain categories, it does not really capture large variation. For example, if we look at these two particular chairs, the idea that we can enforce a limited amount of deformation between these two instances is not really a reasonable one. These two different objects, while they're both chairs, have a very differing shape, and more or less any notions of category level parsimony that we enforce will fail to capture this large variation. And that is why the results that we were seeing earlier were restricted to categories like birds and cars, where the variation across objects in a category is very limited. And so while this idea of using category level parsimony is reasonable, it only works for certain categories and cannot capture variations such as the ones we see in chairs or maybe even vacuum cleaners and so on. And so one alternate approach of preventing degenerate solutions that has been, I think, gaining popularity, especially over the last couple of years, is this idea of enforcing novel view realism. So what we say is, in addition to the predicted 3D being able to explain the original image, any rendering of the prediction should be realistic. So let's say I have an image of a chair from front, and I predict some 3D representation, and I say that it should agree with the original image. In addition to that, a rendering of the volume of the representation that I predict from any arbitrary viewpoint, such as side, back, etc., should also look like a chair. And this is something we can enforce using adversarial networks or generative adversarial networks proposed by Ian Goodfellow et al. And sort of one specific illustration of this work is from Hensler et al. In ICCV 2019, where given an input image, such as the one on the left, they predict a volumetric 3D representation, where for each voxel, They predict an occupancy as well as a texture, so you can decode out RGB images from this. And as always, they say that this particular 3D volume should explain back the original image. But sort of the more interesting objective is the discriminator-based one, where what they say is any rendering of this 3D representation, sort of rendering of this representation from any viewpoint, should look realistic. And there's this discriminator D, which is seeing many examples of real images, which it learns to classify as real. And it's adversarially seeing many of these generated examples, and it's trying to classify them as fake. And our predictor or the generator is trying to therefore generate 3D volumes whose renderings look as realistic as possible. And so this sort of two-player game prevents degenerate solutions because the 3D structure that we are predicting should not only agree with the original view, it should also look reasonable from a novel viewpoint. And this allows us to learn, without limiting the amount of variation that we have in a category. And just as an example from their paper, they showed these very nice results on being able to learn the 3D structure of some of these mushrooms, which are pretty complicated shapes to handle. And sort of the deformation across them is not very easily modeled as some simple deformation of meshes. And in fact, we actually have a follow-up on their work that is in submission, and I'll maybe not go into a lot of the details here, but just this idea does allow us to scale to many object categories and allows us to predict 3D representations of things that have pretty diverse shapes and topologies, such as even the donut on the right or the hat on the left. And different donuts are not really easily modeled as deformations of spheres, as we saw earlier. And it doesn't work for just these 5 categories because we can handle deformations across a lot of them. The same approach can handle many different kinds of categories like guitars, cups, etc. And of course, the reconstructions are coarse because we are learning using very limited supervision. We are not using any 3D supervision, but only just these image collections with very sparse 2D annotations. But this approach does allow us to learn 3D across, at least coarse 3D representation across many categories. But I think this is maybe a good time to take a step back and take a stock of what we have looked at so far. And especially pertaining to the learning-based approaches, we really just looked at essentially one single approach in the abstract, right? So we only looked at approaches which, given a single input image, are trying to learn a convolutional neural network to predict some sort of 3D representation. And what we saw today was that there are varying levels of supervision that can allow us to learn this sort of a prediction function. So in particular, one can either rely on using ground truth 3D as supervisory signal, where maybe using a Kinect scan or synthetic data, or maybe slightly painfully collected scan of indoor data can allow us to learn this way. But there are some limits to being able to collect large-scale ground truth 3D supervision. And so then we saw this idea that the exact same prediction system, which again goes from an input image to some sort of predicted 3D representation, can be learned by not using ground truth 3D, but by just enforcing consistency with novel viewpoints of the same instance. And this sort of allowed us to bypass the requirement of 3D supervision. And I'd argue it's a very plausible approach for real humans or robotic agents to be able to learn about the world. But sort of towards developing approaches that can more easily learn from internet scale data, we also saw that we could relax the constraint of novel view images requiring novel viewpoints by just enforcing self-consistency with the input image. But because there are infinite possible solutions, we do need some additional constraints to prevent non-degenerate ones or to prevent bad solutions. And we saw sort of a couple of variants where we say that the variation across a category is limited, or that novel view renderings might look realistic. And yeah, I think that was maybe looking back at what we covered. And maybe just to finish up, there are some thoughts on what I personally feel are interesting and exciting directions, so that if you are getting started in the field or are looking to work in some specific aspects of the area, maybe these thoughts will be useful. But one maybe rather obvious thing we need to accomplish is be able to make our 3D reconstruction approaches work reliably well across a very broad category of objects. So actually, when I started grad school, I think back in 2013, we could really get accurate 3D for maybe a couple of categories from single images. I think they were faces and cars. And now I think maybe after 8 years, we have scaled this to somewhere between 10 to 30 categories. But if we really look at the natural world, the number of object categories that exist out there are in tens of thousands. Some of them have more easily available data, some of them have less easily available data. And we really need approaches that can work reliably well across these many different object categories. And it's kind of interesting to see how one can develop approaches that maybe share knowledge across different categories to possibly accomplish this. And the other thing that we didn't really touch upon that much in the talk, because we focused really on predicting structure of single objects at a time, was how we can reliably predict the structure of a scene. So even just this very simple scene that I'm showing here has a lot of subtleties. It is not very satisfying to just predict a 3D representation of the plate and each of the cups in isolation. What's really interesting about the scene is that the red cup is on the plate and sort of the blue cup is subsequently on the red cup and so forth. And so it's really the relationships across the configuration of these objects that is interesting about when you're trying to understand the 3D structure of the scene. And as a research problem, it's not very obvious yet on how we can best represent and predict these kind of relationships from images when we are trying to reason about the 3D structure of scenes. And again, we were in the talk looking at these very concrete and well modelable shapes, but sometimes maybe if I'm looking at sort of the water in my bottle or maybe the snow on the road, it's not really a very simple solid shape. It's somewhere between a fluid, and it's again not very clear on how we can represent these more free-form shapes or what are ideal representations to be able to predict some very complex things such as the leaves in a tree or the grass, or how we can best represent the 3D structure or predict 3D structure of these things. And maybe as an analogous challenge in not shape representation, but in texture representation is maybe we also want to be able to obtain more detailed models, not just in terms of shape, but also in terms of texture. And while a lot of great graphics representations do exist in how we can represent the specularities or the precise material or how the light bounces off these particular balls, we haven't really had systems that can accurately or reliably predict these kind of properties given images. And maybe this will require some more advances in differentiable rendering as well to account for these kind of properties. But at least I personally think this is also an interesting area to explore. And maybe one last thing, which maybe I motivated a bit in the talk, but a lot of applications of 3D reconstruction can be found in computer graphics or manipulating internet images. But one of the more emerging areas is also robotic interaction, where for instance, for a robot to be able to pick up a new cup, it really needs to understand that the handle is at a particular place, or that this handle of a cup is similar to a different handle of a different cup. And being able to understand objects or entire scenes in 3D is critical for robotic agents to be able to manipulate objects well or scenes well. And as an analog of this, we humans learn about the 3D structure by actually interacting with the world as opposed to downloading passive data from the internet. And it's also an interesting research question about how robotic agents can sort of learn about the 3D structure of the world. And maybe using multi-view supervision is one starting point, but it's also something that's been largely unexplored of how real agents can learn about the 3D structure of the world. And yeah, I think these were more or less my random thoughts on some directions I think are interesting. But again, these are a very biased and limited sample. So I'm sure there are other exciting things I haven't mentioned. And I'm happy to take questions in general as well now.
Thanks so much, Shubham, for this fantastic tutorial. I mean, your thoughts may be random, but it's the random samples drawn from a very structured and thoughtful distribution. So thank you very much. Let's go ahead to the questions, and I'll start with some of the questions that we couldn't address in the last question Q&A break. So this is another question from Aditya, and he asks something that's sort of related to one of the future work directions that you mentioned, on which, of course, there's also been some prior work. When using human knowledge priors, what do you think of seeing pairs together? For example, even if a chair is weirdly shaped, if a table is nearby, it is very likely to be a chair, and so on. So this is a question about context, and maybe you can address that.
Yeah, so I didn't really get into this a lot in the doc because we were focusing a bit on isolated objects, as that's maybe a clean setting to analyze. But whenever we go to scenes, the reasoning about context, as you mentioned, becomes extremely important, right? And this thing is not really just limited to 3D structure. It's also something that pops up in object detection, where, as you said, if there's some very blurry object or something of which I see very small number of pixels near a table, it is very likely to be a chair. And at maybe a very high level, the way I think of 3D reconstruction from images is there's some sort of a stage where we are processing the images or inferring some sort of features. And that is the stage where I hope enough context is coming in. And then, when we are looking at the relevant regions of the image to be able to make these predictions, even if it's a blurry chair, one would hope that it has seen enough context so that we can then 3D that we infer from this possibly blurry region is then aware. So maybe just to summarize, A, yes, context is very important. And B, I do think standard image processing pipelines, which compute sort of some features at each location by looking at the area around, are able to handle context or able to sort of use context.
Great, thanks, Shubham. The next question is from Anantraj, and he asks, ill-posed problems are solved using the prediction problem. Is that a correct interpretation?
So I would like to say that prediction is just one particular way of addressing an ill-posed problem, where we say that, given the input image in this particular case, or if you're thinking of more general sort of an X to Y problem, a prediction just learns an F that predicts a Y directly from the input X, or given an image, we directly infer a Y. But prediction is not the only way, as we were seeing earlier in some of the modeling-based approaches, we had some prior about the world or some model about the world, and we were really fitting it to the image evidence. There was no explicit prediction, there was no learned network. And so I would say that ill-posed problems are really tackled by having some sort of priors. Those priors may be learned, they may be hand-designed. If the priors are learned, sometimes they are there implicitly within a prediction function. So prediction is not really necessary to solve an ill-posed problem. It helps you implicitly capture some priors that may help you solve a ill-posed problem.
Awesome. Thank you, Shubham. The next question is from Pratik. And if you remember, Pratik had asked a question earlier about the sparsity of point clouds and whether that made them unsuitable for applications. So he's saying, he's asking, could a mesh be recovered from point clouds? Can we, in some sense, generate mesh models from the point clouds?
Yeah, so that's actually a great point, and it's, I think, sort of an open research question, and maybe Siddharth can also correct me because he knows more about this. But my understanding is that in general, no, as in if you're given an arbitrary point cloud, being able to recover sort of the true mesh that underlies it is really, again, an ill-posed problem, and there's no a single mesh that uniquely explains a point cloud. Given that if you enforce some sort of regularizations that, a point cloud is really on the surface, the inside versus outside of a mesh doesn't vary very sharply, then you can recover some reasonable mesh from a point cloud. But so generally speaking, there are techniques that will let you recover reasonable meshes, but from like a precise answer, there's no unique mesh corresponding to a point cloud.
I mean, to add some thoughts to that, the problem of recovering a mesh from a sparse point cloud is in some ways of not quite similar difficulty, but of a similar nature to recovering a detailed mesh from an image. Both are lower dimensional representations of some complicated underlying 3D object. So if you try to solve the problem of recovering a detailed mesh from a sparse point cloud, you're just sort of shifting the task from reconstructing from an image to reconstructing from a sparse point cloud. You may have made it a little simpler by introducing the sparse point cloud as an intermediary, but there's still a lot of work to do to do that second half of the operation. And there's a huge literature on this. I won't take up Shubham's time. There are many other questions, but just as Shubham has talked about priors and model-based predictions and learning-based methods, there's all of this on recovering detailed meshes from sparse point clouds. The next question is from, let me just scroll through the list and find that was not addressed yet. Okay, so this is a question from actually one of my fellow chairs of the tutorials track, Arnav Bhavsar. He's a professor at IIT. And Arnav asks, in the case of learning-based multi-view reconstruction, where the camera is unknown, essentially a learning-based structure for motion task, will it have the same ambiguities as encountered in the traditional geometric approaches?
Yeah. So actually, maybe just a clarification on that first. Today, the multi-view approaches that I was talking about, they didn't really use multiple views at test time. So at test time, it was still a single image-based prediction. It was only at training that we were assuming that we have multiple images of the same object. And in those, I think I described different works and didn't really emphasize this too much, but in some cases, we did assume that the camera was known. In some, we were also learning to predict the camera, and where Arnav is exactly right that there are often ambiguities. For example, if we are looking to infer the camera of a chair, then there are some difficulties in reasoning about symmetries, and there are many different, like 3-4 different possible cameras that can correctly explain what we see for a single object. And we do run into some issues there, which I didn't really get into. But again, all of these, at test time, we still just have a single image. So in that sense, it's a bit different from the SFM-based approaches.
Thanks, Shubham. So Pratik is asking, do we use some pre-trained model which is trained with 3D ground truths for learning 3D via multi-view supervision without 3D ground truths? This is a question about, is the pre-trained model, can that be trained with 3D ground truth, even though your core learning problem doesn't assume 3D ground truth?
Yeah, so actually that's a great question, and it goes to some experiments that I didn't talk about in the talk. So it's definitely possible to do that. So being able to pre-train some models with 3D supervision, maybe on synthetic data, is a great way of initializing the encoders, decoders, making sure that you start off with a reasonable shape space to begin with. And then you can really adapt those models to work well with real images using multi-view or image collection data. And I think in our CVPR 17 paper, which was learning this volumetric representation, we do indeed have this experiment where you can pre-train a model using synthetic data and adapt it to the real data, and actually exceeds both models in performance, one that sees only synthetic or real data. So that's, I think, a great point to keep in mind, that while I was painting these demarcations that either we have ground truth 3D, or we have multi-view, or we have single view, those are good divisions to have from maybe a research point of view. But if you're building a system, then you really have all of these available in different amounts, and you can and probably should use all of them in any way you can.
Great. So we have 3 questions outstanding. We have 7 minutes left, so I think that's a good allocation of questions to time.
Okay.
And 2 of these questions are fairly broad-based, and 1 is fairly specific. So let me ask a specific one first, and then we can take the more broad questions. The specific one is again from Aditya, and he asks, I quote, have capsule networks been used to provide any advantages in 3D reconstruction, as they are said to provide shift equivariance instead of being shift invariant?
Yeah, so I think some instantiation of capsule networks that I'm aware of in context of 3D representation, I think maybe one of the papers I have in mind was from Nitish Srivastav. I'm sorry, I can't remember the title off the top of my head. was used to discover essentially parts amongst different objects. So if you have many different chairs or 3D shapes of different chairs, and you're trying to essentially co-analyze them, using some sort of capsule networks, you can realize that there are these chair leg-like structures across different chairs that are common across different chairs. And this is a part that occurs maybe in slightly different orientations across different chairs. So I've seen some of these applications in being able to discover some high-level structure across different categories. And arguably, this is also a representation that can be more easily inferred from an image, though I think that is still a bit open. So maybe just a high-level answer to your question, that I've seen some initial attempts to it, not so much from predicting these representations from images yet, more so from analyzing 3D shapes. But hopefully we'll also see more image-based applications.
Thanks, Shubham. Okay, questions are coming in. So there are two new questions just came in. Actually, maybe I should ask the program players. I see Parag is online. How much time do we have? I mean, can we stretch the session by 5 minutes? Parag, can we stretch the session by 5 minutes?
Sorry. Am I audible?
Yes, you are now.
Yeah. So we have a break from 11 to 11:15. So you can stretch by 5 to 10 minutes. It's okay.
Great. I would ask any further questions be maybe emailed directly to Shubham or me, and I can filter them and relay them to later. But no more questions on WebEx or YouTube, please. We don't have the time for this, and we do need to wrap up at about 11:05. Thank you very much for your questions. I really hate to cut off any more questions, but we are under a strict schedule.
Yeah, okay, to reiterate that, I'm happy to answer them over email.
Thanks so much. Well, actually, I sort of volunteered you without checking with you first, but thank you for saying that. And there's also a request if Shubham, can you hear me now? Hello? Yeah, I think Shubham can hear me. So I hope everybody else can. There is a request, Shubham, could you stop sharing your slides, and then we'll see you in full screen, which is a more pleasant way in these virtual times. Awesome. Yeah, there you are. Okay, great. So then I'll keep the broad questions still for the end. Here is a specific question from PJ Narayanan. He's the director of IIIT Hyderabad and senior vision researcher. PJ's question is, what are the implications of the NERF-style view synthesis work on 3D reconstruction?
Yeah, so I think that's sort of a great question. So if some of you are not familiar with NERF-like representation, maybe a one-line summary is there have been these amazing results from Google and Berkeley and collaborators, which show that we can learn these volumetric representations essentially, though in a slightly implicit way, where for each cell we store occupancy as well as colors that cell emanates when viewed from a particular direction. And these are called radiance fields, and they really let us represent scenes in remarkable details. And so the initial paper showed very precise reconstructions of a scene given many views. And now there have been some subsequent attempts which try to even predict these representations from small number of views. So I think maybe my reading of this is, I think NERF or radiance fields in general are a great new tool for representations, where the key idea is that at each 3D location represent not just occupancy, but also the radiance field. And this really lets you generate much more high fidelity images. So in all of the image-based, like the differentiable rendering work that I talked about, or self-consistency with the input image that I talked about, having radiance fields as the representation gives you a much more powerful representation that can more accurately represent the original view or the novel viewpoint. And I imagine will make learning some of these things more feasible, or if you're thinking of adversarial losses, using radiance fields might give them more power to produce realistic images. So I think it's, in a lot of the works that I talked about, it's worth investigating whether using radiance field instead of raw voxel occupancies can improve it in certain ways. And for some of those works, I do think the answer will be yes.
Thanks so much, Shubham. I see some panelists have their mics unmuted. Could you please mute your mics if you don't mind? There's a little bit of chatter coming through. Thank you so much. Okay, so there is one question which clarifies that it is not directly related to the topic, but this is from Carrie, and they ask, while writing papers, which softwares could be used for illustrating models like drawing network structures, illustrating parallel cross sections with 3D figure? In other words, for the illustrations in your slides, are there specific tools that you like using and which students listening to this talk could benefit from exploring?
Yeah, so I think across maybe all of the visualizations, what is common is I've tried to create a mesh for what I'm trying to render. So even the volumetric renderings that you were seeing were instantiated as some sort of a mesh. So typically there's Python code which tries to construct a mesh out of whatever it is that I want to visualize. And then based on some requirements, it's some sort of a very simple renderer, such as some differentiable renderers in PyTorch 3D, or more complex renderers, such as those in Blender or Mitsuba, depending on how high fidelity or what kind of effects I want. But the one thing that's still common is, as much as possible in code, try to construct a mesh out of what it is that you want to see, and then render it in a certain way.
Great. Thank you, Shubham. Okay, now the two broad questions that had been mentioned earlier. So the first one is from Sri Gauri, and she asks, how does the depth analysis of objects differ in a closed space like a room versus an object in an open space or area? So indoor versus outdoor.
Yeah, so I think there are some things that are common and some that are slightly, so of course the range of possible depths in an outdoor scene is much more varied. But if, again, you're thinking of a very structured outdoor scene, like there's a road and there are objects on the road, then the thing that's common with indoor is that you still have very strong priors about it. So you have very strong priors about the typical layout of a room and how the size of things varies with distance in a room. And similarly, you have strong priors for how size of things varies in an outdoor scene. And if instead of thinking about depth, you think of inverse depth, or what's called disparity, then more or less the prediction across these two scenarios becomes very similar, because something that's 3 meters away versus 20 meters away, inverse depth is not that different in terms of like sort of 1/3 or 1/20. What really differs in outdoor scenes is if you go away from structured scenes like roads to things like if you're skiing somewhere, or if you have the scene of a forest or a top-down view of some scene, then just the variation in views can be very huge. And in those kind of things, we don't have very easy priors. So if I give you, let's say, a top-down view of New York City, it's extremely hard to have priors about how far buildings are. And so if you're thinking of more generic outdoor scenes and trying to think of depth there, then cues like size familiarity, that if the building is this far away, it becomes this small, don't really work if you have very arbitrary viewpoints, such as satellite views of images. So maybe a concrete attempt at the answer is, if the scenes are very structured, like roads or rooms, then I would think not much changes because you have strong priors. But outdoor scenes can be much more unstructured, much more easily, and there things become harder.
Sweet. Thank you, Shubham. The last question, and this is a slightly provocative question, but I think it's a sort of interestingly provocative question. What are the industrial applications of single-view depth prediction? Because image sequences from live captures and camera intrinsics are available for many of the real-world interactions, like robotics. This is a question from Srikanth. So maybe you can take that as a sort of closing
Yeah, no, I think that's sort of a great question. And it is worth keeping in mind that in a lot of scenarios, you can easily move around, get some sort of a depth estimate or some partial 3D estimate, which really works well. That said, if you think of any internet image that you want to analyze, you don't really have a special camera. Like most of the images that exist out there on the internet are RGB images. If I want to take an image of someone's house and let's say reimagine how it looks with a different furniture, which is something that maybe a lot of artists or interior designers would want to do. Then being able to understand the 3D structure of the room, or being able to replace objects, understand how the room looks without the objects, is something that's very important. And so that's maybe possible applications of understanding, the 3D structure or depth of internet images. But even if we look at other applications, let's say in robotics, or even if you can capture a video, then maybe not so much depth, because depth you can recover from a small amount of motion, but still being able to understand the full 3D structure of the scene is very important, and is not something you can get by a small amount of motion. So if I'm standing at a particular place and I can move around a bit, I do get a sense of how far things are, but still being able to predict what is behind certain things that is not visible from my limited viewpoint is important for robots. Like if, and I mean, okay, that's not an application that is there immediately in the industry, but I do think as we hopefully get to deploy some of these interactive agents in homes, this will be important for them. But again, maybe just to summarize, at the moment, if you want to do anything interesting with, let's say, manipulating an internet image in terms of a graphics application, being able to understand the 3D of it from a single image is critical. And going forward, I do think sort of the full 3D understanding, at least at the course level, will be important for any robotic applications that you want to deploy.
All right. Thank you so much, Shubham, for taking all these questions for this fantastic tutorial. I'm sure we all learned a great deal from it. Thank you for staying up, late into the US night. And I'll hand back to Parag with thanks. We can only have virtual applause here, but assume that the virtual applause is filtering through your speakers. Parag, over to you.
Yeah, thanks a lot for
Thanks to
hosting and helping with all the questions.
Yeah, and thank you to the audience for your questions and for being part of this session, for tuning into this virtual session.
Great. Thank you, Shubham, for that very, very nice talk, and really for bringing graphics and vision really close together, merged into one subject. And I think it's very apt for a conference like ICVGIP to see how these fields are blending and merging together in such areas. As Siddharth keeps on saying, the lines are constantly blurry. And thank you, Siddharth, for chairing this very nicely, and for helping manage time and getting all the questions through. I'm sure our listeners and the audience enjoyed it a lot. So we will take a short break till 11:15, and we will follow up with the startup interface session, where we have a bunch of talks by Indian startups which are working in the area of computer vision, graphics, and image processing. I'll hand over to Uma, who is the session chair for that session. I think she might have stepped out for rehearsing for that session in another room. But we'll be back at 11:15 with the startup session. See you all then. Right? Bye bye.
Parag, can you hear me?
Oh, you are here. Okay, yeah, I can hear you. Oh, I can see you. Okay. So over to you.
Okay. Okay, thank you, Parag.
Ah, you are there. I had to scroll the list up to see.
Yeah.
Yeah. So go ahead, please set up your talks or speakers if they are already here. Then we'll start at 11:15.
Yeah, we'll start at 11:15. So all the speakers are there already. They have joined.
Okay.
So we'll start exactly at 11:15.
Yes, we can start exactly at 11:15.
Yeah. Yeah.
Okay, so we'll be back after a shorter break.
Yeah.
Than what is planned.
Okay, sure.
Bye-bye.
Yeah, for all the startup speakers, so we will start exactly at 11:15 as per the plan, and the timings will exactly shift by 15 minutes.
Okay, ma'am.
Not seeing. So,
आपने जिस व्यक्ति को कॉल किया है वह अन्य कॉल पर व्यस्त है कृपया प्रतीक्षा करें
not seeing. Hello. Yeah, you have not joined it.
Hi, good morning, Ms. Uma.
Yeah. Hi, good morning. Parag, shall we start?
Yeah, go ahead, please.
Yeah. Hi, good morning, all. Welcome to the session on startup interface session. Here we have four talks by startup and the one talk by angel investor. So the four startups are Aviros, Holokita, Snaptood, and Test AING, and the one angel investor by Indian Angel Network. So I thank all the speakers for accepting the invitation, as well as I thank all the attendees for attending this session. So we'll start with the first startup talk by Aviros, given by the Paurush Dubey. Paurush is a product manager with Aviros for more than 3 years. He's an electronics engineer by training and specializes in product and user interaction design, and also a communication specialist. He is passionate about making computer vision and in-specific video AI accessible to masses. He, along with his teammates, are working towards creating an ecosystem wherein video AI application can be easily developed, discovered, and consumed. So over to Paurush. Please start a video and share and start the talk. Paurush?
Sure. Thank you, ma'am, for the introduction. So I'll just be sharing my screen now. Please let me know when you're able to see it.
Yeah.
Yeah, I hope you're all able to see my screen now.
Yeah, we are able to see it.
Great. Okay.
Yeah. Start your video and then probably.
Okay, I hope I can start now.
Yeah.
Okay, so my name is Paurush.
Paurush, start video as well. So that
I'm not sure if I can start the video.
Yeah.
But let me give it a shot.
if you cannot, then it's okay. Otherwise,
Okay, I'll perhaps switch it on once I'm stop sharing the screen.
okay, fine, go ahead.
Okay. Okay, so I am a part of Aviros, and we have created the world's first video AI operating system and marketplace. So now to start off, I would like to talk about why exactly do we need AI for processing videos, right? So firstly, like it perhaps would be an understatement to say that video is the most pervasive form of data that is available in our world today. Like it forms close to 82% of the total data on the internet. And a very redundant form of this data is in the form of CCTV footages, which produce close to 800 petabytes of data every single day, right? Now, while this sheer abundance of data makes video almost impossible to analyze, manually, at the same time, it makes video, pretty much a virtual data goldmine, right? So, and video actually happens to be one of those few data forms which can be analyzed in multiple different ways to, for us to obtain multiple different types of insights or information out of the same data, right? So now lately, the typical scenario of a bunch of people sitting in a certain control room and analyzing a very large number of video features is being very actively replaced by this technology called video AI. And what exactly is video AI? It basically is, it is a mechanism for extracting meaningful information out of videos, right? Using a combination of computer vision and artificial intelligence, and then using it to trigger action wherever necessary, right? So how it basically works is we basically obtain the video data, process it, and then run video AI applications on top of this data, right? And then obtain actionable insights out of it, right? So actually, I'm having trouble playing this video here, but otherwise it basically shows this is a process monitoring application that we had earlier. So here then it's actually deployed inside a steel plant, and this person here is actually supposed to put in a bucket full of magnesium in a certain batch of steel, right? So this process has to be repeated over and over again. If he misses, if the magnesium is not put in into a certain batch, in that case, the entire batch, all of it would go to waste, right? So in order to avoid that, we had developed this application which constantly monitored that bucket of magnesium is constantly poured into every batch of steam, right? Okay, so moving on, this is another application that we had developed for the Telangana police. I'm having trouble playing this video for some reason, so I'll play it at a separate place. Just a second. Okay, so this is what we had done for the Telangana police. So in Telangana, they basically have this event called the Medaram Jatra, and which is very similar to the Kumbh Mela that we have here in North India. And the Telangana police actually wanted a system using which they could monitor the crowd densities in different parts of this the pilgrimage site that was referred to as the Sanctum Sanctorum. So what we basically did was we developed this dashboard for them. Here on, they could view the live video feeds from the on-premise cameras as well as from the drone cameras. And this entire area was divided into 64 different sectors, right? And depending on the crowd density that was present in a certain area, that area was separately highlighted. And then notifications. For every sector, there were people of personnel of Telangana police who were deployed on the ground. So depending on the crowd density in their region or the predicted crowd density in their region, notifications were dispatched to them so that they could take corrective actions. Right? This is how this basically demonstrates how the notifications were dispatched to the personnel on the ground. So say, for instance, if the crowd density in this region is expected to go up by a certain amount, then a notification would go from the control center to the person on the ground saying that, okay, you need to direct people from this particular area over to this exit gate here. That's how this entire application works. And likewise, we actually have a ton of applications for video AI, which are constantly being developed. I think I need not elaborate upon that here because we are already amongst a bunch of computer vision developers here. So, and they are for multiple different industry segments because every industry segment uses video data in some form or the other, right? But as of now, video data is, the field of video AI in general is faced with a certain number of challenges, starting with the development itself, right? Say you could have a very good computer vision algorithm or AI algorithm, but in order to convert it into a product, you need to put in a lot of time and resources, right? At the same time, once you've created a product, you find it very difficult to take it to a market. Say if you're a small startup or an individual developer, how do you reach out to potential customers who are looking for a solution of that kind, right? At the same time, it is difficult for end consumers as well to discover the right solution for their requirements, right? And the third process is that of consumption. So here, and say if you are able to view this graphic on the left side of this graphic, then this is how the video AI applications are currently deployed, wherein you have a bunch of specialized cameras for your application, which of course plug into a certain proprietary hardware. And on top of that, you install your application, right? And at the same time, if you want a different application, then you have to do this entire exercise all over again, right? And if you have a look here, and you are actually creating silos every time you create a new application. And it goes without saying that these are very difficult to, these are not interoperable at all, very difficult to scale up or configure at the same time, right? And towards the right here, this is what a typical control room scenario looks like up until this point, right? You have separate, video walls for every single application. You have a separate video wall for facial recognition systems, for intrusion detection, traffic management, so on and so forth. Now let's go a bit off track for once and talk about what operating systems do in general, right? Or how did our operating systems actually come into the picture? So if you might be able to recall, before operating systems or MS-DOS or the QDOS for that matter came into the picture, Before that, we used to have mainframe computers, each for a specific task. Like there used to be a computer for designing, then there used to be a second computer for accounting and so on and so forth. But then as operating systems came along, then a single computer was now able to run multiple different types of software packages or apps for that matter at the same time, right? So this is basically what Averroes does. It is an operating system for video AI applications, right? Now we will talk about the resolution to the challenges that we had talked about in a reverse order. That is, with first talk about how it helps with consumption, then discovery, and then development. Right. So for consumption, it basically allows you to run multiple different types of video applications concurrently across across video sources, across processing hardware, and across locations as well, right? You need not have any kind of specialized cameras for running your application. It can be deployed on any standard camera that is available in the market. At the same time, you need not limit yourself to a proprietary processing hardware as well. It can, depending on the type of computational power that your application requires, it can be deployed on a laptop to, industrial grade server as well. As for the discovery aspect, so Averroes has actually created the world's AI marketplace, which actually accumulates solutions from young startups, individual developers, as well as academia, and then of course the major video analytics companies which are out there. So basically, developers develop the solutions, and then they are available for consumption for users. So at this point of time, we have more than 50 plus applications for for solving a number of use cases for a wide variety of industry verticals. And the third aspect is that of development. So we have started this program called Averroes Spira for developing the world's first video AI community, and we hope to reduce the process of video AI development by 10x, right? So the computer vision AI developer has to just provide the core algorithm, and then all of the other aspects can be taken. Yeah.
Yeah.
Yeah, I'm just about done.
Yeah. Yes. Thank you.
Okay. So this is all the I hope to get into this in a little more detail, but I'll just skip this for now. Again, this is how the application basically works out. So if you put in a request on the operating system to run a certain application, then all of the deep learning frameworks or libraries which are required, which might be required by the algorithm, are taken care of by the OS. And then you only need to generate the notification or the alert data, and that is then of course pushed back to the user interface once again. So of course, in order to do that, we ensure your ownership, your growth, your visibility, and of course your outreach. If you need to find us on GitHub, then this is the GitHub link for that. Please, we have put in an SDK on GitHub, which for now is a command line tool, but we have a lot of good things coming up, like a dedicated developer dashboard and many other things, which would help you in creating your own computer vision and AI applications. So that's all for now from my side. If we have any questions for now, then we can please take them up.
Yeah. Thank you, Paurush. Probably we'll take up our questions at the end.
Sure.
Okay, thank you. So the next speaker is Dipanshu from HoloKitab Technologies. He's talking on using augmented reality to make books interactive and fuse textbooks and e-learning. And Dipanshu is an edtech entrepreneur, as well as he helps teachers and students to find new ways to teach and learn. He worked with Tres Vista Analytics as well as Amplify Services as an investment banking analyst. He's co-founded HoloKitab Technologies with his partner Miglani, with a motivation of scalable and affordable AR and VR edtech solutions since 2019. So over to Dipanshu, you can share and then start.
Sure. Thank you so much for the introduction. I would especially like to thank Dr. Uma for inviting me here. And I really feel honored to present here at the Indian Conference of Vision, Computer Graphics, and Image Processing. I'm sharing my screen, so just let me know when it's visible. Is my screen visible now?
It's visible. Please go ahead.
Okay. So Yeah. So what's a startup is? It's Hollow Kitab. So basically, it's you can see combination of two words, Hollow and Kitab. Hollow we say hologram, and Kitab is a book. So we have fused this thing, a book that has holograms and that makes you learning even more fun. So I'll begin by just explaining what currently methods we have in schools or at home. So first one is the books like we normally have. We have like standard textbooks, school textbooks, and all that we read. Second is the e-learning. That's the hottest trend right now. Byju's, Khan Academy, and all that. We go to YouTube, search online videos, and mostly this is how our studies are becoming and will become in future. The next one is the standard classroom learning or presentations like these, where your presentation and it's a group one face-to-face learning. So these are the current technology that we use in school. So what's the problem here? So what I feel that there's a one common problem across all these platforms is that the concept of visualization. So there are many concepts that students and teachers may not be able to visualize. And so it takes time to actually explain those things and for students to understand those things because these methods are still 2D and you cannot go to that depth beyond even in using video learning like e-learning. It's not that interactive and that real preview of that thing. So this is the common problem across all the three platforms. So we can like just explaining in more detail. So books, it's a very good and effective way of learning. It's actually keep your brain active and increases your concentration powers. Books will always remain your student's best friend. The problem is that it's very less engaging and have limited information. If you have any doubt or you want to go some more information, you have to go online or ask someone else. So books will have that limited information. The fixed one that it's already printed. In classroom learning, the problem is that everyone has a different pace of learning. So it's sometimes difficult to make a connect with every student and becomes a difficult task to make understand complex things. And the next is e-learning. The hottest trend. It's visual elements. It's fun and easy. The problem is that over a long period of time, it will make your brain lazy. It's a very passive activity. You watch a video for 10, 20 minutes and then go offline and then study, watch a video. So unless you don't read, unless you don't make your brain focus, it's not that you're only feeding videos in your mind. It will make your brain lazy. So what's the solution? So we are mixing books and that fun of the videos into one thing to make interactive 3D books using AR. So our vision is to like keep students always closer to their books. They read in the concentration and without missing the ease and fun of visual elements. And but it's not only the visual elements. We are even improving the video elements to 3D and even making it more detailed, more quickly graspable concepts. What's so unique in our 3D books was the solution that it's AR. So I don't think I need to also explain anything about the AR. So it's we are using from scratch created really in-depth 3D models that explain everything. So I'll tell you, we did an experiment from NCRT book class 6. So we converted one chapter of science and gave it to students 2 years back. And it was really nice to have a central one feedback that they were quickly able to grasp everything. So the chapter was in science, and we have different elements of heart, backbone, and all. So our elements are real 3D. So if you have a study in the chapter of backbone, you have a complete backbone from top, left, right, and all. And it's interactive. If you touch the backbone, you will see the bone marrow inside it, and you will see the text element displayed. What is this? What is this? If you touch the heart, you will see the veins. You see the arteries, and we also included voiceovers in English and Hindi for very better understanding. Well, it's not just computer generated voiceovers, it's natural voiceover. So once you're reading a book, you don't understand anything, just pick your phone, scan, and you interact with the element. You're now actually able to understand what is real and everything text and all. So this is a first product we launched on 27th November 2020, like last month. So we just starting out. So we have launched a 3 textbook for kindergarten right now. It's available on Amazon, and we have 3 available editions for the textbooks. So first one is the normal textbook, second is flashcard, and hardbound gift pack we've also launched. We will soon be launching on the last one. I'd like to show you a demo video of like currently how this thing is working. I'm not sure if video is able to view, but it also has a sound.
Yeah, it is.
Okay.
We're able to see the video.
It also has a sound. I'm not sure if my system audio is
Yeah,
enabled.
it is. Yeah, it is there.
Okay. So yeah, this is a, you can rotate it anywhere. So yeah, it's AR, basically AR. So we have made this book, and we have right now sold more than 200 books since launch. So we have got a very good response, and so we are working on other books right now. Yeah, so this was just a product demo, and yeah, so these are our upcoming products. So the first is the 3D storytelling. That this was the most in demand that we have got from parents. So main feedback is that they want more varieties of books. So we're working on that. And the next is the curriculum-based science. So yeah, so science has many applications that students can learn it easily. So everything will be curriculum-based so that we can uh, keep it to masses and it's acceptable in schools as well as at home. And next is the game-based 3D maths. So there are many projects that we can work on to make maths more engaging in AR using game-based theory. And not only these, there are some life skills that we feel it's not taught in schools, but it should be there for kids, such as disaster management. So, and actually, using AR, we can actually project those things and how things are working, and traffic rules. And another one would be like financial education for kids. So it's mostly like thought that we should teach our kids like that, but that thing can be very engaging and in form of games. So that can be very playable for children. So these are some of our upcoming products. So, so this is a go-to-market strategy right now. So we are serving our retail orders via e-commerce on platforms such as Amazon and Flipkart, and we are also connecting with wholesalers via IndiaMart. So we're getting good response. So and we are to penetrate the offline market. So we are partnering with distributors and wholesalers across India so that it reaches our offline market fast. And we also plan to have exclusive partnership with schools and publishers so that we can create customized AR content or AR books for them. So that's why we're going to penetrate to whole India. And regarding the market validation, so what other players are there? So right now we have the first to market advantage. So in terms of the 3D based book concept, there's one player named Playshiku in Bangalore. So they also make AR based educational toys, and it's raised a funding of USD 13 million. And the other one is NeoBear. It's based in China with the current funding of 56 million US dollars. So it also developed AR-based toys and mobile apps that teaches children to learn words and languages. So we talk about the product life cycle of AR and VR in India. So we have been working on this, like researching on VR and AR since 2018, and yeah, so it's compared to its global counterparts. India is still in a nascent stage, so this shows that it's a very large potential for this technology to be adapted in India and a very good market share to capture. Yeah, so these are competitive advantages that we are the first to market with these type of 3D books, curriculum based, that has the potential to replace school textbooks. And with the economies of scale, our 3D books can be priced closer to school standard textbooks. So, and with that informational content that schools and you can usually provide. So it's not that it's a complement; we are giving a substitute to the normal textbook. So next, our content is certified by experts and as per the guidelines by educational boards. So next is the cost breakup and revenue projections. So we plan to launch 18 different categories of AR books in up to different age groups up to class 10 in the next 3 years. So this is a cost breakup. Like I'm not sure cost projection for some reasons, but our cost breakup is like production. It's 47% of our total cost, and marketing is 17%, and others like salaries and admin staff things it's accounts for 36%. We estimate to generate a revenue of INR 6 million in the coming year, and by 2023 we projected to go to 17 million, implying a CAGR of 60.8%. And so this is some key stats about us that we usually founded in 2018, but we officially incorporated in 2020 and launched our first product on 27th November. Right now, we're located in Jalandhar and in Punjab, and we have sold more than 200 units right now. So our current funding status is bootstrapped, but we're looking for a seed fund of INR 4 million for a 5% equity stake. So yeah, and we got first position in Startup India Punjab Yatra in 2019 for this innovative concept. That's about our team. So my partner Nikhil Minglani. So he's a digital marketer with more than 2 years of experience in SEM, SMO, SMM, and I have more than 2 years of experience in investment banking. And Praveen, he's been with us since last year, and he's been working really on developing AR and NMR applications. Yeah, so I think this is all about us. Any queries, you can reach us here.
Yeah.
I think that should be it.
Yeah, thank you, Deepanshu. I think probably we'll take up a set of questions at the end of the session.
Yeah,
Yeah, after completing. Thank you so much.
thank you.
So the next speaker is Altaf Ganihar from Snaptrude. The title of his talk is Technology Behind the Seamless Design Experience on the Web. Altaf is a founder and CEO at Snaptrude, and he has 5+ years of experience in product development and consulting for developing web applications in the geometry modeling domain. He has a research background in computer graphics, vision, and geometry processing with 10 international publications and 2 patents and couple of papers. Most of the papers are co-authored with me. He has a startup in our incubation at KLA Tech, later moved to Bangalore. So over to Altaf.
Thank you so much, ma'am, for inviting me, and it's a pleasure to be back at ICVGIP after 5 long years. I miss my research days. So today I'm going to be presenting what we are doing at Snaptrude, and I'm trying and going to be a lot more focused on the technology behind what Snaptrude does. But just to give you a little bit of background of what Snaptrude is about, what we are trying to do. So we are in the construction space, the building design space. So basically, if you look at the impact of construction on the world, it contributes third to the world's GDP, and its impact on climate change is actually it's pretty clear and known to everyone that 50% of the climate change is caused by construction, and the impact of design on construction follows the power law, the 80-20. So during the early stages of design process, the impact on the budget, sustainability, and functionality of the project is taken care of, and the SAG goes on reducing over as the project progresses. And in fact, 80% of the construction and operational inefficiencies that are seen in the industry today, and construction is infamously known to be not innovating in nature. So a McKinsey report very recently stated that only 2% of tech spend happens in the construction industry. This leads to huge inefficiencies during the operation stages of the building as well as during the construction, and most of it could be controlled during the design stage. And the main reason why things have been this way is because the architectural process is broken. So it's dominated by legacy tools, by mostly a monopoly. So it involves 4 different tools that are not intuitive in nature by themselves. It's like saying an equivalent to a digital canvas. And because these tools were never meant for the architectural industry, they were actually inspired a lot from the mechanical industry. There's a huge bottleneck when data flows from one application to another. This leads to a flywheel. Since design is such an iterative process, since most of the decisions get taken over here, if you're looking at a flywheel which is broken in nature, where data doesn't get transferred from one tool to another, you're looking at manual data corruption, which will just, like, these are just like naturally happening because the scale of the project is huge and the number of people involved are so much. And these, when they lead on to the construction stage, you wouldn't believe the kind of losses, billions of dollars of losses that actually happen, and also the impact on climate is huge. So what Snaptrude does is it's a web-based design tool. So it's collaborative in nature. It enables all the stakeholders in the construction industry, right from an architect to an interior designer to a project stakeholder or a contractor to collaborate, literally starting from a hand-drawn sketch on a piece of paper. So you can actually just take a picture of it on a phone camera or just do a sketch on an iPad, which magically gets converted into a 3D building model with data as well as analysis added on top of it. So it does a lot of occupancy analysis, built-up area, carpet area calculation, the area scheduling, the budget analysis, which leads to better decisions right at the initial stages of design, where a team can do multiple iterations in lesser amount of time while giving the best efficient design output in reality. So this is what Snaptood is about. But coming to the technology part, so the tech stack largely is a microservice architecture. So the biggest achievement which we have been able to do is run a dynamic geometry kernel on the web, and the entire rendering engine is powered by WebGL. However, we are really looking forward to WebGPU coming out. We are doing a lot of experiments on it, which would be the next spec of how graphics would be supported on browsers. And the entire the era of desktop applications, I have an opinion that desktop applications are going to be sidelined by web applications, where the entire world can collaborate much easily. And WebGL and WebGPU are going to become much more important and standardized as things progress. So in terms of the microservice architecture, we have our 3D rendering engine, which resides a geometry kernel on the web, which in turn talks to a bunch of microservices with shared database, enabling collaboration as well as the optimization and generative algorithms. So if you're looking at just the geometry kernel and the rendering engine on the web, which runs the main interactive workflow, there are the generative models that actually power these things using a bunch of computer vision and machine learning algorithms. So we have a module which actually converts hands-on sketches to 3D models or 2D layouts, and there's a bunch of optimization that goes around. So it uses machine learning and computer vision to be able to optimally create what could be the best possible design that can come out of a hand-drawn sketch, to generative design capabilities of converting massing studies, which are just basically a bunch of blocks, into what could be a better plausible design option on a large-scale project while minimizing cost and area. So these are some of the constraints which we always consider. To auto interiors. So basically at any scale of the project, you can actually just do an occupancy analysis or do automated interiors, which basically serves as a great feedback for design teams to understand how do they objectively evaluate the design. So most of the time, architecture is a mix of objective and subjective constraints. Due to lack of better tools, it just largely resides on the subjective aspects, where we are trying to add the objective aspect into the design process so they can make better informed decisions. So these are just 3 modules. We have a space optimization layout, which is using GAN, but still is not out into the public. It's still under development. And we do use a lot of optimization algorithms throughout the entire process, throughout the entire design journey of an architect. Currently, Snaptood is applicable to not just normal building designs, right from site feasibility or master planning, where data becomes extremely important. Snaptood is perfect candidate for that. We have seen people use it on large-scale projects for master planning to determine cost implication even before a site is purchased by the builder, so that they can actually evaluate, is it the ROI of the land is worth investing or not, to massing studies where they would want to do client presentations, etc. And since we run a geometry kernel, we've been able to bring out the tessellated data and export it to the standard file formats that can go into a render engine like Lumion, 3ds Max, even Blender for that matter. And people can actually generate beautiful renders for their presentation to even the building information data, which would help them do construction documentation or even do detailing of their designs, where they would be able to know how much the wall is, like the kind of insulation that goes into a wall, the kind of concrete, plaster, etc., which is needed for constructing the floor, the plinths, the slabs. All of those details can be added right inside Snaproot, and it's also compatible with the existing workflow which people have been using, the Autodesk ecosystem or the ArchiCAD ecosystem, which has been there, because we have tried to build a layer of interoperability over all of these different modules which run Snaproot. And currently we are being used by over 1,500 users across 9 countries, right from builders for feasibility studies to large architectural firms in India, US, Europe. About 1 million square feet gets designed per month on the product, and the next year we are actively expanding in the Western geographies. Looking forward to looking forward to 2021, as 2020 was a disaster. So thank you so much. So this is my contact details. Would love to. We are always looking out for researchers, etc., to join our team. Like if anybody is interested, please feel free to reach out to me, and would be happy to take any questions at the end of the sessions. Thank you so much.
Yeah. Thank you, Altaf. So we shall take up questions at the end of the session.
Sure.
Yeah, our next speaker is Nilima from Test AING, and she talks about testing AI applications. So I welcome Nilima. Nilima is the mind of Test AING, the next generation AI testing conference. She has 20 plus years of experience in the IT industry, spanning startups and enterprises. She is a serial entrepreneur focusing on generating value for customers. Her focus areas are data science, natural language processing, and machine learning based AI. She has delivered dozens of IT projects in AI and trained over 4,000 students in the areas related to data sciences. So over to Nilima. Nilima, please.
Thank you, Uma and IIT Jodhpur for giving me this wonderful opportunity. And I would like to share my screen before I proceed.
Yeah, please.
I'm the co-founder of TIE Test AING. I would like to brief about our company before I actually tell you about our product. Our company is the first of a kind of its own in the world, which is testing AI products. Right. With the buzz of the AI, there are many companies and products that are developed on AI, right? But there is a lack of testing. It's not tested properly. When I say not tested properly, the reason is it is tested randomized. And that is the reason there are many accidents that are occurring across the world, right? You would have heard of Amazon dropping out its recruitment tool because it displayed bias. You would have also heard of Microsoft chatbot because there are tones of there are tones of bias in Microsoft chatbot also. And the driverless car hit with accidents. It was a pedestrian accident. There are multiple accidents like this that have happened in many of the AI products. The reason being, the AI products not being tested rigorously, and there is a lack of trust. And this is what we are trying to solve. All the AI solutions suffer from trust issues. Right? Trust is a potential.
Hello, Nilima. We lost you.
test ing. We also refer to it as TAI, TAI, test AING. So it is to overcome incidents of accidents of deployments of AI technologies. We want to be able to deliver end-to-end quality assurance for AI-based systems so that they can be fully deployed. Let there be no indulgence of humans coming into picture, which is possible in some places, but which may not be possible in many of the AI pools. That is the reason we are unable to deploy fully. And we are trying to leverage the state-of-the-art innovative practices for testing these AI-based systems. I'll explain you a little more in detail once we come into the next slides. We are developing a comprehensive suite to enhance acceptability and assurance of AI-based systems. The reason behind this, there's a mistrust on these AI applications because they're not tested properly. As I was mentioning before, Google Photos, there are many accidents, right? Amazon, there is a gender bias hiring tool which was withdrawn. And what is the effect? The reason being there is a data bias. There's an issue with the fairness, and it led to loss of reputation. Microsoft chatbot Tay, there was a mistrust, and it led to loss of money. Google Photos, actually, you can see the first picture on the left-hand side. Google Photos mixes sky with a mountain. This is because there is a lack of transparency, and it resulted in an inefficient release. The last but not the least, Uber's driverless car kills a pedestrian. It is loss of life. It is a compliance issues. So all these issues we are actually targeting to resolve with our application, with our solution. And our solution, as you know, AI applications can be on different types of data. It can be on the image data, it can be on the video type of videos, it can be on the structured data, it can be on the text, it can be audio. So we have 5 different pipelines in our AI application too. We are already done with the initial versions of the AI applications which are working on the image data and the text too. As I was saying, the target is to detect the bias, to bring in transparency in the AI application, and to also help detect the corner cases, which is very important, right? Corner cases are the ones which actually lead to the false positive or inaccuracy, whatever you can term it as. And effectively, it leads to an inefficient release. But when our product or our solution is used, it leads to an efficient release. It saves time, money, and reputation. Now let's come to internals of our product. Our product is, we have named it as AI Rawat, okay, AI Rawat. It stands for Augmented Interpretable Reversed and Workflow Integrated Adversely Tested. We use different features like data augmentation when needed, fairness evaluation, right? Fairness evaluation using transparency helps us actually detect where is the problem. So we have used many features like this: data augmentation, fairness evaluation, metamorphic testing. As I was saying, the test oracle is one of the key issues for the AI products to fail. So we are creating a pseudo test oracle using metamorphic testing, the white box testing. We're also bringing features like explainability, interpretability. We're also targeting the security issues using adversarial testing. We're using test case generation, and we're also trying to inference testing and optimization. With our tool, we can integrate with solutions like MLflow, H2O, which is AutoML also. We are integration with experiment management solutions. We have features where we can integrate with experiment management solutions. We can also integrate with performance testing tools. Last but not the least, the privacy and compliance issues can also be handled with our tool, which is ARAM. Now, because of the limitation of the time, let me only focus on how we are going to handle the pseudo test oracle generation using the metamorphic testing. Let me explain what is metamorphic testing and how is AI coming into picture over here. Generally, as you know, as all of you are working on AI, you know, right? For testing any IT solution, we have a standard test suite. You have the input, you also have the output, defined input and defined output. And when this data is given to a tester, he uses this input data and validates if the output that is generated is as expected and as given in the Oracle data. But how does AI work? Does AI work with a set of rules? No. Everything is fuzzy in machine learning. Machine learning uses fuzziness, leading to lack of test directly. Just because the output only is based on the probability of the data that is given, based on the data and the output that is given to, in case of supervised learning in AI, there is a probability that comes into picture, right? Only based on the probability, the output is given. So it is all fuzzy. So there is a lack of test oracle. So we have come with option of metamorphic testing, using which we are creating the test oracle. It's a pseudo test oracle though. In a case of normal oracle, as I said, you have a known X input and Y output, which is also known. And when that is given to the tester, he validates it if the actual output is the same as the expected output. That there it ends. That's the normal oracle. In the case of metamorphic testing, the way we go ahead is we give X input, we have X input and Y output, right? So now when we apply a metamorphic relation on the input data, we know how the output is expected just because we know the relation between the X and Y. And now when we are actually transforming the input data, if the output that is generated is similar to what was expected or same as what was expected, then it is fine. Otherwise, there is something wrong in the implementation of the algorithm or maybe pre-processing of the data. That is the logic we are using. Let's say, let me take a simple example of, to keep it simple, I'm taking X numbers which are in a list. And now the output of this X and numbers, the addition, the output, the sum of all these numbers is Y. Let us say I apply a metamorphic transformation, I apply transformation. That is, I perturbate this number, that is, change the order of these numbers. What is the output? As per our understanding and as per the relation between the input and the output in this particular functionality, the output should remain the same, right? And in case the output doesn't remain the same, there is something wrong in our implementation, right? This is the logic that we are going ahead in our metamorphic testing to create this test oracle. Now, giving the similar example in terms of machine learning and computer vision. Let's say I have a set of images and now I have applied, or maybe the AI application, whichever is using classification, AI application is applying classification to classify all these images. Now, input data we have, but now for me to create the test oracle, what I'm going to do is, because the input data is a set of images and output has actually classified the data with some accuracy. Now, even when I transform the input data with some angular rotation probably, or maybe change in the color or some changes, some permutation, I just change the data in some way, the output should still remain the same, right? The output classification should remain the same. And in case it does not, so what we do as part of pseudo oracle creation using metamorphic testing is we actually transform the input data and see that the accuracy of the classification that comes into picture should be the same as before. And in case the accuracy is different, we would actually share it with the developers or the development team that there is something wrong in the implementation, and the implementators or the development team will rework on it. So this helps build a robust application. I've given you a very simple example, but in reality, we use many more techniques. The way we use metamorphic testing is what was done. Here are some other examples that I was quoting about metamorphic testing. And this is not just metamorphic testing that we use, we also use explainability. Explainability, which helps the developer understand which portion of the image is the AI application targeting, to understand what is a target image. This helps the developer to, not just the developer, again, as I said, the development team to actually rework on the application and build a robust application. Any questions over here?
Yeah.
Okay,
Please,
fine.
Nilima, we can take the questions at the end. So,
Okay,
please
no issues,
conclude.
yeah. And this was a simple example that I've given, but I was saying we are building an end-to-end testing application for testing robust AI applications. And the market opportunity is as shown in the picture here, $733 billion by 2027. And by 2025, just annual global software revenue itself will be $126 billion. And we realize that 50% of the failure rate is reported by 25% of enterprises deploying AI, just because there is no rigorous testing done. And once we are done with all the different pipelines, we are already done with 2 of it, 3 more left. our application will be able to help build robust AI application everywhere our application is native. And we have a set of 5 founders, and our CEO is Vipul Kochar, who is considered as the testing guru. He has more than 25 years of experience, and he was the president of, he was actually leading the testing certification, Indian Testing Board president. And Dr. Srinivas Padmanabhan, who is our CTO, is is an AI guru. He has more than 25 years of experience in AI. He has patented more than 25 plus patents. The third is myself, Neelima. I have more than 20 years of experience in AI. I've also been rewarded as the women in AI. And we have Saurabh Bansal, who's the engineering and delivery head, is Ramit Manohar. All of us comprehensively, we have around 100 years of experience. And with our experience in testing and AI, we are building a robust AI testing application. We have already had 2 successful deployments, one on the EduTech customer side, when the EduTech customer come up with realized corner cases before even it was deployed. Even after the testing was done, they were about to deploy it, but they have used our application. They could realize the corner, they could actually detect the corner cases, and they have reworked on their application. They are very happy about our product, and 2 other customers are in the pipeline. And by us, our team is, we are using innovative technologies. We have 3 patents in the pipeline, and our team, as I said, is best of AI testing and engineering experience. We are seasoned, experienced professionals, and time and exit possibility. Exit possibility is also there because ours is one of first of its kind in the world. Yes, that is. Any questions here?
Yeah, thank you, Nilima. We'll pick up a question at the end. Yeah.
Hello.
Yeah, thank you, Nilima. We'll pick up a questions at the end.
Okay, thank you. Thanks for giving this opportunity.
Yeah. Now we have the last talk by Angel Networks. So this is the most awaited talk. So I invite Sandro Stephen from Indian Angel Network, India's first and the world's largest network of angel investors. So Sandro Stephen is an entrepreneur at heart, and he started his career as a sales executive in 2005 and worked with Max New York Life Insurance, Airtel, and Peterson's Travel Services. Stephen was always keen to explore his entrepreneurial side and started dossier placements, and the startup did not fly due to lack of funds. So later he joined Indian Angel Network in 2013, and primarily he looks into a sourcing and evaluating deal for fundraising, building relations with existing and new potential investors, as well as building partnership with the startup ecosystem enablers across India. He also actively involved in mentoring and young entrepreneurs on how to pitch to the investors. I think I welcome Sandro, and then over to you.
Hi, good morning, rather good afternoon now. Good to be here. It's good to see that, we have a couple of really good startups coming and pitching here and sharing their ideas of what they're doing, especially in the deep tech side of it. It's quite interesting to see how kind of things have kind of really changed, especially with COVID around. Now, what we see is a lot of entrepreneurs are actually doing quality thinking and actually thinking on the right direction. Earlier, we used to find a lot of Me Too ideas coming in, which was really not of much of interest for investors to kind of encash on. But having said that, now with the coming change which is happening, we see a lot of companies coming in with a lot of good quality thought process being put behind actually building what they're building right now. So, great initiatives like today's also all the companies which we're talking about what they're doing is kind of really commendable to see how they're kind of thinking in the right direction and in the right sense. I urge all the participants here to kind of think like that and think more deep in terms of what is the real use case for investors to kind of look at it. I won't. What I'll do is I'll take a lot of questions towards the end, but before that, I would kind of just want to highlight on angel investments and how angel investors kind of perceive when they look at any startup and what they mean by when they look at these companies. So, a couple of points that I would want to kind of highlight, which are really a no-go for investors, which could be a no-go, could be a red flag for them to kind of, say or hold on to a proposition before investing, is that firstly, they would not want to see any incomplete product. So what it means is that you should have at least the POC or some uh, been done of the final product being ready before you reach out to investors. Because what happens is that if you try to reach out before that, it becomes kind of an incomplete product. Firstly, secondly, you yourself are not clear how the product will actually shape out to be in the final terms. So first thing, incomplete product. If you have an incomplete product, I would not want you to approach investors. Rather, do some families and friends and kind of then build it up and then reach out to investors. A lot of investors do want to see a lot of validation of their final product. It could be any whatever you're building, whether a tech or a non-tech company, whatever you are building. A customer validation kind of really helps the investor validate the whole proposition in a much better form. So if you have validation, fantastic. Typically, a single founding team is not completely a red flag, but yes, if you have 2 or 3 co-founders, it kind of really helps a lot for an investor to be more comfortable with the team to kind of invest in. There are multiple reasons of saying that, and that's how they kind of function. So I would urge all the founders who are participants who are listening to me, if you plan to start your own journey as an entrepreneur, think about doing something in terms of finding a co-founder, because entrepreneurship anyways is a lonely journey. You might as well get a friend along or a partner along who understands what you do, and you both have the same vision and the mission to kind of take the company to the next level. If you don't if you're not aligned with your co-founder in the vision and the mission of the company, I would say look for someone else who can actually help you with it. One major red flag, all of you please remember this, is that if you are a non-mentorable founder or a founding team, let me tell you, it becomes a major red flag for investors. When they're speaking to you, they're going to kind of question you with a lot of things and see that, how comfortable are you with taking questions? How comfortable are you with taking suggestions? How do you handle stress? How do you handle suggestions? How do you handle rejections? How do you, rejections in terms of your ideas, what the investors feel, and how do you kind of overcome with it? All this kind of sums up to make an investor understand what kind of founder you are. So if he or she feels that you're stubborn and you're stuck up, you're not open to kind of take suggestions or feedbacks in a positive terms, or open to discuss on points which are not in line, then it becomes a red flag. So kind of becomes a major issue with a lot of investors. Um, one major thing besides a non-mentorable team is that when you reach out to investors, typically you've not done a deep thinking about how much money do you really need. That becomes quite a issue. I mean, it's not a major issue because that can be, if there is interest from investor, they can sit and talk around that. But it's always good for because if you as entrepreneurs know what you want exactly, it becomes more clearer for an investor to perceive that yes, the entrepreneur in which I'm going to invest, the company where I'm investing, the founders are kind of well thought through. They've kind of done a deeper dive in terms of what they want to achieve with this given money. So what happens is typically when I'm seeing a lot of companies come up to us for investment fundraising, at that time they kind of ask for unrealistic ask. For example, they're looking to raise raise amounts like 6 crore or 5 crores for the next 1.5 2 years, wherein actually put together, if you really sit down and kind of do the maths right, you sometimes don't even require anything beyond 3 crores. So what happens is that this kind of becomes a slight negative point for the investor when they look at the entrepreneur, which means that the entrepreneur has not actually done a deeper thinking on what they really want. uh, Along with the ask, what is also important is to kind of understand what is the right valuation. Now, the right valuation is something that you need to kind of figure out while you speak to these experts of the domain, and they will actually help you identify what is the right valuation for your company. This can, I'll give you an example. In a FMCG company, I saw the founder came up to us with a 70 crore valuation. And this valuation was actually derived based on some, research work done by one of the leading big fours, like the KPMG and the PwC of the world. And apparently, there's no point spending that kind of money in kind of actually figuring out what is the valuation of the company, because at an early stage where you kind of go to angel investors for fundraising, typically these valuations, where you kind of derive valuation from these big fours, really don't stand a chance to discuss with the investor. They will not look into it. Why? Because at an early stage, you really can't value the company in some format. But it's typically a mutual understanding between the founder and the incoming investor that they sign up on. So it's ideally two ways of doing investment. One is equity based, the other is convertible. Or you kind of get a convertible note or a safe note to be called as, where you kind of give a discount to the incoming investor that, okay, whenever the valuation is derived, you 20% discount on that valuation when it happens. Unless until you need money for manufacturing, or you need money for setting up a plant, then in that case, I would suggest that instead of looking at equity money or a convertible note, look for a debt, because eventually, equity money should always be invested in company for the growth of the company in terms of working capital, in terms of other aspects. Wherein if you're looking money for actually setting up a manufacturing unit, or you're looking to buy a property, I would suggest that you look for a debt rather than actually looking for equity, because eventually losing equity will not be wise enough in such format. These are the few things. I can actually go on with a lot of more other points which are very important. But everything is important according to me. But I would rather keep open for you participants to kind of ask me questions as to whatever you have. I'm happy to answer that. And
Yeah, thank you, Sandra. I think I'm not seeing any questions from the.
I have a question here. Thank you,
Yeah,
Sandra,
please.
for the explanation. Is it that the valuation of the company is the uniqueness or the revenue that it is going to generate? Because our company, TestING, we see a great uniqueness, and when we have actually shared it with our friends in abroad in US, they find it to be very valuable with people who are in the startup area. Okay, but here when we see when we are actually meeting with the investor, we realize that it is only the investors are only looking at the possible revenue that we get in the future, the revenue that we have already calculated. So, what is
yeah,
that
so
should we not worry about the uniqueness of our product?
no. It is. I mean, that's the only entry barrier that you will have to kind of make you stand out. Otherwise, it gets you become one of the same in the crowd, right? So you don't want to be
Yeah,
like that. You want to stand
yeah,
out different, and that's your USP. Do not let go of your USP, please. I mean, that's not what I meant. What I meant was that, see, here, what you're talking about are two different elements.
yeah.
Investors in US have a different mindset of investment.
Mm,
Investors in India have a different mindset of investment. There are two different sets of people here. Uh, in angel investors in US typically do convertible note. They don't do equity price rounds.
okay.
And if you are getting investments from there, I mean, you're free to kind of go whichever way you feel that, you can route the money with your legal experts and all. But having said that, I think, investors in US are more savvy. Why? Because they've been doing this for a very long time. And hence their mode of investment is totally different. Wherein in India, it is yet growing. Angel investors are more stepping in and kind of looking at what angel investment is all about as a business opportunity for them.
Yeah,
So typically, we as Indians are angel investors, and Indians typically
Yeah,
look at more of realistic numbers also at the same time. But having said that, if you have a unique idea and your value is totally unique, where you kind of stand out different, That doesn't mean that investors are going to let go of that fact. The only point is that if somebody is letting go of that point and really not valuing your USP, until he has a very strong point as to why he is not valuing your USP, then it's different. But if he's not valuing your USP, I think you need to look at other investors and talk to more people around it to see that what is happening, and look at getting the right investor on board. See, it's not only about just getting the money on board, right? I mean, money can be brought in by anyone, but you need value along with that. Now, if you don't find the value with the investor, you might as well look for somebody else.
Yeah, I think in the interest of time, so we'll restrict and anyway, all of us have the contacts of all the speakers. So I request attendees to raise questions or send mails to the speakers for more details. I thank all the speakers again. Thank you so much. Over to Parag. Parag? Parag?
Am I audible?
Yeah. You are audible. Go ahead.
Thank you, Uma, and thank you to all the speakers and panelists of the startup session for this very informative session. I'm sure our budding young entrepreneurs in the area of computer vision, graphics and image processing, and PR and AI would have learned a lot about how to go about starting their startups. And if they have questions, please reach out to the speakers or please reach out to Professor Uma, and she will direct your questions to the appropriate person. Now we have the session with the IUPRI award talks. So we will directly move on to that. I will hand over to Professor Bhavatosh Chanda, who is the session chair for this session, to conduct the talks. Over to you, Bhavatosh.
Okay, thank you, Parag, and good afternoon to all and everybody here. I hope the speakers are already present in the panel. Badri?
Yeah, I'm present.
Okay, and Konda?
Yes, sir. I'm too.
Okay, so we are really happy and glad to tell again that Konda and the UPRI actually presents a best PhD thesis award submitted to any Indian university or any Indian institute for PhD degree. And usually it's award is given to every 2 year cycles. So we have announced award is announced for the cycle 1st October 2018 to 30th September 2019, and that award goes to Konda Reddy Mopuri of ISC Bangalore. As a supervisor is R. Venkatesh Babu. And the next cycle, there is 1st October 2019 to 30th September 2020. This goes to Badrinath Patso. The supervisor is Binoy Nambudri. So they will present their work in around 25 minutes, and there may be 1 or 2 questions to make up with the time given to us. So I request Konda to present first, and please go ahead, Konda.
Yeah. Let me thank all the award committee members and IUPRI for conferring me this great honor. It's it gives me an immense pleasure, and without much delay, I think in the interest of time, let us just go ahead with the presentation. I'll start sharing. That's fine, right? I shall be sharing my screen and.
Not yet. I can't see anything.
Yes, now you can share.
Okay.
Yeah, hope you can see my.
Yeah, that's fine.
Yeah, right. So this is my thesis, Deep Visual Representations, a study on augmentation, visualization, and robustness. So we all have witnessed the success stories of deep learning, primarily in the application areas of AI, such as computer vision, speech and audio, natural language processing. Right, almost all the state-of-the-art systems are now driven by the deep neural networks behind such systems. Not only these application fronts, far beyond these application fronts nowadays. So what has really DL enabled, deep learning enabled? The answer is quite simple: representations, right? The features that DL enabled are the responsible thing behind all this, successful state-of-the-art systems that have remarkable performances in all the areas. So let's just take an example in computer vision. This is how a typical CNN looks, convolutional neural network looks, and below which you can see the features learned also, right from small edge and blob detectors, and slowly towards the combinations of them and parts of the objects, and towards the objects themselves, right? These are the features learned in a data-driven fashion and also task-specific fashion, which have enabled, arguably human-like vision recognition performances, at least, if not the other stuff, right? So the features, which is the new thing, remarkable invention, I would call, as opposed to the existing, handcrafted features and then driving ML systems, which was which had a gap in between the features and the tasks. Pardon. Yeah, so that is the primary remarkable thing that happened with this, deep neural networks in somewhere around 2012. So that was the focus of our thesis. We wanted to study, we wanted to learn about them and contribute in that context. So the thesis is basically about augmenting and visualizing and trying to find out the stability aspects of these features that have enabled this remarkable performances. Although we restricted to computer vision, we believe that these techniques and the study as a whole is general and goes beyond vision into other application areas like speech and language also. So let us start with the different aspects that we studied and contributed. So we studied how we can augment the existing representations using side and additional information for computer vision applications like retrieval, search, and also because in the early days, even now, the models are criticized for being opaque, being black boxes, right? We really have no say in any of this hierarchy, right? The features were learned automatically with some loss function driving the parameter learning. And yeah, as a whole, it was not decomposable. So for that problem, a lot of, doubt was there in the initial days whether to adopt, whether it will become a more sustainable, technology, etc., etc. So yes, we had the responsibility of making the models more decomposable or interpretable, so that not only the decisions but also the whole mechanism has to be human interpretable. So we contributed and analyzed in that aspect also. And another important aspect we studied towards the end is robustness. So adversarial perturbations is something very intriguing about these models, where a small structured perturbation can really throw the models off the track by making them almost stupid-like. So we wanted to understand and try to unearth some of the vulnerabilities that were not familiar to the community, so that people can study them thoroughly and make them more trustworthy. So let us start with the first part, where we kind of augmented the existing representations with additional information, which is objectness and strong supervision. So on the right, you can see the dataset images, where these are from ImageNet. You can see images are very simple, where you have almost one of the objects, only one object that is present, and labeling is almost unambiguous, and things can be learned in easy fashion. But on the left side, you can see the real world images, where you can see all sort of challenges with respect to scale, with respect to clutter, background, everything, right? So we need to use the learned features on the images on the right to perform some tasks on the images on the left. Right, this is where we wanted to adopt. Right, the naive way should be going for different scales and then try to pool and concatenate and do some sort of multi-scale approach, which is computationally heavy, and issues of background coming into the representation and contaminating the thing all will come up. So what we did is just a caveat, because of the time and the vast scope, we just wanted to present the broad ideas. Of course, some of the techniques are no more state of the art, but they were when we published them. So I think it's a good idea to discuss the ideas and the value of it than presenting and throwing some of the tables at you. So please stop me if it is if there is any question, but let me progress with presenting the ideas that we had contributed. Okay, so because of the issues with the naive approach, what we did is we tried to make it more computationally effective and also performance-wise also effective. How? By concentrating on the object-like regions. Particularly, this application is a scene retrieval where we were trying to use the deep learned representations to drive the systems, right? So instead of going for multi-scale and then contaminating and spending more computations in getting the representation, what we did is we kind of restricted our description or our representations only to the object-like regions. So we extracted regions like this from a given scene and then went for describing those and then pooling a signature out of all this set of representations, right? Also, while pooling, we try different poolings because we need to effectively summarize the scene content without losing the discriminability of the resulting response, right? So this is one of the early works from our lab, which got published in Diffusion Workshop of CVPR and won a travel award also for its efficiency in the representing the scenes. So for example, from all these object-like regions that are extracted, we can go all the way down to 32-dimensional vector to represent the scene, right? Further, we investigated binarizing on top of the pooling also, not only PCA kind of compressions, but also we went to an extreme compression of binarizing the representation and then performing retrieval with a simple Hamming code, Hamming distance sort of a metric, which was very effective despite its despite the loss of information in all these compressions, right? So this is the first of our works that started with visual representations. So we also wanted to use strong supervision when it comes to representing scenes, right? So we all know transfer learning in machine learning and deep learning. So what it means is basically trying to transfer some of the learning from task A to task B. When it comes to deep learning, it may be copying some of the layers, adopting them to the another target task at hand, right? In the figure, you can see data A and task A is learned in the orange network, and I'm trying to copy a couple of layers from the left side, which are the shallow layers, which are processing the data directly to another task, which is B, and then on top of the these borrowed layers, I'm building new set of layers that are specific to my task B, right? And then we fine tune the earlier layers and learn the new layers that are shown in blue also. This is very familiar. The task A, most of our works uses the ImageNet trained models like VGG, ResNet, AlexNet sort of things because of the vast data they have seen, they have learned from. So this is a this is like a step zero after the ImageNet revolution. So what we wanted to do is, if you look at these models that are pre-trained on ImageNet, they are learned from ImageNet labels, and which are only presence or absence of one of the 1,000 objects, right? The information conveyed them in a way is limited, right? So all that they say is presence or absence of one of these objects. right? But if you take applications like retrieval that require attributes of the objects also to be considered, not only dog, but I want a specific dog sitting next to a specific thing, right? Something like more specific object retrieval, right? So those applications, because of the variable invariance learned in the pre-trained representations, is not possible to get as easy. So in that problem, what we tried to do is, because the label information is very weak, we wanted to look at other labels that are very strong. So for example, if you take a look at some of the images in MS Coco, this is how the images and the labels look. Labels are complete sentences describing the content of the image. A man holding a child while standing at the fence of an elephant zoo enclosure, right? Almost all the predominant, like important objects are there mentioned in the label, and also the action is also mentioned, right? So compared to just the labels, this is sometimes labels are also it won't be the complete list of objects, right? For example, if you take a look at these, these are not suitable examples. So ImageNet may also have sometimes, so this is an ImageNet image. You have multiple objects, but the label would be only one of them, right? So because of all these issues, we wanted to go for a strong supervision to learn the representations for a specific object retrieval. So if you see these data sets are also in investigation for applications more like caption generation, where the task is looking at the image and automating the caption description. For example, if you see this input image gets a caption like a man riding a wave on top of the surfboard, right? This is an example task that can be performed on data sets like this, where you can throw data of this sort with image and label as the caption, as the training data, and then try attempting the automatic caption generation problems, right? So this is a simple LSTM decoder where the encoded visual information coming from a CNN is just decoded into a sentence using an LSTM, right? So this is one of the applications. So what we wanted to, there are a couple of other applications also, which is this is just one caption for the entire image. And the second application is called dense captioning, which is you will get captions, partial captions for different portions of the image. For example, a man and a dog. It's not a complete sentence, but it's a description for the parts of the image. Right? This is another application which can be developed on data like that. So what we wanted to do is, we wanted to exploit the features learned by the systems with strong supervision, which was not done so far, which was only restricted to the pre-trained networks on ImageNet. So because of the specific requirements coming from the applications, which is a specific object retrieval, so we wanted to use this representations learned from strong supervision, and we developed a system, which is like a Siamese network, where on top of these features that are learned with strong supervision, we built a specific Siamese network where we can perform the specific object retrieval using the modified Siamese laws. We also modified to include non-binary relevances. For example, if you give a pair of images, it's very hard to label them relevant or irrelevant. There will be graded relevance. Sometimes you see a strong relevance, sometimes you see a weak relevance, sometimes you see almost no relevance. So because this kind of a database wasn't there, our lab collected data and made it public also during this work. And with the modified Siamese laws, we were able to train and perform the specific object retrieval, where you want to retrieve not only the images of the same object, but in the same configuration or with the same attributes like color, having similar neighboring objects, etc. Right? So this was presented at SPCOM and won the Best Paper Award also. So the inferences were multiple actually. So for example, applications like scene retrieval, which were not using the strong supervision, we started to look into that aspect and fusing complementary information. For example, if you see the full image caption was giving a global information, and on the other side, dense captioning gives attribute information that are present at different regions in the image. So fusing them is because they are complementary will give you better and effective representations, right? Also, caption generator models have knowledge acquired via strong supervision, just lying there, so until then, which was not much used. So we were the kind of early explorers of that representations into other applications like specific object retrieval. So that is kind of what we did mainly in the augmentation part of these thesis. And the second one is about visualizing the models and the representations they have learned. Right, this was some way back, maybe 4 years ago. This was the feeling of most of some of the researchers in CV because all that they see is image is sent in. We don't know what features it is extracting, and it simply says the label out. So we just wanted to dig it out, right? We wanted to make it explainable, the model to be interpretable, right? So we also did something in this. So we took a specific example of object recognition and caption generation. We wanted to make the models more explainable. For example, you see the images here, a CNN like ResNet will look at this image, process it, and throw the labels out. Right? Sometimes you may be, these are simple images, but look at, take an example from medical diagnosis, right? Instead of just saying a decision like yes or no, you may actually want some evidence to the predicted inference from the input on the image that it is being processed, right? So this is in a way visually explaining their inference, right? Remember, these are models that are performing recognition, which is they are not trained on any input like this. They are just trained on image and label sort of base data. And despite that, we developed a technique to make the models explainable in terms of giving these visual explanations. For example, instead of just saying the label bird, it will also show the regions where the evidence for the predicted label is highlighted. Right, so this is one way to make them. This is not the way, but this is one way to make the models explainable. The features that are there can be, grounded, can be made to point the evidence on the input. So we did develop such a technique. So this is an overview where we backtrack the label predicted. So this is the input image, and we have convolutional layers and then fully connected layers, and towards it you have the label predicted. So once the label is predicted, you can kind of extract this evidence. As you see, the pixels in the input image are highlighted in red, saying that this is the evidence for what it is predicted. Right? This is why it is predicted, what is predicted. So I'll try to briefly give you the technique behind the technical details behind this algorithm. So what we do is we essentially backtrack the evidence right from the label layer all the way down to the input layer, which is the image, right? So what is happening is you just unroll the forward pass operation in order to identify the strong actuators in the previous layer, right? So if you see, this is the final fully connected layer, and this is the embedding coming from all the previous layers, right? So you can find out this is just a Hadamard product happening, right? W transpose X plus P is what is happening as the confidence. So W is weights learned and X is the feature embedding. So you can identify the portions of X because we know the W. Remember, this is all happening in a on a trained model where the Ws and all are learned and given it to us. Right? Because of that, we can identify the portions of X that are strongly contributing for this neuron to be activated, which is the confidence for a particular link. Right? If you just go on doing this iteratively, we will end up doing finding the important regions that are contributing for the predicted label on the input image. So this is as simple as it looks. So just backtracking the forward pass operation in order to find the evidence in the input image. right? So this is very generic. You don't need to do any modifications in the architecture, or we don't need to train, retrain, or change any modifications. So these operations can be made available as simple layers, and which we did and made the codes public. So this work is also presented, accepted in TIP, transactions in image processing. So it's one of the widely adopted codes in the recent years from our lab. So yeah, multiple people, primarily from the CNN-based applications in medical images, and it gives some kind of an evidence to the prediction made. So yeah, we've seen questions coming from people who are using CNNs in medical image diagnosis, etc. Right. So not only that, there are a lot of applications to these techniques, such as weakly supervised learning, weakly supervised localization, because remember, we trained the models only on the image and the label pair. There was no localization information. Despite that, the models can localize the objects. You can see, right, this image, if you are given to these visualization methods, they don't not only give the label, but also locate the object, right? So this is one of the interesting applications. And we could ground the captions also, right? We took existing caption predicting algorithms and did the same thing what we did for recognition. And see, we can locate multiple regions that are responsible for the given caption. In this case, a woman is riding a horse in a field, right? So a man is standing in front of a stove. So yeah, so all these things are possible despite the model not being trained to do so. So that's something what we've done. Yeah, we took it to other modalities like sketch recognition, also, as I said, medical imaging as well. And yes, this is another interesting application we found out. What it is basically trying to find explanations for erroneous predictions. See, this is the input image where the ground truth is suit. This is an image from ImageNet. So the model predicts loafer and identifies the loafer region actually and correctly. And the problem with this is the label is suit. Yes, suit is present, but there's another label, loafer is present, but the database doesn't give the label. So the image is not labeled with loafer. So this is an issue with the data set itself, right? The model recognizes loafer because it is there. Just that the ground truth is suit doesn't make the model inaccurate, right? So presence of these images complicates evaluation and complicates learning also, because all the way during the training, this image is enforced. The model is enforced to learn suit label from this. Although there is a conflicting ground truth label and evidence to that label also. So by identifying such images and removing them from the data set, we can make the models learn better and avoid these issues in the evaluation. All these images are very similar to them. Binoculars is the ground truth, but the model predicts macaw, and there is a macaw. Similarly, window screen is the ground truth for this, but at the same time, the image has a flower pot, which is a valid label from those 1,000 ImageNet labels. Similarly, quilt is the ground truth label, but you have a Labrador, which the model identifies and predicts. So these are some of the applications we found. Yeah, visualization as a whole is very important, right? At different stages of AI development. When the particular AI is significantly inferior to humans, we need it because we need to identify the failure modes. When the AI is on par, something like a recognition application, we need to establish the trust and reliability of these models to users. So visualization can do this also. And the third stage where AI is significantly stronger than humans, for example, applications like chess and Go, right? We've seen machines, beating the humans. So in this scenario, visualization is required for machine teaching. We can learn those important strategies probably by visualizing the prediction, right? So visualization is really important, and we've been doing even now. So that's from the second part. And third part is about robustness of these learned representations, right? So we might have seen this number of times already. So this is the scenario where a structured perturbation, although it is very mild, when it is added to a clean image, these convolutional neural networks predict something absurd. For example, this left side image, which is predicted like panda, which is correct, upon adding the same image, I mean, for us, we have no problem recognizing the gibbon. But the same model which has predicted, after adding, predicts it as a gibbon with high confidence, right? This is something serious about their stability. Small added perturbation. It's not random. It's a structured perturbation aimed to fool the CNNs. So the CNN gets fooled actually. So these are called adversarial perturbations, adversarial noise, right? So we studied the models against these adversarial perturbations. This is an important issue because when you know such a vulnerability is there with models, we cannot really deploy reliably models, right from a simple access granting, maybe it is a defense or banking application, maybe it's a very sophisticated medical diagnosis being performed, without really understanding their stability, their vulnerability, we cannot reliably deploy these models, right? Let's not go there to autonomous navigation without solving these things. So what we wanted to do is there was a lot happening during simultaneously also when we picked up this particular topic. So universal perturbations are something which are even more dangerous because if you see this slide, this noise shown is particularly crafted for this input, and then they removed one more degrees of freedom by finding or by constructing a particular noise which is universal. That means you can add this noise to any of the natural image, and the resulting image can fool the chosen CNN, which is driving the recognition in the target model, right? So not only that, it gets transferred. That means you don't need to know the target model or the data set on which the target model is trained. Things get more and more dangerous. More and more degrees of freedom are broken by the attackers. You can think of it as an attack happening on the deployed model where they're trying to fool it by adding this additive noise to the input images. So this is a serious issue. So we wanted to really understand, yes, they are performing really well, but they're easily breakable at that moment. I mean, I'm talking about the CNNs performing recognition. So yeah, this is what is universal adversarial perturbation means. So you add, delta is the perturbation. When you add a very small perturbation, so you can see it is LP norm limited. For example, if the image is 0 to 256, you can only add a maximum noise which is of 10, right? So you cannot exceed. Only then you can call it. Of course, it is arguable, but the communities kind of started to work with L infinity of 10. Yeah, so this is how the attackers construct a delta, a universal perturbation. Upon adding the output of the CNN, k of x plus delta is no more same as k of x. Right? This is the optimization behind the crafting of such an universal perturbations. So at the time, it was it's a discovery that kind of surprised all the people that are in vision that are performing. So only one catch was basically you need to have access to the data, right? The training data was required, although it is universal. The optimization is dependent on the input data X for alpha to be constructed. So there was one safety, because if you don't give out your data, maybe you can think that you're not very vulnerable. But that's what we wanted to really investigate. So if we can corrupt the features that are responsible for these remarkable performance, maybe the representation gets corrupted and the inference goes to wrong, right? We wanted to perform this without having access to the input data. So we wanted to investigate data-free objectives so that we can really understand whether we are safe without releasing our data. So this is our first work in this robustness analysis, and we constructed data-free objectives to construct perturbations, universal perturbations, and we showed these are, if not greater, they are equal, almost equal to the vulnerability caused by the data-driven perturbations. Right. What we do simply here is basically we start with a random delta. I'm talking in a simple CNN recognition context. You have the trained CNN in your laboratory, and now I start with a simple delta, which is a random noise, and then try to maximize the response of the CNN for this delta, right? I keep on modifying my delta so that it gives maximal activation at all the layers. Remember, what we're trying to do is we're trying to corrupt the representations. We wanted to see how stable the representations are. For a small noise that I am adding, is the response of these representations is small, or as opposed to the belief, is it going to be too much change in the representations? If it is too much, it's going to corrupt the representation and wrong inference is going to be resulted. So we did this and we showed very significant fooling rates. Fooling rates means this is the percentage of times the CNN gets fooled upon adding this noise. If you see, when we know the diagonal numbers are white box attack, that means we know the target model, whether it is AlexNet, whether it is VGG, whether it is GoogleNet, something like that. So if we know that, yes, we can craft very strong attacks. And if we don't know them, for example, if I construct with my model, which is VGG, and attack different model, GoogleNet, it's less than 38%, right? Of course, this 38 may not be small for a model that is deployed commercially. It is still dangerous. That means almost 40 times I'm able to fool by adding this small noise, right? If I know the model itself, it's as strong as, sometimes 81, sometimes 43, right? So this is the vulnerability we brought out. We revealed that the models need not have the access to the actual training data, right? Not only for not only for the object recognition, but other computer vision tasks like semantic segmentation and depth estimation. We kind of generalized this data free objective and showed that the representations are not very strong, very stable. Pardon. Yeah. So we've shown on multiple applications that if you have any prior, right? You may not have the access to the data set or samples of the data set, but if you know any prior, for example, the mean of the distribution or some examples themselves, like a few shot, right? That also can be utilized effectively in this framework to craft more and more dangerous attacks.
Konda, can you wrap up soon because you're out of time?
Yes. I just have only one more. Yeah. So after finding out that there are a lot of vulnerabilities, we just wanted to capture them. So instead of saying it is possible to craft an attack, can we kind of quantitatively come up with some kind of a metric, or can we even come up with a subspace of such things? Obviously there is not one single UAP, but there might be a huge number of them. So in this work, which is our CVPR 2018 work, we tried to capture that subspace in a GAN framework, where our generator tries to give such UAPs, right? So it was also very surprising, very simple objectives like fooling. Fooling means trying to reduce the confidence for the ground truth label. Such a simple loss, and with added diversity coefficient in the whole loss, we were able to see number of variety of such UAPs possible, right? So that was one of the very surprising to me, because I was wondering, if you see the revolutionary work of UAP that was presented in CVPR 2017, there was no variety. People thought that maybe there is a local minima where these UAPs are coming from, and however random initializations you try to run, it was just landing on that particular local minima. But with our GAN framework, we could see variety of patterns coming in, and we also saw, they were all continuous.
Konda, please finish it by one.
Yeah. So that was all. We studied different techniques of different things, different aspects of this CNN learned representations, And yeah, thanks for giving me this great opportunity. Yeah, in conclusion, basically, this was very um, novel things we've done, and there are a lot of issues we haven't fixed. There are a lot of things we are doing now. I hope I will be able to communicate if you have any doubts about how we can, take it forward, etc., etc. Yeah, sorry if I have taken and broken the time agreement. Yeah.
Well, thank you for a nice presentation from Kunja. I just invite one question from the audience because we are running short of time.
Sure.
Any question from the audience? Well, it's none from them. So thank you again, Kunja, for nice presentation. Okay.
Thank you.
Forget about the time overflow. Okay. Fine.
Thank you.
Okay, we are waiting for the next one. Thank you. Bye.
Bye.
Is Bodri there?
Hi, I'm here.
Okay. So could you can you share your content?
Yeah, I have already said. Is it visible?
Okay. Yes, sure. So please go ahead. 25 minutes time.
Yeah.
Please stick to that. Thank you.
Okay. Thank you. Thank you, IUPRAI, giving me this award, and also thank you to the selection committee, and also special thanks to my guide who support me a lot. So today I will present this like towards understanding vision and language systems. That is, with the help of controllability, uncertainty method, and the interpretability for the vision and language system, like visual question answering task and visual question generation task. Most probably, I will discuss about these two tasks. So, vision and language system. So it's a multimodal conversation system which includes the vision modality and the language modality to have a meaningful conversation. So what is vision modality? It's just a mobile phone and any camera device. You can take a picture and that, and the text modality is something like a keyboard, and they want to communicate with each other. So language system. So the first vision and language system is visual question answering, like given an image and you need to ask a question based upon this image, the model need to give an answer, like where is the plane going? The model will answer it's going to home or somewhere, some city place or something. So now the next challenge is, can I generate a question given an image? Can I generate a meaningful, engaging question? Yeah, the model are there, and that is known as visual question generating system. And the third sort of modality is like, given a question, can I generate a similar type of question? Yeah, that is also possible. And given a image, can I have a meaningful conversation? It's not a single question answering, it's a multiple rounds of question answering. That is known as visual dialogue. In my PhD work, I have worked on this food task, and I will discuss more detail on VQA task, and I will go overview on VQG and PQG and VD task. So my thesis tree that is basically deals with the computer vision stuff and the natural language processing stuff with the help of machine learning. So I built up my vision and language system based upon these three tools. The first branch of my tree is a controllability branch, which takes care of differential attention network, and the second is multimodal differential attention network, that is, and the third is paraphrase question generation. And the second branch of my tree is giving the uncertainty based method, that is an uncertainty class activation map. And the second And the second leaf of this branch is multi-queue, uncertainty-based multi-queue method that gives a fruit of WCV, and the probabilistic method for visual dialogue. And the third branch of my tree, it tells about explainability or interpretability of a model, and which deals with a bar network. And the second is for collaborative model network, and the third is multimodal attention network. So, these papers in my thesis is included, that is differential attention network for VQA and multimodal network. And the uncertainty branch, these are the papers I will discuss more detailedly. Basically about the first paper for all three branch and the interpretability branch also. So the first question to, can machine able to answer? Yes, machine can able to answer. So that is what the machine can able to answer. That is known as visual question answering task. So what are the different challenges in this task? So you can see in this image which game is being played. So whenever I ask this question, your focus is going to this place. When I ask the second question, what type of surface is this? Exactly, you are looking into this place. So as a human, we can look exactly correct places, but machine can able to look or not, we'll see. Do the machine and deep network look at same regions? This is the basic intuition. The the answer is not exactly. The human is looking some different places, exactly the places, but machine is looking some different random places. You can see what are they doing. They are eating. Human is exactly focused on this part, whereas machine, the basic network that is known as a stack attention network. So in CVPR 2016, they focus on here and there, exactly not on the plate. And another model in that CVP paper only, so that focus on little bit, but not exactly as human looks like. So our challenge is, can deep network attend to the similar regions as human looks? Yeah, we can solve. From this challenge, we propose one method known as the example based method. What is the exemplar based method? It's derived from that child psychology, and like in when you saw when a child learns something, let's say a child learns a ball and a bottle, she or he already learned ball or a bottle. When you bring a glass in front of him or her, so what he will do, he will compare this new target object with all his past history. Let's say this glass, he will compare with bottle, and glass with ball. So she already learned about ball and bottle. So he will tell that, okay, this glass is similar to bottle. The structure of a glass is similar to the structure of bottle. So it will classify as a bottle. But as a parent, we are giving supervision. It's not a bottle, it's a glass. So just to give a end supervision to the child, he already know the basic structure, what are the structure of a glass, and how he can compare all these things. He or she knows that. So from that analogy, we develop a algorithm that is not an exemplar based theory. So we have a supporting example like bottle and an opposing example like ball. So whenever a new target is coming, so we'll compare this target with supporting example and target with opposing example. We will bring this target example close to supporting one and far away from opposing one. So initially you can see what color are the cows. It will give the black and white because this move. highlighted. This is a black part is there. Later on, you can see when you take with the help of the supporting and opposing, you can see the brown part of supporting part is more highlighted. That's why, and the black part is less highlighted as compared to here. And you can see the brown part is more highlighted as compared to this one, basic network. So that's why it classify as a brown and white. This is the algorithm. So the model we have developed, it's a very simple. We pass target image through a CNN module and a target question to a sequential network, that is LSTM. Then we combine, we got a feature, then we combine this feature in the attention domain, and we bring this target one close to supporting one and far away from opposing one. How will I this can be using uh, loss, that is a triplet loss, which can able to do that job, bringing target close to supporting and far away from opposing. And the end supervision part, we have a supervision based model, that is a classification loss. We have a ground truth for that, so we can improve the supervision part using classification loss. This is the basic method for visual question answering, and that improve a lot in a different space. So we used both the triplet loss and the cross entropy loss, that is basic cross entropy loss, and the triplet loss to design this model. So the data set is that VQA data set. You can see that questionnaire, how many aeroplanes are there, what color are the waves, and what are the zebras on the road, and these are the human attention. You can see, does the painting related to the location? Yes, you can see how hard the question is. So human is giving here. So this is the location related attention network. So the main problem is we don't have a human supervision for entire data set. We have a very limited human supervision. That's the main challenge in any of attention network, where there is no ground truth available for the attention. So how will you improve that? So in our method, the attention, you can see that the attention is improve in attention is measured using the rank correlation method, and you can see the improve in rank correlation base compared to the baseline method is our another method is the DCN method, differential context network, differential attention network. Both have improved in rank correlation. You can see the more exact and accurate map are compared to the human, it's improved in attention from the baseline method. Result in rank correlation method, and this is the state apart result in VQA in 2018. So we are in the state apart for VQA1 dataset and 2018. So we also experiment we also analyze our method with the help of, if I consider only the supporting example, or if I will consider only supporting and only the opposing example, how impact to our model. You can see if I will take only supporting without any opposing example, so how impact to our method. You can see both supporting contrasting, you can see the attention, and it is an attention. This is for a attention reason, human attention, reference attention map, supporting attention, contrasting attention, and we show the differential attention network. And here it will give the complete picture how attention is moving, how attention is improved as compared to reference attention. This gives a CVPR 2018 paper. And the second question coming to the mind, can question? Yes, machine can generate a question. That gives a paper in Yemen. It's a similar type of network, like we combine our target image along with caption, then we do a mixer model, then the mixer mixer representation is given to a decoder, and decoder is able to generate a meaningful question. So we use a similar type of example or technique as we have implemented in visual question answering. So I'm not going more detail on that. So these are the data set. You can see that the visual question answering a more challenging data set as compared to VQA data set. So it's a very challenge to improve model performance like blue score and meteor score and the meaningful generating. It's a very challenge to generate a meaningful question. So the second coming to the picture is UMNLP 2018. And the third type of exemplar based technique we propose, can machine able to generate a question? Yes, MDN is there. So can machine able to generate a similar type of question? Yes, that is a paraphrase generation. The problem with the existing method, you can see that word by word comparison. There is no meaning, the sentence based comparison or meaningful comparison was there. So we propose a method to provide a sentence level improvement that is known as a discriminator, pairwise discriminator based method to improve meaningful communication, meaningful paraphrase question generation. Our method, the important criteria is we proposed a pairwise discriminator method, and the next method is we have shared both encoder and the discriminator. So till now, whatever the GAN based architecture, the discriminator people are not using that. We have used this discriminator as an encoder. So we have improved encoder performance by training discriminator. And this is the first branch of machine able to confident on answer prediction. Yes, machine can able to confident on that. You can see that what are the game they playing. You can see the baseline method, the state apart method at that time can give a confidence score like 0.27, and the 10 is 0.19. You can see in this case napkin and paper, it's very confusing. So adding bit a small bit of noise into that, the answer may flip. Or the napkin may go to the paper and paper go to the napkin. So in order to avoid this, we can see we proposed a uncertainty or the probabilistic method based upon uncertainty theory to improve the confidence score. What is that? Very simple. Given an input to a model, we predict. From this logic, we measure a uncertainty score using uncertainty network. That uncertainty score, from that uncertainty, we sample a Gaussian noise of variance, whatever the predicted uncertainty, we add to the logic, and after that we calculate a loss based upon that. You can see the logic score and the noise value based upon this uncertainty score, and we obtain a distorted logic. From distorted logic and the ground truth logic, we find a cross entropy loss that is known as uncertainty loss. Then we train our network, both this network and the model network, and obtain that more robust answer prediction and more confident network. Given input image and the query question passed to a sequential model, we pass through a attention network finally to a classifier. Finally, a classifier, we predict a logic value and also predict an uncertainty score. From cross entropy, we obtain a gradient with respect to attention. Also from uncertainty loss, we obtain a gradient with respect to this attention. The objective of this attention, where it is less confidence, we want to increase. In this region, the model is less confidence, so give a more value to that. If it is a high confidence, means if it is more certain, so emphasize the certain values, and where it is less certain, de-emphasize the certain value. You get a certainty. So from this uncertainty, we flip that uncertainty and multiply with this attention region. Where it is uncertain, give a less value. Where it is certain, give more value. After that, we multiply these two and pass through this attention layer. So finally, we try to visualize this attention layer. We can see it's exactly looking in the center of the train. So this is what our complete network architecture, the classifier. This is the uncertainty network. This is the logic value. Then from that network, we predict a variance, as I explained earlier. Then we obtain an uncertainty loss. Also, you obtain a cross entropy loss. From that, we obtain a gradient. Then we reverse uncertainty gradient, multiply with the this cross entropy gradient. Then finally, you obtain our activation map, uncertainty activation. How our map is evolve. Only the question, if you give a only question based uncertainty map, only question based uncertainty map, only image based uncertainty map, when you combine both image and question, how this map is evolved, we have shown this one. And here we have we visualize our uncertainty score along with the uncertainty map, where it is highlighting. Since we have proposed a probabilistic method, so we have sampled our network, and each time where it is focusing, we have visualized this one. We have visualized another example here. This is more towards uncertainty method, and we have shown we have shown our network, means evolution analysis our network, how our network is evolved, and compared to the state of art method in VQA1 dataset, and also we have compared method with VQA2 dataset. So for each, we sample few example, and we have shown that what about incorrect prediction and high uncertainty, and the correct correct prediction, and it is a low uncertainty. Incorrect prediction, low uncertainty. Incorrect prediction, high uncertainty. Where we have shown the baseline uncertainties, and our finally it's a predicted a gradient certainty for attention, and A for aleatoric gradient certainty for attention. So we have shown all detail in this. And this gives fruits and ICV 2019. The second part of this branch is how confident on generating question. Yes, you can generate a question by combining these different cues, and you measure how uncertainty in the combine, and how will you improve these certainty score in this combination. And finally, we combine this individual question generator using a moderator, which moderate the value, which one is giving how much importance in our net, and finally we generate a meaningful question. You can see, are the cows are being milked, as compared to the individual score, where do this animal lives. This is a basic question type of thing, but when you generate a question like, are the cows being milked, it's a more human oriented. Human can ask such type of question, not like a machine. So this is a bit complicated network, and we combine each architecture, CNN with place network, CNN with caption, CNN with tag LSTN, finally a fusion network, and the moderator network, which will moderate then the final output is given to a decoder. So in this case, we have used uncertainty based method for a generative model, and previously we were used for the discriminated model in answer. We use a generative model. The next part of that, can machine confidence on both generating question and answering question? Yes. So you can see at the multiple round of questions are there. Then we use a very uh, VA-based method to generate a question. From that question, we obtain a answer that how confidence in our model for generating question as well as predicting answer. So this is for the visual dialogue and detail. I'm not discussing detail right now because for the time limit, I'm not discussing detail. Yeah. So you can see the caption is given for the image. Caption is given. First question and its ground truth answer, then prediction score for no, prediction score for yes. Is this in the prediction score you can see here, and the baseline model that is epistemic uncertainty based method, it's giving no score is here and yes score is here. Finally, you see the PUDN method, the probabilistic method. You can see the difference between yes and no is too high as compared to the baseline method and as compared to the epistemic one. Epistemic is nothing but a sampled version of the model. The patent recognition 2020. So now, can machine explain the answer? Whatever I have predicted, okay, I have matched the confidence of the answer. Can I explain my answer? Yeah, I can explain my answer. So how can I explain? Can I use those to improve my attention? Yes, I can. I can use them to use my attention as well. So we combine this question representation and image representation using attention network and predict that answer. From that, we obtain a great game score and also a attention. We have an attention map. We obtain a great game map from the predicted answer. Then we use a discriminator. We use a great game, whatever explanation as a real and the predicted attention as a fake, and try to use them as like adversarial loss. So each time, whatever my prediction based upon, I generate a great cam and I will try to improve my attention. If my attention improving, my prediction is also improve. If my prediction will improve, my grade cam is improving. So it's a looping type of thing. If attention improve, prediction will improve. From prediction, I will improve my explanation like grade cam. So this is the architecture I have we have proposed, like a discriminator based architecture. So which use each map is use a one discriminator. There are 196 maps, so 196 discriminator. So which each discriminator same logic. Grade cam is a real and attention is a fake, and try to improve that. So using this, we have visualized both our attention, also our explanation. Yeah. Hello.
Please wrap up within 2 minutes. Right? The time is over.
Sure.
Okay.
Sure. So this is for the visualization of GradCam. These are the evolution analysis to find both rank correlation and accuracy, and these are the state of result, both VQ and VQ2. And I have shown how these are warmed up for each time, how my attention is improving for epoch 10, epoch 50, epoch 100, and I have shown that. So this is for the visual dialogue data set. I have did that. So the PAN model, and second is my machine explainer robust. Yes. So we proposed a collaborative defender module to generate a robust one. So we use a discriminator model with answer and combining answer and explanation and predicted answer and explanation and ground truth answer and explanation. Improve both explanation, attention, and my answer. So this is the results, and this will give a collaborative defended model. And the last part of my thesis is can machine provide a self-explanation and can I improve my attention without any supervision? Since I don't have a supervision, I use a self-explanation method to improve my attention. So we proposed a network by masking each reason in the image and finally predicted attention score. Finally predicted answer score. Based upon that answer, we measure how explanation is obtained, and similarly we mask in image, we mask in question, and try to the mask based on the image masking, based upon the question masking, we obtain an explanation. Using that explanation, we improve both image attention and question attention. So here just I have shown that question attention, how the original attention, how attention after masking, we got our result. So this is my file slide. Thank you.
Well, Bodhi, thank you for nice presentation, and I think most of the part is very much accessible. I request any question if there is from the audience.
Hello.
No? Yes, please. Okay. There's no question so far. I don't see anything in the chat also. So I have a question, right, Bodhi? Suppose we take the simple case of answering the question, okay, and or basically generating the questions. Okay, that is second thing is generating the question. Given the same image, okay, even the same image, many different people will generate different questions.
Yeah.
Right, because their attention is something to different objects or different activity. But for example, the image you have shown and generating the question, what the girl is eating. Why is I may ask the actually the what the girl is doing. Okay, your attention was on the object itself, what it is eating, and my attention is on the other hand is attention to the activity, the what the girl is doing.
Right. Right.
So there are many different questions. This is a very simple example. Many complicated example, complex image will generate multiple such questions. Now, how to compare your predicted or generated questions with the ground truth, because there are multiple ground truths. Anyone matching with anyone is fine, or
yeah. So nice question. So yeah, actually I'm comparing with the HAT dataset, the human attention dataset. In the dataset, there are very few example, let's say 1,000 example, and their answer for a given image and a particular question, they have predicted that attention map, they have annotated the attention map for particular answer. Means let's say you are asking like in HAT dataset, there are questions like what the girl is eating. So he's eating chocolate. So based upon that answer, the attention map is annotated. So that is there in the dataset. So I'm comparing that attention only. I'm not comparing the other attention.
Okay. Secondly, all these actions or these ground truths, not only your case, many of the machine learning or the object detection, object understanding, whatever it is, even the classical pattern elements.
Yeah.
All these ground-truths are generated by human beings.
Yeah.
And this is generated by human beings. So far, we have discussed that is the correct ideal answer, correct information as the ground truth.
Yeah.
There might be the person who is the ground truth, he or she may make a mistake.
Yes, yeah, right. Yeah.
But we always take the ground truth is the quote unquote the Bible for the answer what we are going to predict, right?
Yeah.
So, have you ever thought about incorporating some kind of incorrectness in the ground truth into such elaborate work?
Yeah, so there is no correct answer for that. So actually, there are always a human error. So what people are doing, so when they are trying to create this data set, so they ask for person for same question and image. They ask for 8%, and they are trying to collect more means let's say 5% are giving a same answer, so they are and they mention that this is the most probable ground truth, and they have mentioned all 8 answer, but finally we train our module with the maximum means who means maximum number of people has answered something, so we program we train our module like that way. But in our data set there are all 8 options are available, means okay, 8 annotator has given these answers. So it's up to us which one we will decide. So there are some errors are there. I'm truly agree with this.
Okay, thank you for clarification. Thank you for presentation also.
Thank you.
So, well, let's stop here. I conclude the session and over to Parag. Thank you. Bye.
Thank you. Am I audible?
Yeah.
Uh, Thank you to both the award winners for their very nice talks. Thank you, Professor Chandra, for coordinating the session, chairing the session, and for the questions. We are a bit over time, but we will, since we are in lunch, so I would request all of you to get a working lunch and to be back at 2 p.m. Where when we will start our plenary talk for the day by Lihi Zellek Manav. So please be back at 2 p.m. For what promises to be a very interesting plenary talk. And I'll see all of you there. Bye-bye. So we'll resume at 2 p.m. sharp. Thank you.
Yeah. Thank you, Parag. Thank you. Thank you all.
Thank you.
Hello.
Good afternoon,
Good
Parag.
afternoon. Hi.
Hi.
We will start at 2 p.m. Lee is already here. She's joined.
Lee is here?
Yes, she is.
Okay. Is she?
Hello, Lee. Are you around? Can you turn on your video?
Is Lee around? Then we can.
Yeah, I just messaged her. Yeah, she's here.
Yeah.
I'm here.
Hi, this is Shantanu. I shall be coordinating your session.
Hi, nice to meet you.
Nice meeting you.
So this
So it's, this is at what time? It is at you are in where in Israel right now?
very good.
Yeah, sorry.
Lee, your voice is a bit unclear and it's breaking up.
Yeah, there is some problem with your voice.
Let's see.
It's fine now. It was breaking up earlier.
Okay, so maybe I need to make sure I get close to the microphone.
Yeah.
Yeah, we shall start at 2 o'clock.
Yeah, a few more minutes.
I think this is the first presence in ICVGIP conference. So it's a conference, it's an Indian conference on computer vision, graphics, and image processing. And it started way back in '98.
Wow.
And this is, we do it every 2 years. And so it's continuing for 22 years.
Wow, so it's 22 years. That's impressive. Were you there at the first one?
Yeah, yeah. I was, I think, organizing chair. I was possibly some organizing chair of the first one.
Cool. I think my first paper is from 1998.
Okay, good. So it's almost aligned with your research career.
Yeah. I just want to say I'm in your generation.
Yeah.
We were there in 1998 where conferences we had just a few people.
Yeah, in fact, that was in Delhi. I think it was just following ICCV. ICCV
Hi,
was
Lehi.
there in Bombay.
Hey, PJ, good to see you.
So PG and I was talking about first ICVGIP.
Agreeing to our request. Can you hear me?
Yes, I hear you well.
Hello.
There's some problem with your network, I think. Just Yeah. Now I think you're visible.
Parag?
Now your voice is audible. Yeah.
Yes.
Yeah. Hi, Lihi. Thanks for accepting our invitation. Can you hear me?
Yes, it's my pleasure. But you know, this invitation doesn't mean that when we're back to real conference, you need to invite me to a real one. I want
Yeah,
to
yeah.
talk for
Yes.
See,
Definitely.
sure, we
You
shall
are
be
all.
having the
Yeah. So we have
look
had,
forward.
yeah, we have had Shmuel speak. We have had Abhan, Shai speak at this. So we'll
Shmuel
be
was,
glad to have you next.
in fact, Shmuel was plenary the first, 98.
Yeah.
I think last time I was in India was maybe 2010.
Yeah, you had
Or
come. You had come to the Hyderabad event, right?
yes,
Yeah.
and that's it. I haven't been back.
Okay, so I think it is time now. We can start. Right? Welcome to the post-lunch session for day 3 of ICVGIP 2020. We are ready to start our plenary talk for the day. So let me hand over to Professor Shantanu Chaudhary for taking this session ahead. Over to you, sir.
Thank you, Parag. Good afternoon. Let me welcome all the delegates for this plenary talk. We are very fortunate to have Professor Lee Zelling Manor as our plenary speaker. She is currently an associate professor in the Faculty of Electrical Engineering at the Technion and the head of Alibaba Demo Academy Machine Intelligence Israel Lab. Professor Lee holds a PhD in computer science from the Weizmann Institute of Science and a BSc in mechanical engineering from Technion. It's a very interesting combination. Her main area of expertise and interest is computer vision. She has done extensive community contribution, computer vision, program chair of CVPR 16, associate editor at Transaction PAMI, served multiple times as area chairs at CVPR, ECCV, and was on the award committee of ACCV 18 and CVPR 18, CVPR 19. Looking forward, she will serve as general chair of CVPR 21 and ECCV 22, and then program chair of ICCV 25. So we really have an extremely distinguished speaker today. And she will also talk about a very interesting aspect of computer vision, how computer vision techniques can be turned into products. In fact, her interest in this area of use of computer vision for a variety of applications, and she has actually contributed in that area, and that's a very interesting aspect that we love to know. Professor Lee, please take over and start your talk. You can share your slides.
Okay. Thank you for the very nice introduction. Let me share my slide. Okay. Is it working? Did I succeed?
It's visible. And you have about an hour. Please go ahead.
Okay, cool. So, as was shared, Santu shared in the introduction, I wear two hats. I'm a professor at the Technion, but over the last 2 years, I've been leading Alibaba Israel R&D Center. And notice that I call it R&D Center rather than a research lab, because we don't do just research. We actually go and productize our research. And I thought this is a very interesting aspect. How do you go from research to practice? It's not trivial. And I think the first day we had a keynote talking about careers in industry. And now I'm kind of bridging the gap between the two. So I thought I'll share my perspective. I'll share this story, and not all of this is my work. Not all of this is published work. I thought it's what I thought would be nice for us to hear today. So let me start. So as I said, my personal story started mostly in academia. I was doing research at amazing universities across different geographical locations. So I started in Israel. I'm 100% Israeli, and did my PhD at the Weizmann Institute. And then I moved on to sunny California and did my postdoc in Caltech. And then back to Israel, where I got a position at the Technion, which was indeed where I did my bachelor degree. So as part of the Technion, I couldn't sit still, and I took the time to go to New York and spend 2 years in Cornell Tech, which is a joint initiative by Cornell and the Technion. And there the focus is on entrepreneurship and bridging the gaps between research and industry. So this was I was very curious about this, and this is why I spent 2 years in Cornell Tech, and then was back to the Technion. So as I said, what was mutual to all those places is the wonderful research people and that do amazing work continuously. It's all around you, and you can always go and hear great talks and see great articles coming out and great people working. But I've also been very fascinated by the real world. And the problems it presents to us. And somehow, even though we have collaborations with industry, I didn't feel that I'm going all the way through to experience what it is like to deploy a real product. So 2 years ago, I embarked on a new journey, and I joined Alibaba Group to lead the establishment of its R&D center in Israel. And this adventure really introduced me to new culture that I was not familiar with. So I shared with you the part of my journey that connects to this plenary talk. And let me move on and tell you what I'm going to actually share with you today, and how I'll actually talk about this gap between good research and awesome real products. So I will reflect on this gap and try to give you examples through the way we see it in Alibaba Israel. But before I begin, I'll give you a quick glance at the Alibaba ecosystem. So I'm not sure how many of you are familiar with Alibaba, and because I think the main business is in China. So let me just give a brief overview, and you see in this slide the summary of the Alibaba digital economy. So if you see that at the bottom, there's Alibaba Cloud. Alibaba Cloud is actually the third biggest in the world, according to Gartner. And this is the infrastructure that everything lies on top. And on top of that, there is the payment system, Alipay by Ant Financial, and then marketing and services and data management platform, Alimama, and the logistics by Cainiao. All of these are very big business units. And then on top of all of that, there are all those vertical directions. So the main business is the retail. And you with Taobao, which is which is the biggest retail platform within China, but there's also Tmall, where international brands can sell their merchandise in China. You might be familiar with AliExpress, which is the opposite direction. So for AliExpress is a platform people international use to buy products from China. And there are many other ones that maybe are more specific to Malaysia or other countries. There's also wholesale commerce, Alibaba.com. Then beyond retail, you can go on and into other domains. So Alibaba has also Fli, which is the travel services, Youku, which is the entertainment, the alternative to YouTube in China, DingTalk, the platform we use for everything we need to do in office. You can think of it as WhatsApp and Slack combined. AMAP, which is for navigation, etc. So I will not go over everything, but just want to give you a gist of how huge this ecosystem is and how many opportunities there are for us in Alibaba. My lab belongs to Alibaba Cloud because we are the infrastructure. We provide the AI, we provide the technologies that take Alibaba and keep it a high technology company. And actually, we are part of an organization called, within Alibaba Cloud, called Damo Academy. And you see the Damo Academy centers in 7 locations in the world. The biggest ones are in Hangzhou and Beijing in China, but there's also a team in Singapore, in Israel, and Seattle. And Damo is a research institute, but the focus is to actually bridge this gap between research and product. And the one in Israel is focused on computer vision. There are many technologies coming out of Damo, but just to give you a glimpse into 2 of them. So on the left, you see here an autonomous vehicle from Damo Labs, and this is for last mile delivery, and it can last for over 100 kilometers with and deliver over 500 parcels. And it's already being used in practice. And then another very different direction is health. Outbreak took the world by surprise. The Damo people very quickly went on board and developed a system to diagnose COVID in 20 seconds with 96% accuracy based on development that was required for the emergency situation back in March. So, and there's a lot more, like language analysis, audio analysis. I will not go into this. I just gave these 2 cool examples from my colleagues. But what is mutual to all of that is that we're talking about real solutions. And today, specifically, I will talk I'll tell you what happens when you develop a real application with real users, and then you face real AI challenges. And the difference is that you cannot assume some challenges have been solved by some other algorithm. You just have to solve everything. You must address all the constraints to be able to not just enjoy the research, but also make it profitable. So in Damo, our slogan is doing research for profit and fun, but both are important. And sometimes we don't care about profitability. And as a company, we do care about revenues, but let's take a broader perspective. Profit is one way to measure the value you bring to your users and customers. So people pay for products that are useful. People pay for services that create value for them. And through measuring that, you know that your algorithms are good. You know that your algorithms are doing their job. So I really love that aspect and of connecting this down-to-earth measure, materialistic measure, to evaluate the quality of my research. To make things more concrete, I chose today to center my talk around one of the coolest products out there, Cloud Drive apps. So I know people really like to talk about things that the common person might think are cool, like autonomous driving or virtual characters. But I chose to talk about drive apps because there are lots of drive apps out there, and you might be using one yourself. Maybe if you're in China, you'll be using Baidu Wangpan or Tencent Huiyun. And if you're in the West, maybe you'll be using Google Drive or Apple iCloud or Dropbox or Box, and there are plenty others. So millions of people are using such apps. And this is one of the reasons I chose to look at things through that specific, this specific product. I love the fact that it is used by millions of people. I love the fact that it is the palm of your hands. I love the fact that it's in your mobile phone. And this way, it's almost like making AI a commodity. So today, well, on one hand, we see people afraid of AI. On the other hand, it is not. Actually, many people AI. And in drive apps, we do get to enjoy it, and we do get to reach massive numbers of people. So I think that's what makes drive apps cool. And I want to tell you my story about through this. So what drive apps, just to make sure we're in case we're not completely aligned, and in case you've never used Dropbox or iCloud or one of those apps. So let me give you a concrete visualization. So in drive apps, a user can store, synchronize, and stream and share their files. So let's look at an example. So for example, I'll focus on the photos because we're a computer vision conference, right? So let's see what is the beauty of a drive app and what the extra benefits it gives you. So for example, you can get very nice visual of your photos. So it's not just a lot of files, you get the best photos highlighted for you, and the display is kind of appealing so you can enjoy browsing your photos. And then you can also find your photos. So you can get your photos organized to you. You see here on the right, automatically curated albums for various scenes that could be interesting for you. So maybe hiking or water or flowers, and these are automatically created and organize your photos. You can also get them organized by location, and you can also search your photos. And we'll talk about this later today. And then the last bit, which is the one I really love, is this fun part where you can get, here I'm going to use some stickers that can automatically be generated for you from your own photos. So I really like all those aspects, and we'll talk about most of this today. Now, why do I link this drive app to Computer Vision Conference? Well, because there are multiple computer vision challenges hiding under the hood. So if you just take these few examples of the features that I presented here, you can already see that we need to solve so many image understanding and image manipulation tasks. So for example, if I want to just generate this nice display that shows the most beautiful photos highlighted, I need to have a way to evaluate how good an image is. What is its quality? Is it a static? I also need to be able to detect the salient object so I can crop it nicely. And then if there are some images that are duplicates, I need to identify similar images and remove the redundant ones. So all that just to create this display and to let you find effortlessly the images that you seek. I also need to be able to detect objects, to recognize objects, to search objects, to do multi-level classification, and so forth. And to make those creations, I would need to do pose estimation and face mapping and image stylization. And you can see almost everything in computer vision is hidden behind this application of a drive app. So I hope that by now we are convinced that drive apps are cool for computer vision people. And I will not go into all the tasks I mentioned here. I'll talk a little bit about multi-level classification, a little bit about image search, and a little bit about imaging thinking. So before we go, as I said, we go into the computer vision parts. One last slide where I talk a little bit high level. So I talked about the gap between research and product. So I cannot just talk about the cool research aspect and all the great computer vision tasks that we need to solve. I also have to explain to myself and to you, why are Drive apps relevant? Why are they important? And I have to do that from the business perspective, not just the research perspective. So from the business side, we see continuous growth in the amount of content people have. People take photos and videos in abundance, and they rely on those photos. They want to be able to share them with friends. They want to be able to share them and use them at work together with collaborators. So we need to address those needs. And today, actually, we can, because the connectivity to the cloud is becoming better and smoother. And finally, file manipulation is becoming intelligent and better because we have better device synchronization. So the technology is there to make Drive apps enjoyable and useful and effective. And also looking forward towards the future, you might want to go onto AliZilla website and look for personal computer, and a new product that has been announced recently by Alibaba Cloud that will be a gateway to the future of personal cloud. So this device will enable users to enjoy infinite computing. Not just today we enjoy in Drive apps infinite storage, but this device will provide also infinite computing, which is really going into the future. Okay, so let's dive in. So what is the gap between AI research and practice, the way I see it? So there are many gaps. I try to kind of organize them into three main categories. Maybe later on I'll mention a fourth one. So the first category that I will talk a lot about today is that in practice, we need to adhere to multiple objectives. We need to develop algorithms that have high accuracy, but also are fast and easy to train, that have low memory requirement, provide fast inference, and are user-friendly. We cannot just choose one objective. We have to comply to all. Another challenge in real world is data. So the data has its properties, and I will talk today just about one aspect, the imbalanced data. So I will leave it to later on. And then the last aspect is reproducibility. When you develop things in the real world, you must make sure that you have backward compatibility, consistency, and manage mission critical requirements. I will not talk about this today, but I just wanted to mention it here in this slide. So how do you handle this? How do you shrink the gap? First and foremost, you need a great team. So you must build a strong team, and it can't just be a team of researchers. You need to have also practitioner algorithm engineers, data engineers, software engineers, and product experts that all understand AI very well and can work with the researchers and make sure the algorithms that are developed are practical and effective. So you must have all those types of expertise, and otherwise you just can't make it work. So you have those people that thrive when they see an elegant optimization problem. You need to have the pragmatic algorithm experts that love making things work by finding methods that consistently lead to better outcomes. And then you also need those wizard software engineers that can make your models run fast on various devices, may it be a GPU, a CPU, or NPU on cloud or on a mobile device. And then when it comes to research, you need to identify the topics, the approaches, and the method that tackle the real world scenarios and objectives. So let's see how we do all of that through examples. So the first challenge, the first real world challenge I will look into is that of data. So what happens when you work with real-world data? And we'll do this through the problem of multi-label classification. So what is multi-label classification? The goal is to assign multiple labels to a single image. So for example, it could be just the object in the image. So let's take this image, for example, and I put the list of tags, right? Let's say that table of labels. I will use tags and labels intermittently. It means the same. So often we limit ourselves to a closed list because it makes it easier to define the data set and the accuracy evaluation measures. So here, for example, we see a rather complex image with multiple tags. So there is cake and candle and glass and orange and person, window and more. Nonetheless, out of the list of thousands of tags we want to be able to recognize in a Drive app, only a small fraction appears in this image. So this takes us to one of the key challenges in multi-label classification, which stems from the task definition. So because we have a large set of labels that we wish to recognize, then by construction, most of the images will have only a small fraction of the tags. So even though I said there are multiple tags, if you consider how many appear in this image out of this list, it's just a fraction. So this means that inherently, we will suffer from a huge class imbalance problem. So for each image, the number of negative labels is going to be much, much larger than the number of positive labels. And then when you think about Drive apps, often those rare labels are the ones that users search for the most, and therefore you can't make mistakes on those rare labels. So for example, while you might have very few photos of birthday cakes, like you see in this image, this could be one of the categories people search for the most. And then another problem that has been explained by studies is that there are relatively many labeling errors in in multi-label classification, probably because this labeling task is difficult for the human annotators. So for example, in this image, I labeled cat, but it's a mistake. There is no cat in this image. So we cannot fully trust our labels. So there is huge class imbalance. We have very few positive training samples per class, and we have frequent labeling mistakes. What does this mean? So if you go and try and train a network for multi-label classification, and you use the cross-entropy loss, which is the typical approach, what you see is this graph. So what am I showing you here? I'm showing you first the cross-entropy loss, which for positive images, or images with positive samples per label, is defined as the log probability, and for the negative samples, the log probability of 1 minus p, because we want to measure the confidence of the computed probability of the sampled image. And this graph here shows you the imbalance that we get between the negative and positive samples. So during training, the orange, which shows the probability of the negative samples, you see that we go to, but the probability, the positive samples doesn't go all the way to 1. And this gap is something that we want to close. So the probability doesn't converge when you use the cross-entropy loss, which is, as I said, the common solution. So what can we do? So first thing we try to do is go into the focal loss. You might be familiar with this one. It's a solution that has been proposed by Lin et al. For object detection. And in object detection, there's also class imbalance, because most of in object detection, you search over an image for an object, and most of the candidate windows do not have the object. Only a few have the object. So there's also class imbalance. So we tried it out. And I don't know, for some reason, I couldn't find works that use focal loss for multi-label classification. Maybe there are such works, I just didn't find them. But anyway, we've tried focal loss. And what is the difference between focal loss and cross-entropy loss? In terms of the equation, you see that it adds these terms that actually puts a focus on the positive samples. But when you try it in training, it is better than cross entropy, but still there's a gap. Now we try to understand what's going on, and we did that with the gradients of the loss. So here I show you the gradient of the loss of the negative samples, gradient of L minus. And I plot here in blue the gradients for the cross entropy, and in orange the gradient for the focal loss. And if you look at the gradients, it starts to tell you the story. So first of all, you see that both have continuous gradients, which is good for training. But then you see that the focal loss gives nonlinear attenuation. So you can see that for the negative samples, that there is an attenuation, their impact is lowered, while for positive sample, the focal loss increases their impact. And this is, again, to cover up for the imbalance. But what we see, this orange curve is not sufficient. So what we thought might be missing are three things. First, because of the high imbalance, we want to actually threshold and annihilate the samples that have very low probability. So samples that have very low probability are probably just easy samples, and we don't want them to impact the training too much. So we want actually to zero out things here. So this is one thing we wanted to do. The other thing we want to do is to look at this area, samples that get very, very high probability. And actually those samples are mostly mislabeled. We don't trust them. As I said, in multi-label classification, there are many labeling errors. So we want to, actually, we don't want to keep the high probability. Attenuate this region as well. So the curve we're looking for that attenuate the hard negative. And we were able to do this. So we defined a different loss function, which is called the asymmetric loss. It breaks the symmetry between the positive and negative samples, and it breaks the symmetry in two ways. So first, the focus parameter is different from the positive and negative samples. And this way we can really focus on the positive samples even more strongly. And then we also do another thing. Rather than just using the probability as is, we threshold it. We use a hard threshold to kill the easy negatives. And training with this loss closes the gap between positive and negative samples. So we were very happy about these results, and then we went out to test on data sets. And as you can expect, we got very nice results. Or as I said, as you can expect, because otherwise I wouldn't be presenting this, we got very nice results on the three biggest data sets, Pascal, MS Coco, and NewsWide. We got very good results. And here in each, our results is in red, showing you the map score. And this is the previous known state of the art. And you can see that each one is a different work. So we just compare to the best state of the art on each of those data sets. If you were to choose one of those methods, you will see bigger gaps between our solution and theirs. So we get state of the art on all those data sets. Also on open images, which is the only data set which is really huge. We get state of the art results. Here we compare to focal loss because actually I couldn't find results, published results by other work, but maybe there are out there and we need to find them out. So forgive me if I missed anyone. But you can see that we get this nice improvement using this asymmetric loss. And then, as I said, we're bridging the gap between research and practice. So the beauty of this, that it really works also in practice. This is not something that just we benchmark and get nice results on some data set. You can actually deploy this in your Drive app, and user can search for photos. And you see here an examples of my personal photos of flowers, all kinds of photos that are found automatically using this a model trained with this loss. So as you saw, the real world scenarios is complex since the data is challenging. And I believe that to overcome these challenges, one of our responsibilities in industry is to promote science in the way we can. So, and how can we do this? We can make those realistic scenarios accessible to the research community. And this way, everybody will enjoy the benefits of collaborative research on the real problems. So just stand behind words and not just talk about it. we actually started to go in that direction, and we released one realistic benchmark. So in CVPR 20, we ran the first retail vision workshop, and this year in CVPR 21, we will run it again. So as part of this workshop, Alibaba team released a benchmark called Ali Products, which consists of approximately 3 million images of roughly 50,000 different products. So it's a 50,000 classification problem. This workshop was also a joint venture with Trax, and they released another benchmark, which has images of densely packed products on shelves. So this is another realistic benchmark. And in 2021, we'll run this workshop again, and this time it's not just Trax and Alibaba, we also joined forces with Facebook, and we hope to broaden the scope of the workshop further into further retail domains. So stay tuned. Okay, so I talked a lot about data, and now let's talk about the other aspects of real world objectives, and this is efficient training and accurate models. So how do we do that? So how do we create models that can really be deployed? So the buzzword here is going to be efficiency. To deploy a model, it must be fast. It must have low memory. It must be with high accuracy. We have all those objectives that we need to comply to. And when talking about a drive app, this means it might need to run on a mobile phone and possibly not the best out there. So all those constraints we have to comply. And when we looked at that, we said, okay, we have all those setups. What can we do? How can we find an architecture for each device, for each task, for each scenario? And we try to approach this through neural architecture search. So neural architecture search methods are on the rise, and they already dominate computer vision challenges. And I want to make sure we can do this, but sorry, when you use neural architecture search, you want to make sure that actually the search is reasonable. And the reason I mentioned this is that in 2018, the search methods for architectures required thousands of GPU days to converge. So it essentially rendered them non-practical. So why we're here talking about this, because today they are. So just to give you a brief overview of what neural architecture search basics are. So the idea is to find valuable models, and you do that in two stages. First, you define a search space, which is the space of feasible architecture you're willing to look for, and then you design a search algorithm. So essentially, if you propose an algorithm and you have your model search algorithm to look for the right models. I will skip through the history. It's just there were many methods along the years that brought us into the point where, starting from the seminal work by Zap and AmoebaNet, by Real, both 2017 and later on in 2018 came up methods that reduced the search time to several days, like Bob, which is based on Bayesian optimization, and Darts, which is based on continuous relaxation, and brought us to the point that really it's just a few days to train. And then we went into this as well and proposed methods in 2019 and 2020 that reduced the search time to a few hours. So within a few hours, we can obtain great architecture, which seemed very exciting. So a little bit about what we do. One of the approaches we proposed, called XNAS, does the following thing. So it builds on Darts, and the idea is that, let's look at it from a 3-layer network. So we have an input network and marked by 0. And sorry, the input to the network is marked by 0. And then we go through along those arrows into feature maps. So 1, 2, 3 are feature maps. 3 is the output feature map. It's the final one. And architecture is going to be those edges that are marked with question marks. And on those edges, we apply operations. And the task is to find which operations we're going to place on each edge. Now, this is the micro architecture problem. We're going to design such micro cell, and then the final architecture will be a combination of those micro cells. But the micro search, how is it done? So you can think of it this way. So here we have this 3-layer network, and each colored arch marks a possible operation, and we need to choose if we want the blue operation, the green one, or the red one. This could be different, like max pooling or convolution of different types, etc. We need to choose between them. And in this paper called XNAS, the way we've done this is as follows. Take a zoom in into those two feature maps, 1 and 2. So each feature maps enter a set of forecasters, marked here by F1 to Fn. And the forecasters are associated with weights V and normalized weights U, marked here above. So weights V and U for each forecaster. And normalize those weights, which is important to overcome the parameterization bias. And then the weighted mixture of experts we create is the basis for the prediction for the output feature map. Finally, we use also, in addition, a gradual wipeout of the edges along the iteration, thus removing connections that become very weak. So this saves us computing time and leads to better architecture. So maybe to summarize, our idea is to use actually a novel mass optimizer that is based on learning with an exponentiated gradient step. And the key ideas are gradual wipeout of the edges. And we also provide for competition between the operations. So because we have those forecasters that always predict and we normalize them, we get normalized weights, then we have fair competition between the operations to get the final architecture. So going out of the details to see some results, you can see here in comparison to other architecture search methods. And you can see that in terms of the search days, the x-axis, and the accuracy, this is on C410. Here we want to be ideally at the bottom left corner, so fast search, low error. And you can see our algorithm is here at the bottom left corner. By the way, this is true for the time of publication. Probably by now there are better methods out there. And we are at a very good spot and we're very happy. But our conclusion was that indeed architecture search can find good models, but it was not sufficient because it ignored the inference, what happens at inference time. It only considered the search time, the training time. So this was not enough and we have to move on. And the next thing to look at is network pruning. So architecture search gave us a way to find good models, but we could not control the inference speed. So we had to do more. And the next tool is pruning. And we do the pruning. So a typical method is to take an unpruned network, prune a fraction of the model, fine-tune this model, and then get the final outcome. And you could iterate this process of pruning, and usually people iterate the pruning and the fine-tuning. In our case, we actually were able to avoid these iterations because we have a closed form solution for the pruning. So how did we do that? We actually found out that you can formulate a pruning problem exactly. So what you want to do is to get a pruned network and test its accuracy on some validation set. And you want to maximize this accuracy. You have to constrain your pruned network to belong to the space of pruned networks. And you want to put constraints of the inference time, the max number of flops. So at this point, we thought flops would be a good estimate of the computing budget. And going into details of this equation, but essentially you can take this accuracy and formulate it by the what is the loss, how the accuracy changes as you independence with the network weights. And you can decide using those variables B that are binary edge indicators to decide which edges in the network remain and which ones you want to kill and set to 0. And you can also, but you want to do this optimization while having this constraint that the number of flops per edge is bounded by the computing budget C that is given a priori. And can be solved in closed form by dynamic programming. It is actually an abstract problem, and if you're familiar with this term. So this is a nice formulation that can be applied for both sequential and non-sequential architectures. And now we can use it. So to show you some result, I'll skip this slide, sorry. I'll show you some results. So what do we see here? X-axis is the number of flops, Y-axis is the top one accuracy, and you can see that we can take very famous networks, very famous architecture that are known to be excellent, like Resonance 50. And we start the pruning, and as we prune, the number of flops is reduced, so we move to the left, but accuracy at the beginning is not harmed too much. And only when we really prune hard into 30% of the net of the size, we start to harm the accuracy. Same here for ResNet 1-on-1. And we actually also try this for mobile net, and we still get very nice improvement by this pruning. So this was one. So I talked about efficient training and efficient inference. But now let's add another constraint. We're in the real world, and complexity goes up and up. And we also need to care about the device we're going to be deployed on. So far we cared about search time, training time, good accuracy, inference time. We also want to care about deploying a certain device. And if we're thinking about the Drive app, we're going to need to deploy it on multiple different mobile devices, low-end devices, high-end devices, different operating systems, run also on cloud. And we're going to have many different computer vision tasks to solve. So to tackle all that, we also need to resort to other avenues, and we cannot afford to do the careful microsearch or the heavy network pruning. Just imagine the scale of this problem with all those devices and all those tasks. So we have no other choice but to keep those tools we are talking about so far, put them in our arsenal of tools, and then go and look for another solution that can scale up to multiple architectures. And to do that, we actually borrowed an idea from another team, from a paper published by MIT, by Tsai et al. From MIT at ICLR, called Once for All, or OFA in short. And the idea here is, look what happens when as the number of deployment platforms goes up. Search costs for traditional neural architecture search will just go linearly up, and the CO2 emissions will go up. Instead, we want something that remains constant. And their idea was very cool. So let's say we want to do text classification. And let's say we want to have an device is our target platform. And we want to have a target latency of 20 milliseconds. So what can we do? We build a priori for this high-end device. And now, during training, we train a super network, an accompanying accuracy predictor. So when we get as the requirements of, we're using this high-end device, we want 20 milliseconds, we go to the lookup table that predicts what's going to be the accuracy and runtime for this specific device, and we just pull out the sub-network from the supernet that gives us those target goals of latency on this specific device. So we pull out, but we had to a little bit refine suggestions by Tsai et al. So we also take our target data set, because we need to work on another data set from the one that SuperNet was trained on. And we apply some transfer learning and fine tuning using similar methods and tools that we have developed in-house. And finally, we get our high-end device specialized models for text classification that we can deploy. So this is how we can scale up. But sometimes we are also willing to do the opposite extreme. We still want to be a platform where we still want to for a specific device, but maybe if this device is a GPU and it's going to be on the cloud, it's going to be used by many, many users, and we're willing to put in a lot of effort into building an extremely strong backbone. So we've done that as well. And this is, we've developed an architecture called T-ResNet, and this is going to appear at WACV in 2-3 weeks. So go look for this work for T-ResNet. And it's a cool solution that integrates architecture design and implementation. And I think the authors of this paper, they like to call this implementation tricks or architecture tricks. I don't think these are tricks. I think these are the things that actually make deep learning algorithms work. And you can get then high inference throughput on GPU and high accuracy at the same time. But we'll be aware of the architecture, by being a device you're going to run on, this case, GPU. So you can actually go and look for doing such a design. In this table, what I show is for each of the contributions we have, like we have an idea that we need to do different anti-aliasing or optimize weak squeeze and excite layers. I won't go into the details of all the refinement we did we started from 50 and added different modifications to it. And for each modification, we evaluate what does it do to the accuracy, what does it do to the inference speed, what does it do to the training speed. And you can see that sometimes there's a plus, which means, okay, we improve the training speed, but sometimes there's a minus, some that reduce the training speed. But overall, we got an excellent model. And you can see here a comparison of ResNet 50 and a variety of architecture that we can propose later on, and T-ResNet. And in terms of training speed, the neural networks are slower because their focus was on accuracy. And they were hoping to reduce the number of flops, and by that being faster. So you can see EfficientNet V1 has 0.6 number of flops and MixNet 0.5 G flops. But when we go to inference speed, it's not necessarily aligned. So for example, MixNet has not that great image per second because flops do not necessarily directly correlate with the inference speed, which is another thing that we found out. So we're optimizing the inference speed rather than the flops. You see that actually the number of flops seems high, and the training speed and accuracy, which is better than ResNet 50. So we test this, just to make a point, we test this on multiple data sets in the single label classification test, or just because eventually we'll take this as a backbone for multiple different problems and multiple different tasks. So we tried on 4 different data sets and compared each one to the state-of-the-art model. And on all of them, we get state-of-the-art results pretty much, definitely in terms of speed, and usually also in terms of accuracy, although not always we're first, sometimes we're second or third. And skip this one. And I think that overall, if you go to SOTA Bench, and you'll see that they evaluate images per second and accuracy, you'll be at the top right. So we're very proud of that. Okay, so try to focus. I see I talked longer than I expected, so maybe I'll skip some slides. So let's try and look back at my starting point. We're talking about real-world practice, and there's real-world data that balanced data from multi-label classification. We talked about multiple objectives, high accuracy, fast and easy to train, fast inference. Let's talk about user-friendly. How can we make things user-friendly? And to make things friendly with users, we need to think about user intent. We might want to provide interactivity. We might want to provide user good feedback about what's going on. and some automation, and finally make things simple. So I'm going to skip those slides. If we have time, I'll go back to them in the question afterwards. And let's talk about the fun stuff. Stickers. How can we create such stickers? So we want to create fun for the users. We want to, again, take our research into practice by these fun creations. And again, under the hood, so many computer vision tasks are hidden. So you want to go over an image and filter out portraits, match them, extract the portrait, and to create the stickers, align it to align it with the pose estimation, align the facial landmarks, etc. So we need to go through all that, solve all problems, and then imagine benchmarking this. So now you're a researcher and you want to have your sticker creation. How do you go about doing that? So this is another challenge of real-world scenarios. How do you benchmark? How do you create these stickers and evaluate their quality? So I love this one where I use it a lot, but these ones maybe I like less. How can we measure quality is another challenge, but I will not go into that too much today. Just a little bit through this example, and you can see in this video a real example of you trying to delete a person from a photo, and we provide two ways to delete. One is just by a click, as you saw in this slide before. The other option is by marking, doodling over the image to mark what you want to delete. And again, in the real world setup, you can't solve anything as you wish by marking a square rectangle at the center of the image. You need to think about the user and what the user wants, and the user wants to be able to get them. And to do that, presentation of person for your, and then we need to be able to past. So a lot of the actor, you can try this out on we have this deployed there, you can check it out yourself. But going to the benchmarking, if you want to evaluate your algorithm and you're talking about something like in painting, then the standard you have to do two things. You have to measure quantitatively. Even if the quantitative evaluations are problematic, you have to use them. Otherwise, you have no way to refine your algorithm. And here we show results on the div2k data set, and we try both distortion measures like PSNR and perceptual measures like SSIM and FID. And you have to prove that you're improving on the state of the art. But you also need to do this qualitatively. And here we actually compare to an app. We took one of the best apps out there and compare what we deployed to what they deployed, because these are real scenarios. And as we saw, deploying the real setup is not exactly what you get in the lab. So this is just an example of one competing app, public app, and our solution. And you can see that, zooming in, you can see that we maintain the structure much better. Another example, again, here it's completely blurred and we maintain the structure much better. So let me wrap up and summarize what we talked about. So how do we bridge the gap between research and practice? We need to realize that real world data has its own limitations. Sometimes it's imbalanced, sometimes it's unequal. We need to adhere to multiple objectives. We can't just have an algorithm that has high accuracy. It has to be also fast and low memory and user friendly. And make an algorithm user friendly means that we need to make it automatic and simple for use. So let me wrap up. I hope I convince you that Cloudera apps are awesome because they both provide real value to users, but they also create real world challenges specifically for us computer vision people. There's so much we can do there, which is fun and exciting. And from the industry hat, I think we need to contribute and enjoy the research by carefully selecting the methods that are out there and are relevant and work with real world objectives. But we should also contribute this type of research. We should also contribute benchmarks to help others, other researchers to continue the work and exploration of real world scenarios. So, okay, I'll summarize here. So thank you for listening, and maybe I'll stop sharing and see if we have questions.
Yeah, we can have some questions if there are Q&A. I think I may just pose a question. See, you have use of reinforcement learning. In fact, in some cases, in one example, I found that there are experts who are providing a choice. So is it like an oracle in a kind of a learning system? Or these experts are actually indicating, making the choice, or is there provision also for some kind of reinforcement learning also to be fitted in those kind of problems?
Okay, so I think I'm not sure I completely heard your question fully, because the line was a little bit breaking. But I think the key idea is that you don't want to take hard decisions too early. You don't want to kill when you're doing the architect research. You look at an edge and it gets a weight, and if that weight goes down, you don't want to kill it too soon. You want to give it a chance, because it's at random start. So I think this is the reason we try to have those experts and try to use the gradual wipeout. Maybe the better approach, by the way, would be to just so this is what we started to do at first, and now as you see, we're going more defining the objective properly and using closed form solutions like what we did with the pruning, and we're doing that now also with architect research. We're trying to define the objective that we're really looking for properly and use the right optimization that will solve it in code. So when we can formulate things like knapsack, then we can enjoy the power of optimization and not suffer from making mistakes.
Okay, thank you. Any other questions? Pijan, any questions? I'm not finding anything in the chat box or Q&A. Parag?
Can I ask a question? Yeah.
Yeah, Parag. Yeah.
Yeah. So I wanted to ask. You said that NAST methods are very useful for figuring out network architectures. What is the current state of the art in figuring out architectures for generative models?
I'm not sure, actually. That's a good question. But so I don't know. It's good homework for me. But I think that specifically for me, for generative architectures, we've done in published in ICCV last year, we're going more towards the direction of pre-training maybe 1 or 2 networks, and then during the inference, just manipulating those are. So in a sense, more similar. What we're doing was more similar to this idea of once and for all alpha that I mentioned, that you pre-train, you invest a lot of effort in pre-training a super network, and at inference time, you just choose the sub-network that you need, or you create combinations, maybe you call it linear manipulations of networks to get what you want. So this is what the last thing we've done. But yeah, I should check, and maybe I can look afterwards, and maybe if I find something cool, I'll share with you.
Thank you.
Maybe one more. Any other question? Okay. let me thank Khalil for this fantastic talk, and it has opened up various new avenues to look at computer vision problems, and as we have been exposed to those possibilities, which is coming from an industry perspective. Again, thanks for your participation, and we shall look forward to your presence in ICVGIP in person in the future. Thank you. Thank you again.
Thank you so much for inviting me.
Thank you. Yeah. Thank you, Lee, for that wonderful talk. Thank you, Professor Chaudhary, for chairing that session and taking the questions to Lee. So we will now move on to the next session um, for today. I'll hand over to Chetan. Chetan, are you around?
Yeah, I'm around. But is it going to be a tea break in between?
Yeah. So I was okay. So we will break till 3:15, and then we will move on to another invited talk session. So when Chetan will take over. Chetan wants me to announce the break, so we are going on to a break.
Yeah, so we are going for a break for 10 minutes. So the tea break small, and we will reconvene at 3:15 with Tanaya's talk. I see you back in 10 minutes. Thank you.
Hello. Hi, Tanaya.
Can you hear me?
Yeah, there seems to be some issue with my broadband, so
Okay.
I hope it doesn't disconnect this time. So, do you see the share slides option at your end?
No, hang on.
File and new whiteboard. There's
Yeah.
two options.
Now it should be there. Can you check again?
Sure. Yes, I can share screen. Yes, I can share a particular app. So can you see my screen
Yes. Yes.
now? Okay.
Okay, so we will start in 4 minutes from now.
Sure.
Yeah, hi Abhinav. So maybe we could just wait for a couple of minutes more and then we can start. So it's 3:12 in my clock. So we just ask them to come back at 3:15, all the participants.
Okay. So we'll start at your go.
Yeah, okay. I'll just notify you 2-3 minutes.
Ji. Sorry, it's really noisy at my end right now.
You're in office or?
No, I'm at home and it's close to 9 p.m. So the kids, they are now in sleep mode. So noisy.
That's all right. I'm still waking up.
Yeah, it's really early at your end, yes. Yeah,
No.
well, thank you for agreeing for the talk. I know it's not a very convenient time on Monday.
Yeah, not that early, but yeah, I'm late.
How is the situation in UK now, Antaraya? So we have been hearing about in the news, the new strain.
Not good.
Of virus.
not good. We are all in and out of lockdown, like the entire year. They have very complicated systems, but I guess the bottom line is situation is not good, and they're vaccinating. They've started vaccinating, but I think it will take a few months before we can see the effect. So yes, that's and most of the things are like shops and other things are closed.
I just wanted to get a sense whether they are overreacting or they are still hiding. The UK. I mean, see, we know that in the Indian context, they're usually hiding. See, for
you mean
example, we
hiding
just know
the
at this
true
moment.
case? Hiding the true case,
Yes.
you mean? No, they're not hiding because it's a. So here it's more of everything is like public and the media is like public funded and everything. I don't think the government can hide. So they're not like not all the organizations are part of the government, so they don't have to listen to what government's saying. They're not hiding. They have always the
I
truth.
get the sense, for example, they just said that we know at this moment that there is that it's more virulent or more infectious than the previous one, but we don't know whether the mortality is more or whether the vaccination may or may not be effective. But many times I see it as the fact that they perhaps know that it is perhaps more deadly, but it's just that they are not very sure, so they won't say it.
Yeah, it's hard to say what is the case, but sometimes, yeah, I think sometimes they are a bit understated for the sake of public, I think. I don't know exactly if that is the case, whether it's more deadly, but they have found a new strain of virus which has been infecting more people than before. I think, so there's a lockdown in London, just announced, I think, 2 days ago.
Okay, I think this is time now, so maybe 3:15. So okay, yeah, Abhinav, you may please now take over, introduce them.
Okay, thank you. All right, welcome back to our invited talk session. And we have Dr. Tanaya Guha with us, who would be kindly presenting on trajectory forecasting, multi-object to multi-camera. So Dr. Tanaya Guha is an assistant professor of computer science at the University of Warwick, where she's also a member of the Warwick Machine Learning Group. Prior to joining Warwick, she was an assistant professor at IIT Kanpur and a postdoctoral researcher at the University of Southern California. She holds a PhD in electrical and computer engineering from the University of British Columbia, and her research focuses on building machine intelligence capabilities to understand, recognize, and predict human behavior, combining machine learning and signal processing. She regularly serves in the program committees of InterSpeech, ICME, ACM Multimedia, and ECI, and is also a recipient of Warwick Global Research Priority Award, ICME 20 Outstanding Area Chair Award, and has won many prestigious scholarships like Mensa Canada and grants from Amazon and Google. So welcome, Tanaya. The stage is all yours.
Thank you, Abhinav. And I'm very glad to be here. Thanks for the introduction, and a big thank you for inviting me for this presentation. And I'm really to be able to share some of my more recent work on this emerging topic of trajectory forecasting. But before I start, I'm just curious which part of India or which part of the world our audience is from, since it's a virtual. So if you don't mind writing where you're from in the text box. I'm not familiar with this platform, but is there a text box that we can see? I would love to see where our attendees are from. There's also a check that you are listening and you're not sleeping.
So our attendees can type in either the Q&A or the chat as well. So
okay. So which part of India? I guess most of you are from India. Chetan says Delhi. Great. Anyone else? Mumbai. Okay. All big cities.
Well, we do have a lot more attendees.
Right. Okay. So, all right, I'll move on. Okay. Oh, that's nice. On the okay. So thanks. That was just my curiosity. So I guess only Abhinav and I are probably attending from outside India. Okay. Anyway, so coming back to the talk, my plan today is to share some of our more recent work, which has been done in in the last 2 years on the trajectory forecasting. And so the material and the work that I'm going to present today is basically a joint work with my colleague, Professor Victor Sanchez, and our PhD student, Holly Stiles. And most of the slides are also adapted from the slides made by Ollie. And I will be talking first about, give you an overview of forecasting, vision-based forecasting as an area, and then I'll move on to our work. Humans, we are obsessed with knowing the future, aren't we? And if you think of knowing the future or seeing through the future, you probably think about Saruman or an old wizard with a crystal ball. Well, in the world of AI, this sort of wizardry is possible to some extent. So now that computer vision systems are generating near perfect performance in recognition and detection tasks, they can outperform humans very easily in several tasks. And then we also see the vision-based forecasting as the next frontier for computer vision systems, probably. That seems like the next critical step. And if we are able to do good vision-based forecasting, then it can enable human-like capabilities to the machines, and in some cases may give more than that. And this is a very broad area, actually. There are a variety of problems people are working on in a variety of domains. For example, there's work on human behavior and activity prediction or forecasting, or precognition, if you may call it. There's motion prediction, which we are doing in terms of vehicles or pedestrians. Facial aging, you can also consider this as a forecasting topic. And another very interesting work that has been going on is medical prognosis. And this to me seems very, very important and can be a game changer, where people are trying to predict what kind of disease you might have in long term, or given a particular disease, what is the risk for a particular patient. So given all this variety of topics that we have, I thought that we can get organized a little bit if we are talking about vision-based forecasting. So this is how we view it. We have this kind of a ladder, if you say, and at the bottom of it, we have the pixel level forecasting or pixel level precognition prediction, whichever word you like to use. And this is at the lowest level. And as you go up your level of abstraction, you go up to the event level prediction. And at the same time, as you go from the lower level to the higher level, you can also see the time steps that you can predict is also increasing. At the pixel level, you can expect up to, let's say, a few milliseconds, where as you go up in the event level, you like to predict an event in the order of minutes, hours, and possibly days and years. So that's just kind of a way to organize. This is not like the only way to organize forecasting work, but there are different. This is how we view it, and we think this is convenient for this. So here are a few examples for every level of abstraction. So at the pixel level, you can think of an example like a video frame prediction, and semantic level, you have some segmentation forecasting, instance forecasting. When you go up to key point level forecasting, you might think of human pose forecasting, and the trajectory level forecasting is what we are doing, what I'm going to discuss in this work. And some examples would be human trajectory forecasting, vehicle trajectory forecasting, etc. And then if you go up to the highest level of abstraction, which is the event level forecasting, and it's very, very exciting, where we have this action anticipation and the medical prognosis that I was talking about. So let me give you a few examples just to give the broad context of vision-based forecasting. So frame level forecasting or prediction is something we can easily think of given a set of n video frames. The task is to predict the future set of frames. And we want to predict every pixel. We want to have the value of every pixel. That's why pixel level forecasting. Now, of course, some of you who are familiar with video compression, you might know that frame prediction is also a critical part of video compression, but it's done in a very different way using motion vector prediction. And you can only predict one frame given another frame, either future or past. It's a different paradigm when you do this sort of frame level forecasting. And this particular work uses GANs to do the forecasting and gives very good results. This is an example of semantic level forecasting. So here we do not care about individual pixel values, but what we do care about is kind of a rough shape. Like, for example, here you can see the outlines of the cars. So we want to keep these shapes preserved while we do not care about the individual pixel values. And the two bottom rows that we have here, one is the ground truth of the semantic level prediction, and the ground truth, and the second row is the prediction. So as it is expected, as you try to predict farther away from the given current state, you do worse and worse. So that's of course is a challenge and always going to be the case. As we move farther in time, we are not doing as good prediction as we are doing in the first few seconds. So that was an example of semantic prediction. This is what I meant by key point level forecasting. So these are human skeletons, which is represented by the key points in the joints of a human body. And the task is to predict the motion of each of these key points and then thereby predict or forecast what kind of action we are looking at. So this is also another example of forecasting, vision-based forecasting. If you want to think of it as a event-based forecasting, because at the end the task is to do action forecasting, you can, but it can also be seen as a key point level forecasting. Before I go to the trajectory level forecasting, let me just say a few words about the event level forecasting, where I was talking about medical prognosis. So the task in this particular slide, what we have here is basically given a mammogram, the task is to predict whether a patient who is at high risk or low risk of having developed breast cancer. And this, we are looking at a timeline of over like years. So given like you are right now at the 0 years, how likely is a person going to develop breast cancer in 10 years or 15 years? And the plot below shows that how this prediction changes over the years. And as we have seen before, and as it is intuitive, and we can always expect that as you go farther away from the current state, your prediction gets worse and worse. So these were the different level of forecasting. Now, if I look at the trajectory level forecasting, that's where this current talk will be focused on. So I'll be talking about particularly pedestrian trajectory, but it doesn't have to be pedestrian trajectory. There are a lot of other moving objects that this methods that I'm going to discuss will be applicable to. Okay, so let me show you a short video. So this is the motivation for the task, which is a lot of the times because of the autonomous vehicle. So here we have who's trying to cross who's crossing the street. So let's say if you are in this vehicle and this is driverless, so you'd like the car to know well ahead whether to stop the car or keep going. So that's why we want to forecast where the person is going at an earlier stage, as early as possible. So this is basically the motivation behind this. And it has several applications outside autonomous vehicle navigation. You can apply this in mobile robotics, intelligent surveillance, which is also another important area that we are interested in. And also you can augment this with regular object tracking systems. So now what I'm going to do is I'm going to talk about two of our recent work, two threads. One is this multi-object trajectory forecasting work, and MOTF for short. This work was published this year in WCV, earlier this year. And the other work that I'll be talking about is how to extend this multi-object trajectory forecasting in a setup where you have a network of cameras. So this work has not been done before. So I'll be talking about that work later. So let me first talk about the MOTF, for multi-object trajectory forecasting. Okay, so MOTF work, simply put, you can think of this as three-step task. So given a video, you want to detect the objects, all the objects. In a multi-object scenario, you want to detect all the objects, all the pedestrians in this particular case, because pedestrians are a challenging case of objects where they change their direction or movement very quickly. So this is more difficult than forecasting trajectories for cars, let's say. Okay, so once I detect all the pedestrians in the video, the next job is to track them. So basically have their bounding box attached to their pedestrian ID. And after that, you want to, given all these past tracks, you want to forecast where they will be appearing in the next n frames, let's say. So that's the 3 steps that we are interested in, and we want to train a deep learning system so that we can directly get the forecasting output. So the difference between the existing work and this particular work that we did is that most of the existing pedestrian trajectory forecasting work, they had this kind of setup where you have a fixed overhead camera and this gives you a bird's eye view. And then these pedestrians are usually, they look like points. You can just track them like points. And what these papers did, they studied the social interaction among these pedestrians. So if you look at some of the key TF papers, now this list may be a little bit outdated because this was created when we were writing the paper. And there has been so many work that that has come out in the last few months. So apologize if I missed any of the key trajectory forecasting papers. But if you look at most of the works on until the future person localization work, they were all using this fixed overhead camera, and they are mostly concentrating on how these pedestrians interact. And then in CVPR 2018, this paper was published, which first tried to look at trajectory forecasting problem from a first-person perspective. So what they did is they used pose estimation and ego motion so as to predict the future trajectories. But they did not look at the entire bounding box. They just looked at one centroid point of the pedestrian, which is equivalent to treating it as a point, if you think of it. And it was not multi-object, so they were only forecasting one object per video. And they also had a very, very small data for doing this. So kind of motivated by this work, we wanted to extend this work at scale, and we want to move to a more challenging scenario where you stop treating pedestrians just like one point. So you can think of our TF paradigm as an extension of the multi-object tracking. So the difference with multi-object tracking here is that in multi-object tracking, you would like to predict the bounding box of tracks at a given current time step, whereas here we want to do it for the future steps. So the problem statement is fairly simple. Given this bounding boxes and tracks in M video frames for each object, what you want to do is you want to predict the future object trajectories in the upcoming N video frames. And when we want to do that, we do not just want to give the centroid, we want to give the entire bounding box as our output at every time step. So that's the problem statement, fairly simple. So when we wanted to do this problem, we looked for databases to do as a first step. And we found that there is no large public database that we can use for this particular task. There were some databases for tracking, but they did not always have all the information we need. Or there are some databases which has bounding boxes, but no tracking annotations, which was needed as well. So we created this large database called CityWalks, and this database is completely machine annotated, and it has becoming a little bit popular in the last few months. We have seen a lot of people are using our database, and that's great. So let me a few words about how this database was created. So CityWalks is a large and diverse database. data from 21 European countries. As you can see in this particular case, the pedestrian density is very sparse, and we have different types of pedestrian density of appearance. This one is in the evening time, so there are videos which has been shot in different weather and different time of the day. So does that mean that we travel to these 21 European cities to get these videos? No, of course not. We got all these videos from a YouTube channel called Pop Travel. So if you are interested, you can visit their channel as well. So after we get these videos, I'll just show you one example. Annotate them, and it was not possible to do any manual annotation. And in UK, Europe, we do not have mechanical Turk, so we had to seek some machine annotation strategies. So first we filter out some of the, so one big problem with dealing with first person videos is that you sometimes have large ego motion. So we had to filter out those segments or some of the video. We did not discard entire videos, but we just discarded some big segments that has a large ego motion. And then we ran standard object detectors like Yellow V3 and Musk RCNN. And then we use on top of that a tracker called Deep Sort, then so that we can tie all these bounding boxes to their pedestrian ID, so as to generate the tracks. So that's the basic idea. And here is an example where you can see that, as you can see that all the people are kind of getting detected, even if they're very small. And then each person has been attached to a number, which is their pedestrian ID, and that's how we are generating all these tracks. So this is how CityWalks has been annotated. Everything is annotated, and there has been some human verification, not a lot of it. So at the end, we had this 358 video clips, and as I said, it's quite a diverse database, and there are variation over how many pedestrians you are detecting. In a frame, it can go up to, let's say, 14, 17 pedestrians per frame, and also the track length varies quite a bit. We have used both Yellow V3 and Musk RCNN, and we have not combined them. So the annotations are available separately for these two detectors. And as you can see that Musk RCNN can find more tracks, it can detect more people than Yellow V3. So when we do the experiments also, we keep them separate and we did not try to combine them. And this database is, of course, available publicly from this GitHub link. If you're interested, you can download everything. Okay, so now coming to the model. So now that we have the annotations, we want to actually do the task, the forecasting. And we have this simple encoder-decoder approach. So in the encoder part, as you can see, there are two branches. One is the bounding box encoder, which takes all the information about the bounding box, the centroid position, XY, and as well as the width and the height that gives you the entire bounding box. In addition to that, we also have the velocities in X and Y direction, as well as the changes in width and height, just derivative over the frames. So we add all this information in the bounding box encoder input. And then there is another encoder branch which takes dense optical flow as input. So basically, if you have, let's say, 10 bounding box, you compute dense optical flow for all of them, and you separate them into X and Y direction. So basically, you have twice the number of small images, and then you put it through a CNN. So the first encoder branch, the bounding box encoder branch, because it has temporal information, of course, it uses a GRU. We also tried LSTM, but turns out that GRU gives better results in this particular case. So you basically have this GRU1 per timestamp, and at the end, we get to a single embedding vector, which is then fed through a FC layer. And similarly, for the optical flow branch, we also get another single embedding, which are concatenated. And then we have a decoder, which takes the single embedding, concatenated embedding, and then has a GRU, one step for every frame that you want to forecast. And this is the GRU output is followed by a FC layer, which gives you the bounding box output. So here, unlike some of the previous work, we did not explicitly use ego motion. We expected that flow vectors will be implicitly take into account both the object motion and the ego motion. We tried to add ego motion separately and not give us further improvement. So this is the simple model that we have. And when looking, we used some known metrics like average displacement error and final displacement error. These are the known metrics because where you are looking at the average distance between the ground truth centroid and your prediction. And for the final, you just look at the final time step. But we also, because we are predicting bounding boxes, we also wanted to look at the union for the bounding boxes for between the ground truth and our forecasted, our predicted ones, and similarly the at the final state. So you want your error to decrease and intersection over union to increase, right? And these are the results, and as we compare it with some of the recent works, our model works very well on this particular database. And this one just shows you the results using yellow V3, but similar results are similar trends are seen for the other object detector as well. And of course, we did some ablation studies to see which of this encoder branch is useful. And it turns out that both of them do have enough information, and when you combine them, they improve the results a little bit. We also break down the results across cities, across different weather, different illumination, and we found that our model consistently performed better than the competing models. And here we are a prediction up to 60 time steps, so we have 30 frames per second, so around like two seconds. I don't remember if there has been a downsampling. So I think it's around 2 to 3 seconds, not more than that. So we can, as you can see, that we are also, as we move farther away from the current step, of course, the prediction error will increase, but at the same time, we are still better than the others. Some examples of the results. So let me explain this a little bit. So what you are looking at is the result at the final time step. So ground truth is labeled in green, and our result is yellow, and arrival method is in blue. So, and the video shows the initial position of the person, which is the last frame that was put as an input. And at max, you will see 2 pedestrian trajectories being shown. We did not want to make it clumsy. So, but actually, in reality, all of them are being, all of their trajectories are being predicted. So as you can see that we are able to predict quite accurately in most of the cases. However, it fails terribly when we have very small pedestrians, or for example, in this case, there's a cyclist. We could not predict the cyclist motion at all. And also, if there is large ego motion, our systems do not work as well. So these are some of the results and failure cases. Now, the question comes, because this is machine annotated data, if we train our model on this machine annotated data, can we basically generalize to other databases where we have human annotated data? So what we did is we took database, MOT17, which was part of that CVPR 2018 paper that I was talking about. So this database, we trained on CityWalks, and then we traced it on this particular database. And we saw that we do generalize well if you train on CityWalk. So even though the data is machine annotated and it has not been human verified as extensively as we would like, but it still gives a fairly good test bed and good platform to train your forecasting models. So, of course, there's a lot of scopes of improvement still. As I mentioned, that the annotations that we have done are manual verification. So annotations are machine generated, and manual verification has not been done so much. So maybe we could improve on that, and better annotations may be possible. Another problem that we had is that we generated these two different type of annotations using YOLO v3 and NASCAR CNN. And the question is there a way to combine these annotations and make more robust annotations? That's an open question. We do not know yet how to do that. And as you might have noticed that when we are training our model, we just put one object trajectory at one time. So we are not putting like all the object trajectories together. So the joint learning of all pedestrians are not yet there. Now, this will bring new questions that how are we going to do, because the number of pedestrians will vary in every frame and things like that. So, of course, that might improve the entire system, and then we'll be able to look at the interaction among the pedestrians as well. So that's also something that is required, that calls for sophisticated modeling. And also, we don't have to stick to just one trajectory, because there can be multiple possible trajectories. As humans, we are predicting multiple possible cases. So, but that might require a different type of training database. But there are work that are looking at this sort of questions, that can we predict all the possible trajectories of a pedestrian. And also, finally, if we want to deploy it in the real world, we might want to take into account different types of moving objects like pedestrians, cyclists, and cars. And how to do that? Are we going to model them separately, or if there is one general model for all of them? So these are also some of the questions that are of interest here when we are talking about vision-based forecasting. Okay, so this was my first part of my talk. I don't know, how am I doing in terms of time? Are we good?
So we
Yes.
have like 15 more minutes, 15 to
Okay, yeah. I believe I'll be able to finish. Okay, so let me move on to the second part, which is multi-camera trajectory forecasting. And so far, we have only published the database, which was published in CVPR workshop, precognition workshop, and where this paper got Best Student Paper Award. But the modeling part we're still working on, and it's very much an ongoing work. And I'm hoping to get some feedback and good points of discussions from our audience. So let me discuss this particular work. So this is a new problem that we introduced called the multi-camera trajectory forecasting. All the work before this work has been on single camera forecasting. But now what we have is we have this network of, they may or may not be overlapping view. So what you see, your input is this black dashed line, which is the past trajectory. And most of the work in this domain was to predict this red dotted line, which is within the same camera view where the person is appearing. But now what we want to do is we want to extend this to this network of cameras, and we want to predict the entire trajectory across cameras. So we want to predict the red line as well as the green line. And again, the task, simply put, is to predict the trajectory of a person across multiple cameras. And we are looking at a much longer timeline here. The last work I talked about 2 to 3 seconds. Here we are talking about 12 seconds. And this is basically the task. Of course, this was a new task and there was no database. So what we did is, in collaboration with NTU Singapore, we created this database called Warwick NTU Multi-Camera Forecasting Database, or WNMF for short. So this database is pretty big. The shot in NTU campus, and there are 15 cameras which have this type of layout. And we have the 600 hours of footage from all these cameras taken over entire day and over 20 days. So it has enough variation in terms of illumination. And it also covers certain indoor areas where there's some areas which are open, kind of semi-outdoor. So it has good variation. And this is a large footage that we collected at NTU. And then, of course, comes the big problem, annotation. Before that, here are some examples. The videos look like. Okay, so of course we can never do this manually. So we actually had to come up with a system to do the annotations itself. So how we do it is, the first step is to take all this footage from all the cameras and run our detectors and trackers as before. And then what we do is, for every camera, for every footage, we mark the entrance track and the departure track. So that would be like 20 frames when a person is entering and 20 frames when a person is departing a particular camera view. So for each footage, we will select this tracklet while a person is entering and departing the same camera view. And then our job is to do these matches across camera. And for that, used a person re-identification system. So we have our person re-identification model, and its job is to find the matches across all this entering and departing tracklets. So we compare all the entrances with the departures, and always across different cameras. And we use this re-ID features to see whether they are visually similar. So basically there is a person re-identification going on here. And we put some thresholds. We also put some thresholds on, like the distance. If a person you think is reappearing after like 1 minute or a long time, then that's likely not to be a match. So we put certain conditions and thresholds, a lot of heuristics here. And then we come up with this cross-camera matches. And then there is a manual verification for all the matches that were generated by the person re-ID model. So this one has been verified at every level. But the manual job is not that difficult, because all a person has to do is look at this pair of matches and see whether they are the same person or not. So this is how this WNMF database has been annotated. And here is, for example, you have an example, like this person gets out of camera 9 and then enters camera 10. And this is a match that has been found automatically using a person re-ID system. So now our task is this: given this past trajectory of a person in a single camera view, we want to predict in which camera this person is going to appear in the next 12 seconds. It can be multiple cameras. And when will the subject appear in those camera views, and where? I mean, that means like spatially within the view, if we can find out the bounding boxes in those views. So these are our MCTF tasks. So these are basically the 3 tasks that we want to perform. And the database is currently available. As I said, it's already there with all the features, all the videos and everything. So if any of you are interested in working in this problem, which is a very challenging problem, given all this footage and all these different cameras. I'll be very, very happy to hear from the interested people. Okay. So now what we have done so far is just the which camera part, which is very easy in the sense that you can look at it as a classification problem. Given this past trajectory tracks, you have your model, and then you can give an output, which is a vector of the same length as your number of cameras, which gives you the probability of the person appearing in every camera. So of course, this one we have done so far. And you can also argue that why not use simple things like it is likely that one person will move to the nearest camera. So of course, we compared with that. Also, given all this training data, you can come up with some statistics that how the person moves, or you can get these transition probabilities from your training data set, and you can directly use them as a prior and give some results. And this is also something we compared with, but as you can see, as you have trained models, you get slightly better result on which camera. So this is the work we have done. And of course, now what ongoing is something I just wanted to put forward for discussion is that what we want to do with this database is, so this is what we have done. Let's say, given a trajectory, you have your system, some recurrent models, and then you have your output, which is a vector. Now, if you want to move to the domain paradigm of when it is appearing, what you want to predict is basically a matrix like this, where every column is a camera and every row is basically the time. So here in this example, what I'm showing, at the first two for the first two time steps, this object is predicted to appear within camera view number, and after that it appears in camera view number, let's say K. And of course, it can also appear in multiple cameras if they're overlapping. So that is definitely possible, and we want to give an output of this. Now, if you want to move to which, when, and where paradigm, the problem gets a little bit more complex. And then we have this sort of tensor with basically 4 dimensions, where you have camera, you have time step, and you also have a location X and Y. So this is where we want to get at, where we have this complete output of where the person is going to appear when and within which camera views. Okay. So, sorry. So this is what we are currently working on, and hopefully we'll see some results. But the questions that we are facing, and I'd like to open this up for discussion, that how to best represent this multi-camera trajectories. If you have a single camera trajectory, it's simple, but when you have multi-camera trajectories, think of this, that some cameras will have no trajectories at all. So you have null trajectories, and how do you represent them in this kind of setup? So how to evaluate the performance? Most of the metrics and work has been done on single camera, but they may not work here very well. So if you predict the camera right, but the time step a little bit off, how do you evaluate that versus what happens if they appear in multiple cameras and you can predict only one of them? Do you look at it like a retrieval? What sort of metric will be best? That's another question. So what we haven't done here, that we haven't leveraged the network structure that much. So if you're given the camera network structure already, if you know it, can you leverage it in doing better forecasting? Okay, so now the problem is that this is not a problem, sorry. This is an application, it's a good thing. So this is, MCTF can improve surveillance network, and we are currently working towards applying it in some real problems. And it can complement the current tracking and models. But there can also be some new MCTF tasks. For example, it could be possible that, or maybe it's too difficult, but if given all this data, can we have an inverse problem where we want to learn the locations or the structure of the camera network or things like that. So I'll be very happy to hear about your thoughts on these challenges and opportunities in pedestrian forecasting. So that's it from my side, if you have any questions.
Thanks, Tanaya. Thanks for the very interesting talk. Let me see the question and answer tab. Okay, to all, if you have any questions, you can please type in the chat or in the Q&A tab. And meanwhile,
questions, comments, thoughts, anything.
So, Abhinav, can I go first? This is Arnav from Mandi. Yeah.
Yes, sir, please.
Yeah, thanks for the very interesting talk. Particularly the multi, camera formulation is quite interesting. So, in fact, I had a question which is probably related to the third point you mentioned about the camera network structure. So, I was just wondering that if we know the camera parameters, for example, we would have an idea about the field of view of the camera, and that information, if we are using it, all the three questions, which, when, where, I think that's probably a very important information, because in your toy diagram, for example, you showed that even the closest camera, if it is facing the other way, there's practically no information there. So would you like to comment on that?
Yeah, absolutely. Thanks, Arnab. Yes, I think if the cameras are some information like, I'm not sure if you're talking about the intrinsic parameters or extrinsic parameters.
Both, actually, both. Yeah.
Both. Okay.
Yeah.
Okay. And also, it's also kind of the views are limited by the building structure also. But if we have that, we can leverage that. I mean, exactly how to leverage it is a question. Like, how do you form a graph structure? Do you those are definitely some open questions, and I'll be happy to discuss. But yes, I think that is possible to leverage, and it will give better results. But then again, comes a question of, if you change the network structure, then you have to probably change your model.
Yeah. Yeah, perhaps they can reflect in the loss functions that you learn your network from, or something.
Right. Yeah, I think we can put some constraint on the optimization function that, depending on the camera positions, where you can go and where you cannot go, sort of.
Thanks.
Okay, so to our next question. So from Hirnay Ghosh, how about correlating predictions of two objects? For example, let's say when two persons are walking together. So do you think that will improve the future?
Absolutely. I think I was saying this as a scope for the first work, that we haven't done the joint predictions. That will definitely help if you start predicting people together. And it will, correlating, looking at similar categories if they're close together. But if this is good for when the density is low, but as you have more dense videos with more and more pedestrians, sometimes these correlations can also be misleading, because if they're close but they're working in opposite directions, or they're not together. So yes, I mean, definitely we'll have to try and see. I think that's
okay. And just to send a question to the same one. So when, let's say, in a use case, two people are crossing each other, what happens to the optical flow there? Since only in the single camera setting, only one person is visible. Does that affect the prediction of?
So you're talking about a case where we have occlusion in the input boundary, right?
Yes.
So if we compute the optical flow only for the detected bounding boxes. So if we haven't detected a person for a particular frame, we will not be able to compute the bounding boxes, compute the optical flow. So after we detect the people, we have their bounding boxes, only then we compute their optical flow. But at the output, when we are forecasting the trajectory, we do not put any optical flow. It's just the bounding box that we care about. Yes, so if there is an occlusion, we do not have the input data there.
Okay. All right. Okay. So I was wondering, as another use case, especially when you showed the example of a car in the start, there was a scene of an accident. So if we are doing it from a first person perspective, like an ego motion perspective, then would it be useful to actually use the gaze and head pose of the person as well, for whom we are actually going to do the future prediction? Let's say a person who's in the car.
Yes, it will be possible if you are looking at the drive, if you want to do it from the driver's perspective, and extracting that information from the video where the person is looking may be possible, right? With I don't know so much about this, I mean, of your area, you know. So maybe from this, it may be possible, and it might help to do better sort of forecasting as well. For our case, the motivation was mainly for autonomous driving vehicles. So we haven't done those sort of things, but definitely it may be a good direction.
Okay. And when you were discussing about the data collection for the single camera and later with the Warwick Nanyang dataset, it made me wonder. So in 2015, there was a paper by Wang and Gupta at CMU who proposed a self-supervised approach where they tracked the subject in a video and then learned a pretext task where they jumbled up the frames.
Right,
So
right, yeah, yeah.
something of that sort could also be used, given that in the first work, there is no manual annotation going on. So a little bit of manual annotation and a lot more data, which is learned as a pretext task. What are your thoughts on that?
So if I understand the question correctly, you were saying that for the annotations, if we can use some sort of self-supervision or like some pretext task that could be thought of. Yeah, I think I know the paper you're talking about, the jigsaw puzzle paper, right? I think that's the work that jumbled the entire image and tried to predict the order. Yeah, I think in that sort of ways, right now, I do not have any idea how to frame it, but it does definitely seems like an interesting direction to think about if we can use some sort of, come up with some new pretext task maybe in terms of this bounding boxes and use them. Sure, yeah. Give me more information about that, how to do it.
Okay. So, I see in the chat there are a few more questions. So from Shrikant. So the question is, how is the varying size of the object handled in the sequence, and is any pooling performed on the flow vectors?
So the first question is about the object size. So as you can see, what we have is we want to predict both the entire bounding box. So that basically takes care of the scale. So we do put this information about the width and the height, and that's what we also predict. So that's how we take care of the scale. And what was the next question about?
So the next question is that is any type of pooling performed on the optical flow vectors?
No, there has not been done any pooling. This was there's just a regular convolutional network that goes in. Yes.
Okay.
Not yet.
Okay. All right. So moving on to the next question. So here's a question from Garima. The question is, can we use the information of the setup of the cameras, such as placement of the cameras, as there are multiple cameras which would encode this information implicitly?
Yes, I think that's the question. I think we also discussed with Arnav that we definitely want to use it, but what is the best way to use it, whether it is to put some keep some constraints or to use it as an input, like if you can have some sort of matrix that encodes the network structure and use it as an input. We are working on these things, like what is the best way to do it, but definitely it will help the forecasting, because as you might remember that if you just look at just use the next camera as your next camera, you get a decent result. So that means the network structure has a lot of information there. How to best leverage it is definitely a question, and yes, we are working on it, and it will definitely be useful.
All right. Okay. And so I was wondering, since the expectation of the multi-camera, multi-object tracking work is to predict, let's say, 10 to 12 seconds in advance. But given that if, let's say, there is a generous amount of motion happening where a subject walks through in front of multiple cameras, there would be multiple solutions coming in. So, like my question is, how do you think we can actually constrain the set of multiple paths which a person can take, given that there are few cameras in the future as well, like both spatially and time-wise?
Abhinav, you have to repeat the question. So are you saying that we have more cameras added to the network later on?
So if we want to predict, let's say 12 seconds or 10 seconds in the future, there are multiple options, right? There are multiple solutions based on the current location of the person. So I was wondering if we can actually add a constraint based on the location of the future cameras, which can actually limit the search space of what could be the optimal path which a person could take.
Yes, actually, there is a possibility that you can put these constraints based on either use like information as a prior, that what is the most common route, right? I mean, for people. So that can be used as a, I think all this information can be used as a prior or a constraint to, but for this, as far as search space is concerned, I think that's the bottleneck is when it comes to doing the which, when, where, the all things. If you just want to predict how many cameras, that classification problem, at our case, only 15 cameras. But even if you increase it, it may be like 30 cameras, 100 cameras, still doable. I think the main problem comes in the next phase when you want to predict the entire tensor and all these time steps. So that's I think is more kind of a challenge than at this point the search space of the camera. So our hope is that if so currently when people do person re-ID, they just have to do the entire search over all the cameras. So our hope is that if we are using this sort of forecasting, there we can limit the search space, as you're saying, and we can tell people, okay, you just have to track these 3 cameras and see if the person reappears and match them. So the idea is to augment it with the person ID models that are already people are working on from a different perspective.
Yeah, I think there are some really exciting possibilities with especially the second work. Yeah,
right. Yeah. So the database is out. So if anyone is interested, jump in because it's really, it's a challenging task, and you can come up with new tasks as well.
Yes. Yeah, I see there are a lot of possibilities. All right. So we are well in time. With that, thank you so much, Tanaya. Thank you for such an enlightening.
Thank you for inviting me. Thanks, everyone.
Okay. Thanks. Okay, Parag, over to you.
Okay. Thank you. Thanks, Abhinav. And first of all, thank you, Tanaya, again, for giving this wonderful talk and agreeing at such a difficult time we can all understand because of the pandemic. Thank you again. And thank you, Abhinav, for coordinating all this and chairing this session wonderfully. Thank you to you also. Thank you.
Yeah.
All right. So we have now the next session, which is on the Vision India. So where we ask the researcher with the Indian researcher as the first author for the paper that have appeared in the last year. So I would like to invite Dr. Vineet Balsubramaniam to please take over from here and introduce the session chair. And Vineet, are you here?
Hi, Chetan. Can you hear me?
Yeah, I can hear you now. Thank you. Okay. Yeah, over to you now.
Thank you, Chetan, and thank you for all the organizers for having the Vision India session as part of ICVGIP this year, despite all the challenges. So as we already completed 2 sessions on Saturday and Sunday, 4 talks each. So today we'll have the last set of Vision India talks. We have 4 talks lined up for the next 1 hour. Without further ado, let me actually hand it over to the session chair for Vision India today, Dr. Venkatesh Babu. He'll take over from here and coordinate the session. Venkatesh, are you here?
Yes, yes. Hope you can hear me.
Yes, we can hear you.
Yeah. So, welcome to this Vision India session. We have the final 4 papers in this session. Before getting into this session, just let me take a few minutes of the time. So, this Vision India is actually aimed for showcasing top-tier conferences as well as the journal papers to our Indian researchers. So this is one of the important initiatives of ICVGIP. So why it is very important is the statistics shows that the number of people participating, a number of people publishing good top tier papers are publishing in the top tier venues seems to be very sparse from India. So it is our important objective and responsibility to increase the number of participation in these top tier venues. So that is why we wanted to showcase these top tier papers and encourage everyone, Indian Vision community, to publish more papers in this forum. So it's a very noble and a very important initiative. Hope this initiative is there for at least past 3 editions of ICVGIP, NCVP or MPG. We are yet to realize any effect of this thing. Still, we are not having so many papers that is required from our country. So if you look at our participation in the global AI research area, it's not so good to look at actually. For example, this year's CVP 2020 statistics, it shows. So India's contribution is about 1.5%. And again, if you compare with our closest neighbor, it is Singapore, who's having 1.7. Though Singapore is about 200 times smaller than India, at least we should be doing much better there. So this is just 1 or 1.5% is not sufficient. So with this introduction, so the objective is to not just to listen to the top papers. We are supposed to submit papers to the top conference venues. That is the major objective. And just to make sure that every 5 papers of yours, there should be at least 1 top tier conference. That will significantly boost our numbers in the international forum. So so with this I'll stop here and then get into the papers. Okay. So we have 4 papers lined up here. The first paper actually comes from IIT Delhi. So the title of the paper is sharing egocentric videos giving away your biometric signature. Very interesting. So Daksh Thapar will be presenting the first paper. This paper is presented at ECCV 2020, one of the top venues for our vision research. Let me invite Daksh to present this paper. Daksh, are you there?
Yes, sir.
Sure.
Am I audible?
Yes.
Yes. Yeah, okay. Yeah, so thank you, sir, for the introduction. And hello, everyone. My name is Daksh Thapar, and I'm a PhD student in Indian Institute of Technology, Mandi. This work I have done with my supervisors, Dr. Aditya Nigam from IIT Mandi and Dr. Chaitanya Arora from IIT Delhi. The title of the work is Sharing Egocentric Videos Giving Away a Biometric Signature? The work has been accepted in ACCB 2020, and we have also extended this in ASEAN Conference Multimedia 2020, which also I will cover in the later parts of this presentation. Now, due to the popularity of the GoPro cameras, a lot of egocentric videos are being shared, especially in the streaming platforms like YouTube. But however, not just for end users, but also for research and industry purposes as well, egocentric videos have a lot of applications. So because of that, in recent times, we are seeing many of the large-scale data sets like FPSI, Epic Kitchens, EGTA datasets, and so on. One of the major aspects why these datasets are being shared is that since the camera wearer is never visible in an egocentric video, we assume that the privacy of the wearer is preserved. So for example, if I want to share any egocentric video in YouTube, I can easily do that since I'm never visible and I can assume that my privacy or my identity is always preserved. So for example, here we can see that there are two pairs of videos. Now, can we tell that which of the pairs of these videos are actually coming from the same wearer and which of the pair is actually coming from a different wearer? Now, it is important to note that even if the camera wearer is not visible, but the camera is head mounted. Hence, it captures the head motion and in turn, it captures the walking motion of the camera wearer. And this walking motion, the technical term is gait. We can actually extract the gait of a person, the features of a gait of a person from the given egocentric videos itself. So here we can see that the proposed ego GateNet framework is able to tell whether the two given videos they are coming from the same wearer or they are actually coming from different wearer. And it's important to know that a proposal only needs 1 second of video to do the set computation. Now the other challenge that comes, what if the videos were taken in very different conditions, especially the conditions which have never been seen by the proposed framework. So even in this scenario where the testing condition was a condition where was an outside condition which was never seen by the ego GateNet framework while training, the system was still able to tell whether the two given videos were belonging to same subject or not. So even if and another thing that's about the ego GateNet is that it is an open set framework. That is, it does not even require to actually be trained on each and every subject or each and every camera wearer. So even it can actually verify and identify unseen camera wearers in unseen environments as well. So how does it work? Just a brief overview of how it works. That it takes an egocentric video of 1 second and it breaks down into 15 frames. We compute optical flow over these 15 frames, and that CDCNN and LSTM based pipeline is used to extract the gate features from these optical flows. Now, to ensure that these gate features are actually unique and are discriminative, the whole system is trained by a triplet loss function. So here we can see from the results is that even in an open set scenario, so what I mean by open set is that a camera wearer was never seen by the while training of the EgoGet framework. On the public dataset TBPR, we have got an equal error rate of only 14%. And on our own proposed data set, we have got an error of only 9%. So with just an error of 9%, we are able to identify a camera wearer in an unseen situation as well as in an unseen camera wearer. But this also does not pose a major privacy threat as we do not have a large corpus of labeled egocentric videos to match any given video. However, we do have a corpus of third-person videos available with us, aka the surveillance videos, through which we can easily identify the person by just seeing the surveillance videos. Now, since both egocentric and third-person videos, they capture gait, that is the walking-based features. Now the question arises that can we tell whether given a pair of egocentric video and a third-person video, whether they belong to the same person or not? So if that can be done, then given any egocentric videos, I can actually extract the corresponding third person walking video of the camera wearer. And since in the third person walking video, I can actually see who is the camera wearer. So given an egocentric video, I will be actually able to identify a camera wearer. So if this is possible, so this is a very potent privacy breach while sharing the egocentric videos. So the proposed HSNet plus CombinedNet framework is actually able to do this. So it is able to match given any egocentric video to the corresponding third-person video using the gate features that whether the two videos they belong to the same person or not. Even if the videos were actually captured in very different environments through which the network has never seen and the network has been never trained on, even in such an environment, the proposed system is actually able to easily identify whether the two corresponding videos they belong to the same person or they actually belong to the different person. So how this works is basically HSNet. So the proposed framework has to extract both first person as well as third person gate features. So we have used our own previously proposed framework EgoGateNet to extract our first person gate features, and we have used a state of the art gate recognition system to extract the third person gate features. Now these two features, they are actually gate features, but they actually lie in completely different space. So we have proposed a hybrid Siamese network which projects these both gate features into a compatible space. And finally, a combined net actually combines these features in the compatible space to provide us with the final matching score. And the system HSNet plus combined net are trained together using hybrid triplet loss function. So here we can see that when we are using combined net, we are actually able to recognize any camera wearer with an accuracy of 73%. So this CRR is actually the first rank recognition accuracy, and the first rank recognition accuracy itself is a 73% when I'm trying to match an egocentric video with the corresponding surveillance videos. So this actually shows that there's a very big privacy breach when I am trying to share, because I can easily tell who is the camera wearer of the egocentric video that has been shared, even when the camera wearer has never been seen or even the environment has never been seen. So that was the work that we actually proposed in the ACCV 2020. However, that work has a very big drawback. To extract gate features, we required a walking motion. And hence, the whole EgoGateNet and HSNet framework actually relies that we have walking motion in the egocentric videos. But however, many data sets like Epic Kitchens and EGTA, they have very minimal walking motion. So for example, this is the snapshot of an Epic Kitchen data set. So we can easily see that the walking motion is very minimal in such cases. So now, given such videos, how can, whether there's a privacy breach in such videos as well or not? So this was the question that was answered in our ACM Multimedia 2020 paper. So the problem is again same, that given any two egocentric videos, okay, we need to tell whether the two videos they belong to the same person or not. But in this case, there is no walking motion when it comes to egocentric videos. But despite, even if there is no walking motion, we can easily see that the hands are actually visible in these videos while the person is actually doing the said activity like cutting or washing a plate. So our the proposed framework is actually able to capture the hand gestures. So the hand gestures based behavioral biometric is captured by the proposed framework, and it is actually able to tell using these hand gestures that whether they belong to the same person or they belong to the different person. So to conclude, we need to be very careful in sharing egocentric videos, as by doing so, we are actually giving away a biometric signature. It can be gait or even it can be our hand gestures, and which can be used to easily extract the identity of us as a camera viewer. And thank you.
Thanks, Daksh, for an interesting talk. Is there any question from anyone? I'm not seeing any question in the chat window. Okay. I have a question actually. So, So for example, if where you are fixing the camera for the person and then taking the videos.
Yeah, so the camera is head mounted.
Head mounted, okay.
Head
So
mounted.
how, for example, if the person is wearing a different kind of a shoe or carrying a bag, how does it affect? Because nobody walks without bag and things, right? And they keep changing their shoes, chappals. So does it affect these kind of external factors?
Yeah, actually, so footwear affects both third person as well as first person gait. Footwear actually, so that's the challenge that we are working on with variable footwear as well, how we can actually extract variable footwear. But the initial experiment that we did was shown that the system was robust enough for multiple bagging and clothing conditions.
Okay.
So it's just a matter of getting the proper data. So if we have data for persons wearing different footwears, then yes, the system will work. But if again we don't have the data of a person wearing with a footwear variation or a bagging variation, it will be really difficult for the system to identify.
Okay, one more question is actually, see, nobody is going to keep a camera on your head and then walk, right? It looks kind of odd. Whereas we always keep our mobile in our pocket and then keep walking. So you get a lot of gyro information, right? Have you come across any work that actually exploits this kind of a signature? Because that gives out kind of a very nice walking style, all those things, right?
Actually, sir, when it comes to mobile phones, the work that I've seen published is that people are able to recognize you by the way you are using the touch of the phone. That's one of the work that I've come across in biometric, that the way you touch your phone or the way you use a touchpad, people
No,
can.
no, I don't want to touch the phone because nowadays it is dangerous. Is a way of doing that. Okay.
Yeah, actually, we are ourselves doing experiments with other sensors, wearable sensors, like the shoulder-based sensors and the phone-based sensors. So in the phone, we actually took the accelerometer and gyroscope data, and initial experiments actually say that we are able to recognize a person, but accuracy is still very low, 16-70% only.
Oh, I see. Okay. Okay, Daksh, very nice, interesting. I also wanted to, you're a student at IIT Mandi, right?
Yes, sir. I'm in IIT.
So in the introduction, I just thought it is IIT Delhi. Okay. So the authors are actually from IIT Mandi and IIT Delhi. Hope you have done an internship at IIT Delhi.
No, sir. Chetan sir is my co-guide.
Okay, sure. Okay, so it's a paper is from IIT Mandi and Delhi. So I should have been careful there. Thanks. Thanks, Daksh. So now let's on to the next paper. So this the paper title is Action Quality Assessment Using CMS Network Based Deep Metric Learning. The others are from IIT Jodhpur and IIIT Hyderabad. Hiteshi then will be presenting this particular work. This work is published in IEEE Transactions on Circuits and Systems for Video Technology. Hiteshi.
Thank you, sir. Are you able to hear me?
Yes, I could.
Okay, sure.
Make it full screen so that.
Yeah. Can you see my screen now?
Yes.
Yeah.
Yeah, please.
Good evening, everybody. I'm Hiteshi Jain, a PhD from IIT Jodhpur and currently working as Senior Applied Scientist at Purview Software Solutions, Bangalore. I'm here to present one of my PhD works entitled Action Quality Assessment Using Siamese Network-Based Deep Metric Learning, published at IEEE Transactions on Circuit Systems and Video Technology, August 2020. This paper is co-authored with Dr. Gaurav Harit from IIT Jodhpur and Dr. Avinash Sharma from IIIT Hyderabad. I will take you through the motivation behind this work, followed by how action assessment is different from action recognition, the past works, our contributions, and finally the results and future scope of the problem. We've all come across some news articles that talk about human bias in Olympics judgment. Well, human bias is inevitable. It can be nationalistic bias, bias towards some good athletes, etc. Can we have a CV-driven third empire? The answer is yes. We can have an assessment module that learns to map the input training videos to their respective ground truth scores. If now we give a video to such a system, to such an assessment module, it can provide a feedback both in terms of score and the mistake it makes. A catch here is identifying the mistakes. Judges in Olympics are not accountable. However, computer vision can introduce more objectivity and interpretation in terms of feedback. Human action recognition is a much researched topic in computer vision. How different is it from assessment? The simple answer is recognition deals with inter-class variability, whereas assessment deals with intra-class variability. Further, a small clip can help us recognize that this action that you can see on your screen is a diving action. While in case of assessment, you'll have to see the entire videos and compare them to see which one of these would be better. Having said the background, let us have a glimpse of the literature. The works in the field started in 2014, so it's a new field which has come up. And in the past 5 years, researchers have been using different video representations followed by different aggregation techniques. So if we have a clip level pose features, how do we aggregate it together? And then finally, different ways of regressing the representation to the final score. Thus, in simple words, we have an input video, we have different kind of representations, and then a regression model, and finally a judge's score. The common thing which is there between all the past works that we have seen is that all dives are considered independent, and there is no reference which is being considered while there is a comparison being made. So here comes our contribution. The intuition behind a solution to the problem we discussed was that as humans, we always have some reference in our mind when we are asked to judge a performance. On the similar lines, we proposed a model that compares a test video with a reference video and maps the similarity of the test video to the reference video to the final score and gives the piecewise contribution of each clip in the video to the final score. So we have both overall scores and the piecewise contribution. Well, the immediate direction we can think of is to use a Siamese network to learn the similarity between these two videos. But the problem is that the top scorers in any Olympics or any event for that matter are too few. And the number of prayers that is required to train the Siamese is very less. Thus, we solve the problem in two phases, where in the first phase, we learn to find similarity between any two videos, irrespective of whether it is an expert or not. Once we learn this kind of a DML-based metric, a similarity metric, we use the same model and find the similarity between the expert and the candidate video and then map it to the ground truth score. So we'll start with these two phases. In the first phase, we said that we want to learn the similarity between these two videos. What we do is we inherit one of the representations which is being used in the previous papers, where the entire video is divided into clips of 16 frames each. And then this C3D feature is used on top of those clips to find out the clip level features and aggregated using an LSTM. So the previous paper has been using this OP output and regresses it to the ground truth score. However, what we do is that we have, because we are learning the similarity, we take the two representations from LSTM OP and OQ and then pass it to a dense network for which the output is a sigmoid that learns similar versus dissimilar output. So if the difference in the score between these two videos is less than a threshold, say TH, then it is the output would be 1, otherwise 0. So we wanted to understand first that whether this DML is actually learning some kind of a feature representation feature space that brings these closer scored videos together or not. So we first saw the TSNE plots of this LSTM embedding, which the previous papers were using. And then we saw the mapping, the representation of D2 embedding in space. So when we see the LSTM embedding, it is spread all over the place. So this radius of the circle represents the score which is there for the video. So it is spread all over the space without having any coherence in terms of scores. However, when we see our DML representation, it is spread across in space such that all coherent scores are clubbing together, and the score which is like say 50 is far off from the expert score. So that gives us a confidence that it will work better. In terms of quantitative analysis, we see when the score difference is less than 5, which was a threshold we chose for diving, then the predicted probability, the sigmoid output is also high, whereas when the difference is greater than 5, say 9.9, the similarity output, the predicted output from Siamese or from sigmoid also goes down. So this is where we have solved the problem of identifying the similarity between any two videos. Now we want to use this similarity metric to map it to score. So the only difference that we make is that we change this SP, this video, the top video with an expert video, and the bottom video becomes any candidate video. We freeze this entire box which is there, and then we just use a train and final connected layer, fully connected layer with one neuron to the ground truth score with respect to mean square error loss. So now, so we term this model as reference guided regression. Why? Because there is a reference which is guiding the candidate video to its respective score, and we wanted to see whether it is actually contributing to the loss as well or not. So we saw by simple dense layer equations, the yi has a contribution of this yellow and cyan individually, and this traverses way down to the final dense layer, which is this final black layer, which bring us down to ZQ. This one is equal to AK, which is a contribution from the expert, and then ZX, which is a contribution from the candidate video. And in the loss also, this term remains, W double dash times this term. So when we differentiate it, there is an expert embedding, the expert contribution which is coming in those, during parameter learning. And that is where this expert has a impact on the final representation. So the second contribution, as we said, was feedback proposal. So the results of the scoring model, I'll take all the results together. So we'll first move to feedback proposals. So this final sigmoid layer that we learned in the DML case, it was learned based on the differences in the score on the overall score. So we wanted to understand if the same network can also help us in identifying the clip level similarities or not. So what we did was that if we want to evaluate the jth clip similarity, we padded all j-1 clips to with a black clip and just retained that jth clip and then computed the sigmoid output. And this, when we see the results, we see that this really helped us in identifying the exact similarity of a query video from the expert video. Coming on to the results. So the scoring metric were two. First was the mean square error, which is obvious that there has to be a good, lowest difference between the predicted and the ground truth score. And the second was rank correlation. So if we're coming on to rank correlation, if the ground truth rank, for suppose 5 performers is 1, 2, 3, 4, 5, and the predicted rank is opposite, then the rank correlation would be -1. And if it isn't coherent with the ground truth ranking, then the rank correlation becomes +1. So the range of rank correlation is from -1 to +1. The higher the rank correlation, the better the model is. So if we evaluated our model on 3 action data sets. First was UNLV diving, where the training videos was 204. So as I've said, this is too few to train Siamese alone. So that is why we had that first phase. So we saw that the RGR, which is our model, has the maximum rank correlation and the minimum mean square error as compared to the other state of the art. Again, with UNLV vault exercise, gymnastic vaults, we had highest rank correlation and lowest mean square error. Whereas with this row that you can see here, that is when we train the first phase with diving. I mean, the similarity matrix is being done by diving, but we want to evaluate the performance on vaults. Then also it was performing well, which says that the model is generalizable. With AQA datasets, again, the model was outperforming. We had a placement study just to see whether the Siamese is actually performing, giving the contribution or not. So what we did was we trained the Siamese with too few pairs, and there we saw that when the Siamese learning was not proper, the rank correlation and measure error went. They were not performing. The model was not performing well. But with enough videos, with the Siamese was trained properly, the performance of the model increased. Third is an example of feedback proposals that we got. So the left hand side that you can see, that is a commentary which is given in the MTL action quality assessment data set. So when we talk about diving, the person has to be vertical so that the splash is minimum. But as you can see here, the person is not vertical at all, but somehow manages to have a small splash. So the entry level clip, the similarity is going down, and when it comes to splash, it goes back again because the small splash was achieved. And it's a bit of a crash landing. Again, the entry and splash, everything went down. So we proposed an evaluation metric to evaluate the feedbacks in terms of how good the model was to identify the faulty clips. So there as well, the precision and the recall of our system was far better than the state-of-the-art techniques. In terms of runtime complexity, our model was not too fast as compared to the other models, but it just had a sub-second performance, which was good. So in conclusion, we had a two-phase system which could do a human action scoring using relative scoring using deep metric learning. We had a higher rank correlation and feedback proposals and a weight protocol to evaluate the same. And our model provided better feedback. So the future scope technically immediately that I can see is that how well can we extend it to random and long-term actions where there can be certain misalignments at a very large levels. And in addition, because we can have towards production, we can see that AI-driven assessment systems for Indian-specific actions is a field that calls for a lot of collaboration, and we can work towards yoga, Kathak, Bharatanatyam, etc. With that, these are the references. Thank you. I would be happy to take any questions.
Thanks, Hitesh, for the interesting talk. Yeah, we have a question from Anandraj. How do you choose threshold value?
Okay, so I have certain backup slides. I'll just give you an idea on how we choose it for diving so that, yeah. So for diving, what we see is that the total deviation that we see across judges. So we have 5 judges in case of diving, and the variation that we see is 0.5. So and the top, the middle 3, the top one and the bottom one is just removed, and only the middle 3 are what is taken with respect to give the final score. So we see that the maximum possible variation can be 4.5. So that gives us a threshold of say 5 in case of diving, and similarly we evaluate it for the waltz exercise as well. So that is more from domain knowledge, that what variations can happen in the thing. Does that answer your question?
Hopefully, yeah. Because he was asking only about threshold. Yeah. So I have some questions. How many experts do you have for?
So for experts, we saw that the diving exercise had only 3 experts. When we saw so these Olympic videos, which was there, the data set, it was taken from Olympics 2012. So there we took up all the top 3 experts.
Oh, top 3 is it?
Yes.
I see.
So they were mostly like, for diving, it was mostly like 102.8 and then 99.7. These were the expert ones.
Okay, okay. So I have one more question. For example, if the camera is placed in a different location and the viewpoint is changing, will your approach work?
Yeah, so when we come to dive this gymnastic waltz, right, this was a more of random. So when we talk about diving, it was taken from a single view. But when we talk about waltz, there were multiple views that were there. So in that case also, it was not way too better, but yes, it was performing better. I mean, because the during training, the similarity matrix was considering all the viewpoint variations, right? So that is why it could learn the variations while for the scoring exercise also. Yeah.
My worry is because the expert videos will be based on particular view, right? So if I want to use those experts for evaluating some videos that are taken in our Indian condition or something, how well it will do, right?
Yeah, so in Indian conditions, that is where the challenge would lie, because there are too much of randomness in terms when we talk about Indian conditions, and we talk about
different condition. I'm telling different location and viewpoint, right? So
yeah. So in that case, the only thing that we can do is that we can include a lot of videos with different viewpoint variations, and the experts performing the same, and then the CMEs would be able to learn the similarity.
the why I ask is because expert videos are very rare to get, okay, and it's not easy to get, right?
True.
So you have to make use of the available expert videos and adapt it to your condition, right? So that's why I told, for example, like a medical diagnosis, you can't go and ask a doctor, can you annotate? They won't do, right? These are precious data. So how will you use this data across different, only test scenario is very different, okay? So the expert videos are coming from a same pool, right?
Yes.
Yeah, so that is actually maybe a good future work in this line.
Yes, yes.
Yeah. Thanks, Hiteshi. Yeah, we'll move on to the next paper then.
Sure, thank you.
Thank you. Yes, next paper title is From Strings to Things, Knowledge Enabled VQA model that can read and reason. So this work is from IIT Jodhpur and IISc and TCS, right? So this work was presented in ICCV 2019. Anand Mishra will be presenting this work. Anand?
Okay, am I audible?
Yes, yes.
Okay, thank you, Professor Babu, and thank you, Vision India team, to give this opportunity to talk about our work. I'm going to talk about this work on knowledge-enabled visual question answering model that can read and reason. Myself, Anand Mishra, and this work is done with my colleagues Ajit Kumar Singh from TCS, Sasank Sekhar, and Anirban from IISc Bangalore. So consider this image, typically taken in an outdoor environment. So if I ask, what do you infer from this image? Maybe you will directly read this text which is appearing, KFC. And the modern computer vision techniques also have advanced enough in last few years to do such things, such reading of the text in the wild, right? So and they may be able to read this text as well. But this KFC is not just a string. It's much more than that. As a human, when we see this image, we also use some kind of a background knowledge. For example, KFC has this kind of logo, and it is a brand of USA. It is a restaurant, and KFC produces chicken dish, and chicken dish is a non-veg food. So all such knowledge, which is not the part of the image, but it is more like a external knowledge, which we use while interpreting images. Unfortunately, most of the modern computer vision techniques do not leverage this part. And our larger thesis of this work is to bridge images and external knowledge and do some kind of downstreaming task, like, for example, question answering or visual question answering. So to be precise, this is the one slide which summarizes how we are different from what is in the literature. So given this image, traditional visual question answering models or visual question answering methods will ask like questions like how many cars are there in the image. Though that is interesting, but it doesn't really require this, means it's not something which is the only question perhaps which, or most interesting question perhaps one can ask. So leveraging text has got attention in the recent years, and parallel to our work, there have been some work which appeared in ICCV 2019 as well as CVPR 2019, which try to leverage the text and formulate the visual question answering problem. But most of these questions are not that natural and engaging, or you can end up asking question like what text is written on the red wall. In this work, we ask questions which require not only the reading text, but also accessing to the world knowledge in form of like wiki data, and then doing question answering on top of this. So for example, you can ask like, is this a Chinese restaurant, or which restaurant is this, and so on and so forth. So solution. So this for the solution, what we do is, so this is given to us, the image, a question, and the background knowledge. For background knowledge, we use the largest scale wiki data which is open source. So now given these, we first run the OCR, or like photo OCR, I would say, which is from VGG group, Gupta et al., which actually recognizes this text like KFC or pipe written over here, and if there's some more text wherever appearing, all these texts are recognized. We also run a scene proposal, which is nothing but some top K proposals. Top K is what this scene is representing, and that's sometimes useful for us. Given this, we use this word proposals, scene proposals, and this knowledge base or knowledge graph, and represent a smaller subgraph like this. And this subgraph is also the initial embeddings of this subgraph is obtained from word proposal, scene proposal, as well as the similarity from the question. Right. So once we have this initial embedding, we use gated graph neural network, which I'm going to describe now, to obtain a representation for this this graph. So how this gated graph neural network works in our case, we have this hidden representation, which is HB, which comes. Initially we have the initial embedding, as I said. These are word-to-vec embeddings, as well as the confidence of the OCR words or scenes are also appended to this XV. So this is initially the initial embedding, and this initial embedding is changed by the adjacency matrix, which is nothing but the neighborhood of these nodes. They change these embeddings to get active cells, and then traditional gated neural network formulation, where you have an update gate and reset gate and output gate. Once we have these, the hidden, the Tth hidden state. So this is the recurrent neural network type formulation, where Tth hidden state depends on the Tth T-1 hidden state, and these values called GV, and if GV is 1, this term vanishes, and you only take the output gate value. If GV is 0, this term activates, and this term vanishes. So we have SV, you take the previous hidden state. So once we have this hidden state representation, it's fairly easy to get the overall representation for the graph, which is again some kind of non-linear neural network and non-linearity on top of that. So once we have this representation, which is this OG, we have the question representation using language encoding, and this is a simple multilayer perceptron to train, which is trained from end to end, this part, the not word proposal and scene proposal, but the graph and graph representation part. And this is trained on the training data to get this kind of answer. So In brief, so this is since this is kind of a first work in this direction where we are talking about bridging knowledge graph, text recognition, and visual scene. So there was no data set available for this. So we introduced the first data set for this task. It is a quite large data set with 256K images and 1.2 million question answer pairs, and these are backed up by web scale knowledge base. And this is like a kind of a semi-automatically created because the knowledge base is quite what you say clean. So we can actually create such questions with paraphrasing the templates and all. However, some amount of annotation was required to read this text and all. So this is available for download. I will give the link towards the end of the talk. These are some sample images. Like you have a lot of variations in terms of appearance of these things and as well as questions, as you can see. And coming to the results, so we have a lot of ablation studies which is present in the paper. I would recommend people to see our paper. But here I'm briefly summarizing the result. The methods which does not require, which do not use the text, for example, the bag of words plus CNN or higher order co-attention networks, they do not perform well because these questions require reading text and bridging to the knowledge. There is another work which is memory network, which is traditionally used in NLP community, where you not only use the content but you also bridge it with the knowledge base. That works fairly well. Our GGNN formulation, when only text is used, is almost as good as the memory network. But our GGNN formulation, where we use not only the text but the scene proposal as well, that seamlessly integrates both scene and text, and it improves the performance by 4% or so. So this is the result. Coming to the visual qualitative results, this is one of the result where this BATA is recognized wrongly by the OCR as BAJA. However, this gets corrected using the knowledge base as BATA. And the visual content proposal says like it's a clothing store, shoe shop, and gift shop. Combining this, our method able to recognize this, like which shoe shop is this, and answer is BATA. This is one failure case where unfortunately like detected word is somehow did recognize this Lenovo as Lears, and the closest word in the knowledge base is Sears, which is a clothing company. And the another unfortunate thing happens here is even the visual content which proposal or scene proposal also says that it looks like a clothing store. So combining this, our method does not perform correctly here, and it says, does it sells clothes? But the answer is yes, but which is wrong because this is Lenovo. So to summarize, text KVQA is the first data set which leverages like scene text recognition, knowledge graph, and visual content, and it's a large scale data set which is available for download. We have shown the seamless integration of visual and textual cues as well as the knowledge based effects in GGNN formulation. And this is the first task where we have shown GGNN formulation for BQA over KG. The future directions are like, of course, there are a lot of interesting things on top of this bridge of knowledge and images can be done. So one of the thing is like multilingual. We can do this question answering on multilingual setting, especially of interest for the Indian community. Other things like knowledge aware captioning and retrieval, which we are also looking into as a future direction of this work. Okay, thank you very much. If you have any question, I would be happy to answer it now, or you may also email me. Thank you.
Thank you, Anvisha. Yeah, it was a very interesting work. Again, we have a question from Anandraj. How do you find the elements of the adjacency matrix and what is its size?
Also, this adjacence matrix is constructed on the knowledge graph. So this knowledge graph is not that like dense, I would say. These are sparse knowledge graphs. So your adjacence matrix is not usually big. So it's maybe somewhere like 4 to 5 neighbors, something like that. Yeah. So these are small adjacency matrix.
Another question from Bhavani. What is the weighting factor given to the word proposal and the scene proposal?
What is the
weighting factor given to the word proposal?
Yeah, so that is like kind of automatically learned over this GGNN. We do not a priori decide like what is the weight we are going to give. Yeah.
Okay. Again, a related question. For example, when I look at only text seems to be almost same as full model where you are using.
Yeah, that's true. I think that could also be the reason is these questions are like text is kind of very important. And yeah, so vision is not playing that much
Vision is not playing a major role there.
the role there. Yeah, so maybe that's a data set bias in a sense. These are questions which, like, if you read really, if you recognize things well, I think you are mostly done. But sometimes, yeah, sometimes it the vision part helps.
So is it actually your performance is based on the accuracy of this photo goes here? Because if something goes wrong there, then everything falls apart, isn't it? Kind of.
Yeah, but then you also have a reasoning over that knowledge base. So that is also sometime even if, yeah, if you fail in the photo here or text recognition thing, then yeah, means then recovery chance is very less. That's true. That I agree. Yeah.
So assuming, okay, that is their responsibility to get better result. Okay. So assuming they are 100% correct, what is your performance once it is photo?
So I think that result is there in the paper. I don't remember exactly, but it's somewhere around 65 or so, 65%.
I see.
So
Okay.
the reasoning, I think, is also sometimes challenging. That's
I was expecting above 85. Okay.
No.
Fine then. So any other questions there? Yeah. Okay, good to go. Thanks.
Thank you
for the nice, interesting talk. Okay, so we'll move on to the next paper. So the next paper is title is actually probabilistic word embeddings in kinematic space. So the others are from KLE Tech and others Jamada and D is supposed to present. I don't know whether he is going to present directly or going to play the video, as there was a request from him. So this paper was published in ICPR 2020. Sorry, present.
Hello everyone, my name is Adarsh Chandandi and I'm excited to present our work, Probabilistic Word Embeddings in Kinematic Space at the Vision India, held in conjunction with ICVGIP. So this work has been accepted at ICPR 2020. This work was done with my amazing collaborators, Rishabh, Professor Ramesh, and Dr. Umam. So we'll start off with the most basic question: how do we learn symbolic data? Because we know that symbolic data often exhibits properties such as hierarchy. Like consider if you, for example, if you have graphs, it has tree-like structure. If you consider lexical database such as WordNet, it also exhibits hierarchical taxonomy. So any deep learning algorithm that I choose, it should be capable of giving the
Thanks, Adarsh, for this presentation. Okay. Okay, so I don't think there are any questions. Okay. So how did you evaluate that this probabilistic word embedding, right, is better than our other word embeddings? It was not a bit clear there, right? You're there, right? Yeah.
Yes, sir.
Yeah. So you're proposing some mathematical framework for a word embedding, right?
Yes, sir.
So did you compare with other word embeddings how this is better than the other ones?
No, like we have compared it only with the word embedding framework that do something similar. Like we have a word embedding framework which does the same thing for hyperbolic space, that is the Poincare ball model. So they've done the same word embedding framework there, and the same formulation has been carried over using probabilistic framework by mapping it to Gaussian distribution. So we have compared it with these two methods.
Now, whenever you say word embeddings, the first thing comes to your mind is okay, this word to wake or glow kind of thing, right?
Yes,
So
sir.
you are
Yes, we
not
have.
doing anything with this kind of word embeddings.
No, sir, we have not compared with that kind of word embeddings. So essentially, what we are trying to do is we are trying to infer the hierarchical taxonomy of the WordNet dataset. Like we try to reconstruct that hierarchical taxonomy with minimal distortions.
Yeah, without that kind of a word embedding, how practically your method can be useful? That is the question. Because word embedding means I just give the word, you give me one embedding, right? And the
Yes,
neighbors should look similar, and then okay. So if you, unless you give this kind of a word embedding, I cannot use practically, right?
Yes.
Okay.
So like essentially, the goal is my whatever geometrical space that I'm choosing to learn this word embedding or trying to learn the hierarchical relationships of the data. So that hierarchy should be preserved. So that is the like the general theme of the work.
Oh, okay. Because even the hierarchy we are getting from actually from the data, right? Most of the time.
Yes, that hierarchical nature of the data should be preserved by my embedding space.
Okay. Fine. So I don't see any questions. So if there are no questions, yeah, thanks, Adarsh.
Thank you, sir.
So we are coming to the end of this Vision India, the last part of Vision India session. So let's thank all the participants, Vision India participants for their presentation. And now let me hand over this session to Vineet. Yeah, Vineet.
Perhaps I can take over.
Yeah, Chetan, yes.
Yes. Yeah. Thank you, Venkatesh. Thanks for your help and chairing this session wonderfully. Thanks for your help. I also would like to thank again all the speakers for the Vision India wonderful work, and I hope we'll get to see many more such works in the future. Also, as Venkatesh was saying in the beginning. So I guess we are in the
Kind of. We should impose a constraint there. Every 5 local papers, they should have one submission.
Yeah.
Top tier venues.
Increase the turnout rate. Yeah, Parag, would you like to take over now for the closing ceremony?
Am I audible?
Yes.
Yeah. So I would like to wait for a few minutes. We are waiting for a General Chair, Shantanu Chaudhary, to join, and then we'll do the closing.
But I see the participants number 24. Only that many people are there. 24 plus 8, 32.
Yes, for now, yes, that is the number.
Okay. You didn't hide.
We touched about 100 at some point, and then it keeps fluctuating throughout the day.
Looks like it's like a century. Difficult to hit.
Yes.
Live over YouTube as well.
Yeah, he has added the YouTube number. That's what he said, +8.
I also see, but that's about 10 or 15 because of. Maybe IIT Jodhpur, all the students should mandatorily first attend there. Go beyond.
So we had lots of registrations. We had around 200 registrations, but I don't know where the 100 people are missing in action. At least.
Yeah, that is expected. Yeah. So, yeah, it's a good hit rate. 50% is.
Yeah, so when it is happening at a location, you can bind them in one place, but with this, you can't do anything.
At least during lunchtime, you will find them.
Yeah, actually, session is also going on. That is a problem. Even students, they are bogged down with their assignments and lectures and all.
Classes have not ended
Classes
everywhere.
are the biggest problem actually right now.
Yeah.
Even faculty is also busy with classes and all kind of office stuff is coming. So it's not like the traditional winter time that you get earlier.
In fact, I was attending parallelly 2 meetings. So that's now it became part and parcel of our life.
Yeah, we could see that you are attending.
It's the same story everywhere.
Workload almost tripled actually because of this online thing.
It's multiple screens, your desktop, your laptop, your phone screen, everywhere there is something else.
You need more devices now.
Then if you are at home, then you have online classes for the kids going on, then they take over some of the screens.
Correct.
Let me share. Can you transfer presenter controls to me?
Yeah, Akash, please make Parag as a presenter.
Yeah,
you are.
Visible? The moment I share my screen, my participant list disappears. So we finished bang on time. We should not have kept a break before the closing ceremony. So otherwise, we have timed this really well. Gaurav, where is your background today?
Yeah, actually, I came back from Goa actually.
So now back to Jodhpur.
The virtual background is not there. So we just wait for 2 more minutes, then we can start. Oops. Okay, so we are on time. Am I audible? Hello?
Yeah, yes, of course.
Okay. So, so we are at the closing of ICVGIP 2020. Thank you everyone for being around and attending the conference. So I quickly want to thank uh, people who made this conference a success. So first, we would like to thank all our speakers. So for the plenary talks, Vining Go, Carsten Rother, and D.D. Zelnick Manor. For the invited talks, Shamak Yusefi, Karan Sikka, Walter Schneider, and Sudhir Pathak, Xiaojun Chan, and Tanaya Guha. For the tutorials, Rajiv Ratan Shah and Yaman Kumar, who soldiered through multiple power cuts. Then Madhura Ingal Halikar and Bhushan Gorotikar, and Shubham Tulsiani. Then for the industry panel, we had a very nice set of panelists, Anu, Akshay, Balamudidhar, Stuhin, and Yukti. And then we had the startup speakers, Paurush, Dipanshu, Altaf, Nilima, and Sandro. We had the visual data challenge teams who won the challenges, who gave talks, Future Sight, Tiger, and Metasec, Batman Returns, Nearmat, Night Fury, and Genex Tech Wall. And the IUPRI Best Dissertation Award winners, Kondra Reddy and Badri Narayan. And all the Vision India speakers, Bhasha, Jayashri, Kuldeep, Sarthak, Jogendra, Rudraba, Anirban, Bhakti, Daksh, Hiteshi, Anand, and others. Thank you for joining us and for giving very nice, interesting, and informative talks and engaging with the audience. Then I would like to thank people without whom these sessions would not have been possible to manage, which are all our session chairs. For the plenary talks, PJ Narayan, Subhashish Banerjee, and Shantanu Chaudhary. For the invited talks, Arnav Afzal and Abhinav Dhal. For the tutorials, Aditya Nigam, Arnav, and Siddharth Chaudhary. For the industry panel, Dipender Sekho, who moderated that panel. For the startup interface, Uma Mudanagudi. For the visual data challenge, Saket, Anand, and Gaurav Sharma. For the IUPRI Doctoral Dissertation Awards, Bhavatosh Chanda. For Vision India, Vinit Balasubramanian, Vinay Nambudri, and R. Venkatesh Babu. Then I would like to thank all our committee members on behalf of all program co-chairs, Chetan and Shubhranshu and myself. I would like to thank general co-chairs for their guidance in creating this program for the conference, our plenary co-chairs in helping us finding the plenary speakers, the tutorial chairs for helping us finding both invited talks and the exciting tutorials that we had, the contest co-chairs for setting up the contests and getting the ball rolling, and allowing so many students to participate and become a part of the contests. The Vision India chair for looking at all the Vision India submissions and choosing the Vision India papers and getting them all here. The industry co-chairs for finding the panelists who participated in that panel, for really driving that panel discussion. The startup interface co-chairs for listening with the startups and getting them and all the interesting feedback that we got from the Angel India network. And finally, Gaurav seems to have shut off his video right at this time. Gaurav, come back. The organizing chair, Gaurav Harit, and his team from IIT Jodhpur, Anil Tiwari, Anand Sharma, Yashasvi Verma, and Rajlakshmi Chauhan, and Akash. Can Akash turn on his video? So Akash has been our man behind the scene. He is been managing the WebEx event host role very efficiently and promptly. Thank you, Akash. A big thank you to you. Without you, this would not have been possible at all, right? And finally, thank you to all our audience who listen to us. Yeah. Listen to us on WebEx and on YouTube and asked very interesting questions, engaged with the speakers, and really all speakers come to deliver talks because in order to find appreciative audiences. So I'm sure that they did find a very nice audience here. So thank you for being an excellent audience. And we hope that you enjoyed the conference a lot. Right? And for the concluding remarks, I would like to hand over to Professor Shantanu Chaudhary now, so that he can do the concluding remarks and formally close the conference. Over to you, sir. Your audio is not coming through.
Thank you, Parag. Let me thank all the participants who have all attended the sessions on 3 days. I hope and many more might have watched these sessions on YouTube. And we are really grateful, and we really thank them that again that they have been part of it. I think this was a unique experience for all of us, and I think people have loved it also. And we at the same time we understand and we appreciate the fact that we have to be physically present in many cases to have true interactions, true understanding of each other's work, generate new ideas, build up collaborations. But also at the same time, this online mode gives us advantage of communicating, advantage of knowing things without really spending our energy creating a bad carbon footprint because of travel and otherwise. We can avoid all those things and keep it green, and still we can get in touch with each other. So all of these initiatives therefore has both positives and negatives. I think this experience in midst of pandemic crisis, these ICVGIP 2020 plenary talks, then seminars, plenary talks, invited talks, and other events put together was a different experience from that of a conference for all of us. It was very useful experience. And keeping that in mind, we look forward to a full physical conference in 21. But I'm going back to again that possibly we shall have a blended conference. Even if all restrictions are all restriction disappear, pandemic disappear, and we can come together and interact together, even then, maybe blended mode, having some of the participants online can enrich even a physical conference. I think that's what has been established through our pure online experience. And in 2021 conference, I'm extending invitation to all of you on behalf of the organizers. And at the same time, I'm promising we will possibly get a completely different experience with physical and virtual being put together at the same time. I think that is the reality towards which we are moving, and that will be there with us for some time to come. Thank you.
Thank you. So yeah, with this we can close the conference and have a very happy New Year, everyone, and have a pleasant 2021. And we'll see you again at Jodhpur if everything is okay for ICVGIP 2021.
We shall at least have some of you at Jodhpur. That's for sure.
Yes.
And thanks to Parag for hosting this wonderfully, coordinating all the stuff, managing. Thank you, Parag.
And 3 cheers to the program committee, organizing committee again. They've done a great job. And happy New Year to all of you.
Okay, thank you. Bye.
Bye.
So Happy New Year to all of you. Happy New Year.
Chalo. Bye, Gaurav. And bye, Akash.
Bye Parag, bye.
शक्ल दिखा के bye कर ले.
Yeah, Akash was asking me to close the conference. So I just said, yeah,